everyone, welcome to our Deep Learning with Keras and TensorFlow course by Simplilearn. Deep learning is behind some of the most exciting advancement in technology today. And learning Keras and TensorFlow is a powerful way to dive into that field. In this course, we will start by exploring how model predictions work and how sigmoid activation helps you sense of those predictions. We'll also teach you how to interpret probabilities in machine learning so you can understand what your models are telling you. We will cover data pre-processing with NumPy, which is crucial when working with large data sets. You'll also learn how backpropagation works and how it helps train a neural network. We'll also look into how adjusting the learning rate can improve your models and help them learn more efficiently. As we go on, you will understand epochs and forward propagation and work with the fashion MNIST dataset, a fun example to practice deep learning techniques. We'll also discuss hyperparameters and how to configure models for better performance, plus how to debug and analyze errors that may pop up. Finally, you will dive into the convolution operation, which is key for image-related tasks, and learn how to fine-tune hyperparameters to get the best out of your models, all while tackling the challenges that come with neural network training. And by the end of this course, you will have the skills to confidently build, train, and optimize deep learning models using Keras and TensorFlow. So let's get started. Before we move on, here's a quick quiz question. What does deep learning primarily help us with? Your options are making websites, making predictions from data, creating text documents, or organizing files. Let me know your answers in the comment section below. Before we get started, here's a quick information. If you're interested in boosting your career in 2026, Simplilearn's professional certificate in data science and generative AI program in partnership with Purdue University is the perfect place to start with. This program covers everything from Python and machine learning to generative AI and ChatGPT, giving you hands-on experience with cutting-edge tools and technologies with Purdue University certification, IBM's industry-recognized courses, and Simplilearn's Job Assist to help you connect with top employers. You will be ready for high-paying roles in tech, finance, healthcare, and many more. So hurry up and enroll, and you can find the course link below.
Let's get started with this. So as we understand, deep learning is nothing but an extended field of machine learning. And it has proven to be useful in the domain of text, images, and speech. So the collection of the algorithms implemented under deep learning have the similarity with the stimulus and the neurons, exactly how they are seen in the human brain. And deep learning has extensive applications in computer vision, language translation, speech recognition, image generation, and so on. So these set of algorithms are simple enough to learn in both a supervised as well as unsupervised pattern. So if you actually look into it, a majority of the deep learning algorithms are based on the concept of artificial neural network. And the training of such algorithm in today's world has been made possible because today, number one, we have huge amount of data. Number two, we have huge amount of processing power. Number three, we have huge amount of storage as well. Because these three things are there, deep learning actually geared up. Else there was no reason for deep learning to gear up so fast. So deep learning has these all advantages to say. With additional data, the performance of the deep learning algorithm keeps on improving only. So if you see over here, this is mainly your machine learning, where you see as the amount of data increases, performance increases, but after that you see it stabilizes. But with deep learning, initially the performance is not as great as machine learning, but as the amount of data increases, the performance of deep learning algorithm keeps on increasing. So deep learning loves data. Deep learning basically loves data. That is something which is very, very important point to be noted over here. So whenever you have huge amount of data, you have deep learning. Then going ahead, see the term deep in deep learning refers to the depth of the artificial neural network architecture. Yes, something like this. So in any neural network, you will have an input and you will have an output. Specifically, this is the input layer and this is the output layer. In between this layer and this layer, we call them as hidden layers. So specifically, I can call this as hidden layer 1. I can call this as hidden layer 2. Each ball is called as a neuron. So this is a neuron, this is a neuron, this is a neuron. And input layer, this is the input. There are no neurons in this layer. So although they have drawn circle, most of them draw circle, but ideally it's not like that. So specifically, if I have to redraw this figure for you, you can consider this is your input 1, this is your input 2. I'm just assuming this as x1 and this as x2. And then one layer, right? So this is connected here, this is connected here, this is connected here, this is connected here, this is 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 here. Finish. So that's our output layer. That's our input layer. This is hidden layer 1. This is hidden layer 2. Then here. So I say the term deep in the deep learning refers to the depth of the neural network. And learning basically stands for learning through the artificial neural network. You know how these networks learn? They initially, imagine this, that I have a book to study. So let's say this is the book that you have to study. So consider this network to be nothing but you. What you do, you take this book, you studied, then you give an exam on that book. Once your study is over, so here, while doing this forward propagation, you basically study. And while doing this backward propagation, you give exam. So you are studying for the first time and you are giving exam for the first time. That is exactly what I say you have studied once. This is exactly what I say you have studied once. And you keep on repeating this process multiple times. So this is forward propagation and this is backward propagation. So one forward propagation and one backward propagation is nothing but an epoch, right? So this is nothing but called as forward propagation, and this is what we are calling as backward propagation. So one forward and one backward propagation is called as an epoch. So basically, what you do is you study for n number of epochs. So I say repeat for n epochs. That's exactly how a human studies anything, right? You don't study anything only once and say that, okay, now everything is saved in my brain. You keep on studying the same thing again and again. So neural networks are also doing the same thing again and again. See, these all things are like a story. So you have to understand it step by step, slowly and steadily. So one forward propagation is studying once, one backward propagation is giving exam on that. So you become better on it. So you can repeat this study, exam again and again. So over here, this network is called as a deep network, and this network is called as a shallow network. Again, you see here we have input layer, here you have output layer, and here is what you have hidden layer. But the difference is in shallow network, you have only one hidden layer, and here you have more than one hidden layer. Okay, here you have only one hidden layer, and here you have more than one hidden layer. So next. So deep neural networks are capable of what? See, the deep neural networks, they are mainly capable of discovering latent structures, or I can also say feature learning from unlabeled data and unstructured data, such as images, which is nothing but the pixel data. We have documents, which is the text data. You have files, which can be nothing but audio or video. So basically, deep learning neural networks can automatically extract features from the data. In machine learning, I remember we had to extract the features, like in Titanic data set, we extracted features by ourselves, right? So from the data sets itself, I remember we engineered the feature for extracting uh, price. We engineered feature for extracting the passenger class, family class, etc. But in deep learning, all of this feature learning happens automatically. So I would say automatic feature learning. It can do automatic feature learning. So how deep is deep? See, we often hear the term deep and we instantly get intimidated by it, but there is not much difference between a shallow and a deep network. So over here, you have only one hidden layer, and over here, you have more than one hidden layer. So a deep neural network is simply a feed-forward neural network with multiple hidden layers, right? Multiple, basically, multiple means more than one. That is the basic difference in between the two. Next, we get into the basic structure or the history of the neural network. Now, here, see, each unit or a neuron is simple. Now, what you see on the screen right now is a biological neuron, right? So, if you consider a human brain, our human brain, it has 100 billion neurons, and these are with 100 trillion connections. So the strength and the nature of the connections stores the memory and the program which makes us human. So the neural network ideally is a web of artificial neurons. This is the biological neuron. Then I say ANN is nothing but a web of artificial neurons. So here, see, let's understand how does it work biologically. So let's say uh, this is you. So now let's say here, if I'm pinching you, this is the point where let's say I pinched you. What will happen? Signals travel from here to your so-called brain, right? Signals travel from here to your so-called brain. Oh, it's so bad now. But when signals travel from here to your brain, then where do they go? It basically goes to the dendrites. This one. These dendrites receive the signal and then the signals get processed in the neuron. This is exactly where the signals get processed. Then if the pinch was very hard, hard in the sense outside your bearing capacity, I pinched you really very hard and you just can't resist the pain, then this nucleus will decide that is that pain really harsh? If yes, it will immediately inform the axon to go to your right hand, and quickly go and rub over here. And if the pinch was soft, then this neuron decides that you can ignore it. So this is how the neural network used to work. So if you now see in, so I was saying artificial neural network or perceptron was first developed in the year 1950 by Frank Rosenblatt. And this looks something like this. There are inputs, there is an output. So basically, it takes several inputs, produces a single binary output if the sum is greater than the activation potential. So the neuron is set to fire when the activation potential exceeded and behaves as a step function. So the neurons that fire along the uh, signal to other neurons are connected to their dendrites, which in turn will fire. And that's how it continues step by step. So now this is how it looks like. So now let's understand how does it actually work. It's very, very easy. So remember this thing in very simple words. We are trying to understand what is a neural network. So the neuron which you saw, right? So if you see, this is the artificial neuron. Inputs come over here, get processed, and then signals flow from here. This is a biological neuron. In the artificial neuron, you have inputs, processing, which is nothing but the nucleus. And this is where the output comes. So now, let's understand this with the help of a simple example. So here, the neurons can be sketched something like this. Input. In machine learning, you remember if I was talking about the iris dataset, then I had sepal length, sepal width, petal length, petal width, and I had the class of the flower. That's how my dataset was. And this dataset consisted of 150 rows and 5 columns. Then we divided this data into train and test. This was independent variable 1, 2, 3, 4, and 5. So this is also very much similar to that only. This is my x1, x2, x3, x4, and you get over here an output. So basically, earlier the machine learning model was understanding the relationship between independent variable and the dependent variable. But over here, this is the independent variable, this is the dependent variable, and it is a neuron who is understanding the relation, and that too not one time, but it does that multiple times, or I can say that it does this for many epochs, where we know that an epoch is nothing but a forward propagation and a backward propagation. Okay, now let me uh, come to Mannu first. Before I forget, these layers are derived from another system. Not really, Mannu. We are yet to get into the mathematics of what you are asking. Slowly and steadily, uh, the story of neural network will be something which will be little bit hazy for you, at least for next, I would say, 6 hours. So, you can imagine this neural network to be like a movie which goes in the future and comes back. Just like I'm sure you might have seen the movie Three Idiots. You remember that, right? I hope, Manu, you have seen that. Yes. So we see that till the last, the movie keeps on going, sometimes in the future, sometimes in the past. Again, it goes into the future, again, it goes into the college life. So the entire movie becomes clear at the end. So here also in neural network, the story is there are a lot of small, small connected things which you will understand step by step, and our end will not come at the end of the syllabus, of course. Our end to understanding this working, you can expect a total time span of around 8 hours from our today's session to understand how does this thing work. So basically, we need to mathematically understand what happens in forward propagation and what happens in backward propagation for us to get an answer to your question. So slowly, steadily, it will be clear. So don't worry about that. Right? Yes. Now let us actually look into how does a neuron basically work. See, mm, let's consider this. So I'm drawing a very basic structure of a neural network, and precisely perceptron or neuron. Hmm? It has three inputs and it has an output. So the output over here can be either 0 or 1. So the thing over here is if the summation of Wj xj is less than is equal to threshold, it is 0. Else if the summation of j Wj xj is greater than threshold, the output would be 1. So let's understand how. So let's say I'll take a very nice example to make this thing easy for you. Remember this example for lifetime. So here, suppose uh, weekend is coming up and you heard that there is a Punjabi food festival in your locality. I'll come to it, Raj, sometime. Suppose a weekend is coming up and there is a Punjabi food festival in your locality. So now the thing is, how many of you like Punjabi food? Now let's say you are trying to decide whether, okay, so over here, the, the, task is, the, 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 you are trying to decide whether I will go or I will not go to this Punjabi food festival. And your decision depends on the following factor. Factor number one is the weather good? Yes or no? Now, when I say weather is good means, see, if it is not raining, according to you, it is good. If it is raining, according to you, it is not good. Or if it is too hot, according to you, it is not good. And if it is too cold, according to you, it is not good. So you decide what is good and what is bad. Second, does your partner wants to accompany you? Yes or no? So is your girlfriend, is your boyfriend, is your wife, is your husband ready to come with you to the festival? Yes or no? And the third one is the festival near a metro station? So let's assume that you don't have a car. So obviously you want the festival to be near the metro station. So that is the next thing that you are trying to decide. So your decision depends on the following factors. Your decision depends on the following factors. So now, you are trying to decide whether you will go or not to this festival. Okay. Now a little bit of tantrums. Let's say you are such a person, that uh, let's say your wife says, Darshan, let's say I am such a person that my wife says that Darshan, I'm not coming. And I'm like, okay, no problem, I will go. The festival is not near the metro station. And I'm like, ha, theek hai, chalega. I will travel somehow. Ha, I will go. But if it is raining, if it is raining, then dare I keep my leg outside the house. I just hate rains. If it is raining, I am not going to step out of the house, not even little bit. I just hate rains. I just hate rains. If it is raining, I'm not coming. So what does that say? It basically says that for a person like me, even if my wife says, Darshan, I am not able to make it up, it is okay. I mean, chalega, nahi yaar, mat aao, I'll manage. It's not exactly near the metro station. That is also fine. I will adjust. But if the weather is not good, I will not adjust. So over here, among the three factors, I realize that weather is something which is more important for me as compared to the other two factors, at least for a person like me. And that is exactly what we quantify by giving weights over here, Raj. So, obviously, if weather is more important, because these are the three factors, right? This is the factor x1, yes. This is the factor x2, and this is the factor x3. Among these three, this is more important to me, as I told you, and this is relatively lesser important. So what I do is I give a higher weight to this and little lower weights to this. Now I can give any number. These all are just all imaginary number. It is just that I have given a higher value and little lesser value. Again, this can be 2, this can be 1 also, or this can be 3, this can be 2 also. These all are imaginary values which I have given. Are you all with me so far? One is the deciding factor, and the second is how much that factor is important. Everyone clear so far? Right? Yes. Very good. Now, over here, I also did say, that when I'm pinching you, let's say a girl pinches my thick skin, I won't feel that pinch a lot and I can just smile and ignore. But if I pinch the soft skin of the girl with the same intensity, she shouts, ouch! Am I correct? Am I correct? Right. So essentially, what I am trying to say is the pain bearing capacity of everyone's skin is different. And so is a similar funda which I am introducing over here, which is the threshold bearing capacity. And here I am assuming that the threshold is phi. Assuming this is assumed, and that is what is the figure right now. So let's try to come to the next slide. X1, X2, X3. That's the output. W1, W2. Now, what did I say? The output can be either 0 or 1. It will be 0 if summation W dot X is less than threshold. It will be 1 if summation W dot X is greater than threshold. So over here, let's consider a scenario. The weather is not good. So 0. My wife says, Darshan, I'm ready to come with you. And it is next to the metro station. So I want to decide. So for deciding, I have to do W into X. You know what is W into X? W into X is nothing but W1 X1 plus W2 X2 plus W3 X3, which is 6 into 0 plus 2 into 1 plus 2 into 1, which is 4. Now 4, that's the output 4. Is 4 less than equal to threshold or is 4 greater than threshold? 4 is less than equal to threshold. So if 4 is less than equal to threshold, tell me on the basis of this, output would be 0 or output would be 1? Output would be 0 or output would be 1? 0. So I say output is equal to 0. That means I won't go to the festival. Am I correct? My decision over here is I am not going to the festival. Right. Let's consider the other scenario. My weather is good, but wife is like, Darshan, I'm not coming. I am busy in office work. And the third factor, it is away from the metro station. So this becomes 6 into 1 plus 2 into 0 plus 2 into 0, which is 6 plus 0 plus 0, which is 6, which is greater than thresholds. Therefore, the output would be what? Output will be 1. And therefore, I will go to the festival. You tell me, if my wife is not coming, sorry, if the weather is not good, wife is coming, but the festival is away from the station. Tell me whether I will go or I will not go to the festival? No, right? Correct. Tell me that weather is good, my wife is coming, but it is away. Whether I will go or not go. Yes, I will go. Right. Now I'm changing the ink color, and let's say if I am assuming the threshold over here as 3, if I'm assuming the threshold over here as 3, and let's say the weather is not good, but my wife is ready to come and it is next to the metro station, tell me whether I will go or not. Threshold is 3 now. I'll go. Yes, very good. I'm not computing. Yes. Okay, I will go. If the weather is good, but my wife is not coming and this is also not in my favor, then will I go? Yes. Okay, I will go. So basically, what am I trying to say is by varying the weights and the threshold, we can get different models of decision making, right? So in other words, it is a different model of decision making if I am changing the things. After that, let us try to do a little bit further modification. Now what was this formula? If you recollect, so the formula over here was something like this. Output can be either 0 or 1. It will be 0 if summation Wx is less than equal to threshold. It will be 1 if summation Wx is greater than threshold. Now, what did researchers say? That this is complicated for machines. Therefore, we need to simplify this. So they said, consider W dot X less than equal to threshold. Therefore, I can say W dot X minus threshold less than is equal to 0. Then they introduced a new term called as bias. And bias is minus of threshold. Therefore, this equation became Wx plus b less than is equal to 0. So I can kind of say that now this can be modified where I say output would be 0 or 1. It would be 0 if W dot X plus bias is less than is equal to 0. It's 1 if W dot X plus bias is greater than 0. Yes. So this is what we understand. Now, why is this better? The reason this is better is machines love zeros and ones. It's much easier for a machine to compare against a 0 value. If the output is greater than 0, so basically if this is greater than 0, then 1 is the output. If this is not greater than 0, 0 is the output. This is far, 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 far convenient for a machine. Like, consider an example. So, consider a perceptron where the bias is this. I have x1 with the weight -2, x2 with the weight -2. That's the output. And what was the formula for output? It can be 0 if w dot x plus b is less than 0. It would be 1 if it is greater than 0. So over here, let's consider x1 and x2. If it is 0, 0, then let's perform one calculation, wx plus b, which is -2 into 0 plus -2 into 0 plus bias is 3. 3, yeah? It will not be -3. Don't consider the bias as -3 because I clearly said bias is minus of threshold. So going forward, I will never ever talk of a term called as threshold. You will only talk about bias. So threshold ko bhul jao. Forget threshold now. You will not see anywhere in the documentation as well going forward. Everyone will talk about biases only. So this comes out to be 0 plus 0 plus 3, which is equal to 3, and 3 is greater than 0. Therefore, I will go to the festival. 1, 1 minus 1. Okay. 1, 1 minus 1. 1 is greater than 0. I will go. 1 is greater than 0. I will go. -1 is less than is equal to 0. I won't go to the festival. Okay. Now tell me the same calculations with bias. Sorry, not bias. With the weights as let's assume this to be 2, and let's assume this to be 4. Tell me go, not go scenario based on this. So this was one thing. Now, if we now a problem. So the problem, if I show you your family photograph, let's say if I'm showing you a family photograph, your family photograph, let's consider this is your family photograph, and I am assuming that this is who you are. So I ask you that, hey, you know what? Tell me, where are you? So let's say, today you are 25 years old. And this is when you were just 5 years older. Let's say this is when you were just 7 years old. My question over here to you is, will you be able to recognize how you looked 7 years back? Your own photograph in a family photograph. Do you think you will be able to recognize? Because you are saying yes. My question is, how do you recognize that this is you only and not someone else? How does your brain recognize that this is you and not someone else? face patterns, features, fascia features. I had seen my photograph before. Features we have in mind in the memory. So, how does your brain store the features inside this box? How does it get saved? Right? I'm getting little deeper into it. Memory by seeing multiple times in the neurons, cerebellum. But how is it saved in the cerebellum? How is it saved in the neurons? How is it saved in the memory? I mean, what is the format in which the features are saved? 1 0. Some weights. Links are made permanent, but how? You all are speaking some technical terms. If I say that in simple words, as a layman, tell me how is it saved in your in your brain? You say, I have watched multiple times, I have learned features. How does your brain even know that this is a feature? How does your brain even know that, okay, this is a nose, this is a eyes, this is a left eye, this is eyebrow, this is lips? How does your brain know that? Learning? What is learning? How much soever you try to justify, we ourselves doesn't know how our brain recognizes us in a old photograph. Technically, however I say, so you will say that, okay, something is saved in the form of a chemical in my brain. So how is the chemical storing that? We have absolute no answer to all of these questions. We have no answers to all of these questions. And that is the most important thing. We ourselves don't know how our brain is working. Anand says building from correlation or similarity or from what is known. What is correlation? And how does your brain know how to correlate? How does your brain even know that this is how I correlate? From whatever is last known. So your last known information is somewhere saved. In what format is it saved in your brain? How much soever we try to justify it, we won't be able to actually get the correct answer to that. Human brain is far more complicated than what we can think of. So at some point of time, you are likely to say, Darshan, please shut up. I don't know how is it saved in my brain, but I am pretty sure about the fact that this is me. Even when you say electrical switch as a storage, have you ever seen that electrical switch, Manu? You ever saw that? This is all bookish knowledge which your teacher has taught. Electrical signals, waves, traveling, electromagnetic waves, electromagnetic induction, all of these are bookish things. We all just understand that how the information is coming out of the brain, we don't know, but we are like, I am sure this is me. How I don't know, Darshan. So here, what am I trying to make you realize is, what am I trying to make you realize is we ourselves does not know how our biological neural network is working. But we all agree to the fact that we know how a artificial neural network is working. Correct? We didn't know how a biological neural network is working, but we completely understand how does a artificial neural network work because you only solve two problems on it. Yes, and this is the problem. This is the problem. What are we here for? We are here for building an artificial neural network. This network is not even like a network. Anyone can do some plus and multiplication and get the output. So are we really saying that we are able to build an artificial neural network? Answer is no. A neural network is the one which we ourselves doesn't know how it is processing, but here it is clearly visible. So basically, I don't want it to be predictable. So we need to now change a few settings. Now, what am I going to do is I want to show you the secret sauce of the neural network. Another imaginary concept for now. We call it as the activation function. This is called as the secret of the neural network. What it does is it converts something which is predictable to something which is unpredictable. Deep learning is entire about fuzzy logic. That's absolutely correct. So I was saying over here, now what am I going to do? No, this is what you considered as the secret of the neural network. So what is happening right now? What we learned till this point of time was this part. This is what we learned so far. And this is what is the activation function. So till this point of time, I said that the output is predictable and I want the output unpredictable. I want the output unpredictable. Okay. So now, see, understand what is the problem. If you recollect, linear regression algorithm, याद है सबको? You remember the linear regression algorithm? Y is equal to mx plus c. What we studied during machine learning, right? Yes. So now I remember taking you to this concept of slope of the line, where I said in linear regression algorithm, this is what we did. I remember I had taken several points, and for all of the several points, we added a neural network. So we created a equation, which is nothing but the equation of the line of best fit, whose equation was of the form y is equal to mx plus c. In this case, m is 0.5 and that c, let's say 2.5. And this was the equation of the line which was used for predicting the future things. Now the problem, if you see right now, the equation that we are having is output is equal to w into x plus b, x wm, and this and this. So this is the equation which is linear, straight line, which means that what we have over here is also linear, which means that the output of the neural network right now is linear, and this linear output cannot be considered as the working of how a brain is. No. So the thing is, I don't want the linear output, and that is exactly what the activation functions do. What they do is basically, whenever you have inputs x1, x2, x3, what output you get is linear. What happens over here? Here, w into x plus b happens, and what you get is a linear output. You pass it through the activation function, and the final output that you get is a non-linear output. Now, how? Well, there is a lot of mathematics over here. If I actually take you through the activation function in the TensorFlow libraries, yes, these are the various available activation functions. So many are there. All of these are responsible for converting a linear output to a non-linear output. Can you practically learn the mathematics of each of this? Well, the straight answer to that is no, right? So will we be skipping the mathematical part? No, I will be taking you through the important mathematical part. It's not that we are going to purely ignore it, but how much so ever you try to discuss that in detail, you are definitely going to forget. So, there is a typical way we need to understand how this works. But that's too early to talk of. But yes, we will be going through these all things. But sir, why do we want from predictable linear output to unpredictable non-linear output? Because we are here not to implement linear regression once again. Basically, if you look into this, Amitoj, whatever I explained you over here, right? Whatever we have understood on this slide, in a simple way, I can actually say that I have fooled you all so far, because technically what we are implementing is nothing but linear regression algorithm, mx plus c, na? If it is greater than 0 or less than 0. Without knowing, I successfully fooled you all, because this is nothing but linear regression. Yes or no? This is nothing but linear regression. Without even you realizing, our brain does not work linearly. It thinks of n number of possibilities. And therefore, we don't want the output to be linear. Just like I explained the example of that photograph, where we ourselves don't know how our brain is able to predict where we are in a photograph. In the same way, here as well, we want the neural network to be correct, but we ourselves doesn't know how is it actually predicting the things. That is the reason we have to add this. The performance of the neural network, if you don't add an activation function, would be even bad than a normal machine learning model. It won't be even matching the machine learning model. So the secret sauce of the neural network is the activation function. And hence we need to add this thing, Amitoj. Getting that? So it's a long story, as I told you, right? Slowly, steadily, you will understand it. But let me tell you, without activation function, your neural network will just not function as expected, because you are doing nothing but W into X plus B, which absolutely does not serve the purpose. So to uh, convince you more, what am I going to do is, once we come back, I am planning to get started with a little bit of hands-on to make you understand how does it work, by leaving for some point of time theory aside and focusing on the implementation aspect as well. So, it would be basically covering both at the same time, theory as well as the implementation parallelly. So, how I will let you know as and when we go ahead. But yes, we will be looking into all these things. So, you will be little bit more convinced rather than randomly going ahead with the things. So, But you cannot create a neural network without an activation function for sure. How? You will understand as and when we go ahead. I'll explain you with the help of a very simple problem. Is the activation function a part of the neuron or it is outside it? Yes, that's a good one. So here, if you see, this is how I wrote it, clearly indicating that it is not a part of it. But going forward, I will never draw a figure like this. I will always draw a figure like this, where there will be inputs and there will be output. What happens internally is W into X plus B and activation function applied over it. So this is the standard and the default figure of a perceptron from now onwards. Anytime you think about a perceptron, you will always see a perceptron like this. So expect this visualization to be like this only. So the first notebook is a linear classification. The first one is I am importing the framework TensorFlow as TF. And then I'm printing the version of TensorFlow. It doesn't take so long to import, but sometimes it happens. Even if you are having a different version of TensorFlow, that's not at all a reason to worry about. So this is what we have. And let me see what is basically TensorFlow. So TensorFlow is an open source machine learning framework which is developed by Google. It provides a comprehensive ecosystem for building and deploying machine learning models, particularly deep learning models. It supports various tasks such as image recognition, natural language processing, time series analysis, making it very versatile for data scientists and the developers. TensorFlow is widely used by both research and the production environment because it is very scalable, flexible, and there is an extensive community support as well. That's an advantage that you get with TensorFlow ideally. It allows complex neural network and optimize them for performance and deploy them on different platforms, including mobile as well as the cloud services. Then this framework works on tensors, which are multi-dimensional arrays and provide high-level APIs for building and training machine learning models. It also includes tools for visualization such as TensorBoard, which helps in monitoring the performance. So let us get started with it. So the first thing which I want to do is I want to load in the data. So I'm taking a very basic data from sklearn.datasets. I am importing the load breast cancer data. And then I am checking the type of the data. So I would say once the data set is loaded, I say over here data is equal to load breast cancer, and this is the type of data. So I can say the type of data is a sklearn utils bunch object. The type of the data is a sklearn util bunch object. So this is mainly like a dictionary, which will have key and value pairs. So if I actually say data.keys. This will show all the keys. Now, see here also, one of the keys data, then target, then frame, etc. Let me load this as df then, so that there is no confusion. So df dot data will give me the independent variable, df dot target will give me the dependent variable, and so on. I can actually check it out. So if I say df dot data dot shape, so there are 569 rows and 30 columns. So understand over here, we have independent variable 1 to 30, and there are row number 0 to 568, because 569 rows are there. Okay, and if I say df dot target dot shape 569 comma, which means there is one more dependent variable. So basically it is 569 rows and 31 columns. Yeah, that's what we understand. We have 569 rows and 31 columns. Okay. If I say df dot target, and if you actually try to see that, see, these are the values. And if I say df dot target names, this will show the target classes. So you can see there are two types of classes. So over here, 0 is the malignant and 1 is the benign. So it's a multi-class binary classification problem to predict whether a female has a malignant type of breast cancer or a benign type of breast cancer. So what is malignant cancer? So it is a cancer which is characterized by uncontrolled growth of abnormal cells, uncontrolled. And in the same way, what is benign cancer? It is not that cancerous and relatively less dangerous. It is relatively less dangerous. It's not life-threatening. So we are trying to do this problem, right? To identify whether the female has malignant type of breast cancer or a benign type of breast cancer. Now, see, I said there are 30 independent variables. If I actually say df dot data, these are the ones. But instead of saying that, it's better that we see df dot feature names. So I will come to know what is x1, x2 up to x30. df dot feature names, and let us find out the length of it. 30 features. And if I say df dot feature names, these are the ones. So you clearly understand we have the mean radius of the breast. Then you have the mean texture of the breast, and so on. There are so many features. Next thing that we need to do is train test split. So we say over here that from sklearn dot model selection import train test split. Then xtrain, xtest, ytrain, ytest, df dot data, df dot target, and I'm keeping the test size as 33%. I want to print the shape of each of this data. So we can see we have further divided it into 381 and 188. There are 381, 188 respectively. That's what we understand over here. Now the next thing is I'll be going for scaling. So I say features is equal to df dot feature names, and I don't want it in the form of a numpy array. That's perfect. Then I say extrain of features. No. From sklearn.preprocessing import standard scalar. Create an object of it by the name standard scalar. And then I say sc.fit transform on this and this. What it says, extend of features, that's fine. Sc.fit transform extrain of features. Okay, extrain of features itself is not there because that's not available. So yeah, that's correct. So I'll directly scale it then. So I say from sklearn dot this, create an object of standard scalar. And we have this. If you want, I'll restart, clear output and run all. Perfect. Now after that, let's go ahead and create a neural network. So here, how do you create a neural network? See, understand over here, what are we mainly going to do? Our process is more or less going to be the same. So understand this, without a lot of background, I'm actually trying to create a simple perceptron model. So what I want is I want the model to understand the relationship between this row and this column. Then second row and this value. Then this and this. So on, so forth till this. This is what I wanted to study. This is exactly what I wanted to study between X train and Y train. So this is nothing but X train and Y train. We just have to understand the relationship in between the two. So after this, how do you create a neural network? So pay attention. I'm going to show you two ways of creating a very basic model. You know, what am I going to create? Listen to me very, very carefully. I have 30 columns, 30 columns. So X1, X2, up to X30. These are available over here. Then after that, we are going to create just one perceptron. And there will be output. So basically, this will go inside. This will go here. This will go here, and there will be multiple weights over here. Weight 1, weight 2, weight 30. Right. This is the basic neuron which I'm going to create. And what happens over here is, of course, there will be activation function on Wx plus B. This is essentially what we'll be having. So here, what I do mainly over here is I just add this, and then let us go ahead and create a neural network. So I want to build the model. And there are two ways of doing it. The first one, where I say model is equal to tf.keras.sequential, and I say tf.keras.layers. I'll explain you, don't worry. Input shape is equal to 30 comma, and then name is equal to input layer, and tf.keras.layers.dense, and I want only one thing over here. Activation is equal to sigmoid. All right. Yeah, we are done with it. So observe over here, how am I creating a very, very basic neural network? Here, I'm saying tf.keras.sequential. It looks like a little bit odd way of creating, but this is the one and only way of creating a neural network. tf.keras.layers.sequential. So you know what is sequential? See, if you are going to your office or you are going to your college, wherever you are going, that's not important. But if you are going to your office or you are going to your college, the first and foremost thing that we end up doing is we don't carry. See, if I want to carry my phone, I carry phone in my hand. Then I want to carry my laptop, so I'm carrying a laptop in another hand. Then I want to carry the charger, so I put my charger over here. Then I want to carry my tiffin, I put my tiffin over here. Is this how I go to the office? No. I put all of my items into a bag, right? I put all of these items into a bag. In the same way, whenever you create a neural network, this sequential layer, right from here till here, you know, the sequential layer can be considered of as that bag only. So whenever you want to create a neural network, be it a single perceptron one or be it consisting of multiple other things, you will always focus on putting these things into a bag like structure, and sequential is for that only. So now I say this format is always common tf.keras. So sequential layer. Then tf.keras.input, because we have to create an input layer of 30 neurons. Ideally, there are no neurons over here, therefore I didn't draw a circle. So I say tf.keras.layers.input. Shape is equal to 30 comma. Basically, 30 values will be coming as input is what I'm trying to say over here. And then the name, this name is optional. You can give the name of your choice or you can ignore the highlighted portion completely. Similarly, you can create one dense layer, which is just of one neuron. Activation I have supplied over here as sigmoid, right? Just give me 10 seconds. So I was saying input layer, done. Output layer, tf.keras.layers.dense. So see, every time you are adding a layer, there are only two types of layers. What I said earlier, that we have an input layer, we have output layer, and we have hidden layers. Now, technically, there is only one input layer, and the hidden layer and the output layer are called as dense layers. There is nothing called as hidden layer. There is nothing called as output layer. All of these are nothing but the dense layers. So we say tf.keras.layers.dense, one neuron, because there is only one neuron which I want to create a perceptron model. Activation is equal to sigmoid and name is equal to output layer. So let me tell you activation function. Input layer. The input layer receives the data and there is no activation function applied here because it is the input layer. Never, never, never. The second is the output layer. Now, here I say if we are performing a binary classification problem, then the output layer will use sigmoid activation function. And B, if you are dealing a multi-class classification problem, then the output layer will have softmax activation function. And C, in regression problems, the output layer will have the linear activation function. Remember these three rules very carefully. Input layer, no activation function. In the output layer for binary problem, which is in our case malignant cancer or benign cancer, output layer will have sigmoid. And for multi-class classification problem like the iris dataset, where you have the target variable as setosa or versicolor or virginica, then you will be using the softmax. For solving a regression problem, you will be using linear. See, right now, I would kind of say, memorize this for now. Memorize this for now. Right now only memorize this. Then, after that, let me ask you, which activation function would you use if you are solving a multi-class classification problem in the output layer? Multi-class classification problem? Very good. It is softmax. And for regression problem, output layer will have linear. Which problem are we solving? Binary or multi-class? Binary. And which activation function will we use? Sigmoid. One last rule I would like to add. One last rule. Input layer, done. Output layer, done. The third is hidden layer. So, here, use ReLU as the activation function for the hidden layers. So see, these are the rules. There are many more activation function. I'll show you as I showed you earlier as well. There are many activation functions other than these as well. ELU, exponential, GALU, hard sigmoid, hard CLU, hard switch, leaky ReLU, linear, we saw log softmax. Remember the rules because other activation functions are not very important. When to use it, we will discuss it later on. But for now, remember, we use ReLU, we use the linear, we use sigmoid and softmax. These are the most important and the basic ones. Okay. So I said, this is the input layer, which does not have activation function. There is no hidden layer over here because I'm doing a basic implementation of a single perceptron. So you can see there is only one neuron. And you know from where is this coming? I'll show you. If I actually copy this and I go to Google tf.keras.layers.dense, it will take me to the TensorFlow documentation. Over here, you can see number of units we gave 1. Activation we gave sigmoid. And there are many other terms which I didn't discuss as of now. But remember that they exist. There are many other terms, but remember that they exist. It's just that we have not used it for now, but they exist. Okay. This is one way of creating it. The same thing, I can create it using the second way as well. This is what I like it, and I find it more easy as well. Model is equal to tf.keras.models.sequential. Model equal to tf.keras.sequential, and you used to write everything inside this. But here I'm doing everything layer by layer. Model is equal to this. Done. In this model, I say add. Add what? tf.keras.layers.input, shape given and name given. So I said add this input layer. So here it was everything inside sequential, but here I'm adding it layer by layer. Further, I say model.add. What? tf.keras.layers.dense. One neuron only, which is like this. Activation sigmoid name output layer. So I do that. See, this I commented and executed this. It works. I can actually say model.summary. This will display the architecture of the model. So this is the summary of the model. If you see, input layer is not even mentioned. Output layer, none, comma 1, 31 parameters. Why 31? Because 30 are the weights and there will be one bias, 30 plus 1. So this is a very small neural network having 31 parameters. This is a very small neural network having 31 parameters. Okay, before I go ahead, can you please Google for me and let me know how many parameters are there in ChatGPT 3.5? It is 175 billion parameters. This is only 31 parameters. Can you imagine how big that neural network would be? 175 billion. So what we are building is a very, very basic one. What we are building is a very basic one. So model.summary gives us the architecture. Okay. Now, you know what? What you created just right now. This is like creating of a car body frame. Yeah. This is what is created right now. It is important that you fit in the engine of the car, which is yet not fitted. So I say this step is like designing the body frame of a car. That's what is ready. Now, let's fit in the engine to the body frame of the car and optimize the engine either for mileage or performance. So here we have the name of the model by the name model. So I say technically we call it as compiling the model. So I say model.compile. Optimize the model using the optimizer atom. Optimize the model using the optimizer atom. The error in the model or the loss in the model, because I'm solving a binary classification problem, I'm using the error function or the loss function as the binary cross entropy. And the metric would be accuracy. So model.compile, optimizer is atom, loss is binary cross entropy, metric is accuracy. So basically it is like fitting the engine into the car and then we optimize the engine with some optimizer, ensuring that the loss which is quantified using the binary cross entropy, is minimized. And for that, we have the metric as accuracy. And I'm done. Now, basically, now you have fitted the engine into the car. Now let's start the engine. So I say model dot fit on X train Y train for a total of 100 epochs. Validation data is equal to this. Now pay attention. Now I'm saying model go and fit X train Y train. It is like study the relationship between the X train and Y train data. Then epochs is the number of times the algorithm will study it. As I told you, one epoch is equal to one forward propagation and one backward propagation. One epoch is one forward propagation and one backward propagation. And validation data is where do you want to check the performance? In machine learning also, we used to check the performance on the unseen data. So that is what I'm saying. Now see, when I actually started, it is like we are starting the engine of the car. Boom. Let it complete. Because it's a very small problem, it happened at a lightning fast speed. See here. First epoch, we said we got an accuracy of 46%. So basically, when I studied the book for the first time, I got an accuracy of 46% and the loss of 0.81. And on the unseen data, which is the test data, I got an accuracy of 53% and loss of this. In the second epoch, my accuracy increased from 46 to 59. And my loss decreased from 0.81 to 0.76. Similarly, on the validation data, from 53 it went to 60. And this loss from 75 came to 0.68. Let us look at after 20 epochs. See, accuracy on train became 89 and validation became 93. Loss is 0.29, 0.27. After 50 epochs, 95 and 95. 0.16 is the loss, 0.15. After 80 epochs, 97 and 96. 0.10, 0.10. After 100 epochs, 97, 98. So loss, or sorry, accuracy on the testing data is little more. And this is loss 0.1021 point this. So basically what has happened is it has gone through the same network forward and backward. How many times? How many times has it gone through the same network forward and backward? Yes, 100 times. Now, what it actually did, that mathematics we will study in the next class. Today, we can't cover all of these things. That said, what I told you, right? I need R is equal to model.fit. So I'm asking the network to fit on X train, Y train for 100 times. That means I'm saying that, hey, you go and study this breast cancer data set, the training part, 100 times. Study one time, give exam. Study second time, give exam. Do this 100 times. And check the performance on this part. The weights and the biases, we need not even talk about it. Machines take care of it automatically. Machines take care of it automatically. So there are 30 weights over here. So I want to print the weights and biases of the model. That is how you can actually print it. See here. Model dot layer 0 Layer 0 is this dot get weights. Model dot layer 0 dot get weights of 1. So 0 is, so I'll show you what it basically gives. So here, if you see, these are the weights. W1, W2, W3. So these weights are the final ones. It keeps on running. And the bias is this. So what I did, I just separated it out. So I have the weights and the biases. When the machine is taking forward and backward propagations, again and again, it is essentially doing nothing but adjusting the weights and the biases. Amitav says, Amitav is always futuristic. In this, accuracy is how well the model predicts on the training data and its accuracy. What is the mathematical definition of loss? Yes, we are yet to cover that part, Amitosh. Give me some time. Yes. So, see, these weights are there and the biases are also there. In real life, these weights are biases. These are learned by the neural network. And you don't have to really look into the values of this because these values are enough to confuse us. It is of no use to us. But for a model, it is very helpful. So here, I say, now what will you do? See, we have got so many accuracies on the training. You see over here, 46, 50 lines, 66, and so on. You also have testing accuracy, 53, 60, and so on. All of these values, when I say all of these values, I'm basically talking about, see, these accuracy values, this validation accuracy values, then this loss values, validation loss value. All of these values are saved into the variable R. How to decide the number of epochs? That's again a later part of the story. We will not be talking about this thing as of now, but 100 is a good number over here. Basically, you increase or decrease it till you get a good model, in short. But how to decide upon that? I'll be taking that after 8 hours of syllabus. So today we are done with 4th hour, right? So next class, you will have some idea about it. That is tomorrow towards the end of the session. Sir, one more question. We know Perceptron would have Wx plus V and then activation function. Is there any way to see in this one Perceptron how it went from the first linear and then the activation? No, no, no. So TensorFlow 1.0 allows us to see that. Today we are using TensorFlow 2.0. So it has automated the process. It says that you don't worry about all these things because going forward, this mathematics is going to become even much, much more complicated. So they say that you need not even look at these all things. In fact, you know what, Amitoj and Sandesh, if you possibly look at these 4 red boxes, it is very difficult to interpret these 4 red boxes. So what will I do is I don't have time to go through each and every number in these boxes. So I'm going to plot the accuracy and validation accuracy. So have a look at it. See, these are the 100 values. We went from epoch 1 to epoch 100. And if you see carefully, here, accuracy, accuracy, accuracy. There are 100 values of accuracy and validation accuracy, validation accuracy, validation accuracy. There are 100 values. All of these are saved into the variable R. Similarly, loss and validation loss. They are also saved into variable R. So I'm saying that import matplotlib plt.plot r.history. So R has a history variable. I'm saying that plot the accuracy, label as accuracy. And it also has validation accuracy history as, I'm saying label as validation accuracy. plt.x label epoch, y label accuracy. Y limit goes from 0 to 1, so it is going from 0 to 1. plt.legend will display this, and plt.show. So all the values in the history are being plotted in the same way. Let me also plot the loss and the validation loss. Have a look at this. r.history loss, r.history validation loss. Labels are going to get plotted when I'm plotting the legend and x-label, y-label respectively. So see, we don't have time to look at the 100 values, but these graphs are good for us to understand that the loss is decreasing step by step and the accuracy is increasing step by step, and then it is kind of stabilizing. This is what we see over here. Now that we have some model, I will say, let us ask the model to make some predictions. So I say model, go and predict on X test. And I'll print the predictions. So sigmoid activation function over here gives the output like probabilities. So this is the probability. But the thing is, how do you interpret this? How do you interpret these probabilities? Well, see, if you see, these are nothing but values. This is 8.05 into 10 raised to minus 1. Basically, it is 0.0805. Sorry, 0.805. I'll show you how I do it. So if I actually consider this is what is the value. Or if I consider value like this, see, this is what is the value. 80% probability. This is 1.9% probability. So what will I do? First of all, I would say, let me round to get the actual prediction. So I say import numpy, y predicted is equal to, then I say np.round y pred. Then I say these are the predictions. Now, if you see, these predictions are, because I rounded off, this is 0, 0, 0, 1, 1, 1, but these predictions are kind of vertical, right? I don't want them to be vertical. So what will I do is, I would further say y pred is equal to y predicted dot, it would be all flattened. Now we know what is 1 and what is 0. What will I do is, let me calculate the accuracy, compare it to evaluate output. So what will I do is, I'm going to print manually calculated accuracy, where I simply say, I'll ask NumPy, tell me on an average how many times my y prediction and y actual are the same. And I will also compare it with the deep learning function, which is the evaluate method output, model.evaluate. Both of this will check it out. So I'm asking it, tell me on an average how many times the Y prediction is equal to the Y test. 96.27. And the same thing, model.evaluate on the X test, Y test. That is also 96.27. Basically, this is manual and this is the automated way of comparison. And we see that the accuracies are more or less the same. So we are good with the model, right? I can see the model is having a very good accuracy because the problem is simple. Now, what am I saying is, let me save the model. So I will say over here, model.save. I can give any name and .h5. So H5 is nothing but the HDF5 format, which is used for storing large amount of data. I can just print over here, model saved successfully. And now it says that you are saving the model using model.save or this, but this format is considered legacy. We recommend using the native Keras format, model.save, and save it as .keras instead of H5. So, see, model is saved. You can see over here, linear classifier.h5. Obviously, there is no thing that you will see over here, but yeah, this is how we save the model. And if you want to use this model, which is called as linear classifier.h5, so what I can do is I can say, let us load the model linear classifier.h5. Model is equal to tf.keras dot models.load model. I can actually print model loaded successfully. I can actually print model dot layers to understand the summary of the model. And I can actually print over here model dot evaluate on this. So if you see, it has only one layer, accuracy 96.44. And when I say model dot evaluate, you can see over here 96.27. That means it is exactly the same model of our interest. Now, what I want over here is, see, we created this model, right? Uh, you said this is the thing. There are many things which I want to show you in the notebook. What I want you right now to do is here. The network we understood, the reason we use sigmoid is because it's a binary classification problem. So these all inputs, x1, x2 up to x30, will be giving an output as a probability. Probability on the scale of 0 to 1. If that probability goes greater than 0.5, then the output is 1. If the probability is less than is equal to 0.5, then the output is 0. So we saw that sigmoid will always give probability as output. We have also used sigmoid in our logistic regression at that time. So a similar thing is over here. And this is what we are essentially doing. There are many more things that I can show you over here. But for now, I want you to take this notebook, run it, and try playing around less number of epochs or more number of epochs and see if the overall accuracy of the model increases or decreases. This will run perfectly in Google Colab. You don't have to do anything separately. In Google Colab, this notebook will run as perfectly as it was running here. Yes. Try running in Google Colab. I'll just be back in a minute. Try first running as it is, then try increasing the number of epochs or decreasing the number of epochs, and note the final accuracy and note the curves as well. So deep learning is mainly useful when you are working with the data in the domain of text, image, speech. Primarily, I would say whenever you are working with unstructured data, deep learning is good. So deep learning is good when you are working with unstructured data. So see, if you are considering a CSV file, you have a proper row and column structure. That is structured. If you are considering a Excel file, it is structured, right? Or if you are considering any kind of table data, that is also structured. So deep learning is not for all of this. In fact, the problem of linear classification, which we just solved, which was for benign versus malignant breast cancer, it was a structured data. Deep learning is mainly for processing text, images, speech, right? For all such data, we use deep learning for processing. That's the one thing. As I told you, earlier we didn't have data, processing power, or storage. Today we have all, and therefore deep learning is shining. Then, could you recall me what is a deep neural network? What is a deep neural network? Very nice. More than one hidden layer is considered as a deep neural network. This is a shallow network, more than this. Okay. Also, can you tell me uh, this figure and this figure? Let me call this as figure number 1. Let me call this as figure number 2, which is correct. 1 or 2, which is correct. According to me, second is more correct. Because I told you that hidden layer consists of neurons, circle, 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 circle. Output layer consists of neurons. Input layer doesn't consist of neurons. Most of them draw a figure like this. But the fact is, these are not neurons. That is why technically both are correct. I don't deny. But ideally, this is more correct figure. Because this is how the neurons are. Input 1, input 2. There are no neurons over here as such. Everyone is expected to make a note of it. Then, after that, we understood that whenever I pinch you, signals travels through the dendrites, processed in the nucleus. If it is above a threshold, it will signal through the axons to go and carries here. Right? If it is not, you ignore it. So our human brain consists of 100 billion neurons connected to each other via 100 trillion connections. And that is exactly what you call as a artificial neural network. So, or not, that is biological neural network, but when that is mimicked, we call it as an artificial neural network. Yesterday, we created just a single perceptron model where we had input 1 to input 30. All of them were going inside and we were getting an output, and internally what happens over here is wx plus b, and you apply an activation function. Now little revision with respect to activation function. Which activation function did I say will be used for hidden layer? The activation function for the hidden layer is ReLU. So see over here. You can either solve a classification problem or a regression problem. Classification can be a binary or a multi-class. Regression will be about predicting the price of the house. Be it classification or regression, hidden layer will use ReLU only. Then coming on to the output layer. If you are solving a classification problem, which is a binary classification, then the output layer will have which activation function? Sigmoid. That's why I twisted and asked it initially, sigmoid. And if I am doing a classification problem like iris, where it is a multi-class classification, then it would be, yes, softmax. ये रट्टा होना चाहिए, right? This is something which should be memorized. That's why I'm spending a couple of minutes in this part once again. And if I'm doing a regression problem, then this will be, yes, linear. Then this would be linear. So basically, friends, if you were not able to answer this, then this is the time where I want you to revise these two things. First and second, revise it right away, because this will be required throughout your life in deep learning. Very good. So I'm assuming it is done. Now, going forward. Yes. Now here, we looked at one very important thing. Here, initially, we understood that how is the processing happening? It is happening like this. W dot X, and you check it against the threshold. Then I modified it where I said over here. Yeah, we modified it where I said the final equation would be this. So over here, the output would be 0 if W dot X is plus B is less than equal to 0, and it's 1 if it is greater than 0. Okay, I think this much time was sufficient. Going ahead, then what did I say? The equation Wx plus B is very similar to what? What did we compare this equation with? Wx plus B? With which machine learning algorithm? Right. A linear regression. So the output, yes, that's correct. The output of Wx plus B, that is nothing but neural network, was very much linear in nature. And for adding non-linearity, we added an activation function, which is responsible for converting linear output to a non-linear. So going forward, whenever you talk about a neural network, it will always consist of Wx plus B and applied activation function. That's absolutely correct. So this is what we have actually done. Now, after this, here, in this network, if you want to create a little complicated network, you can do that. Like, for example, pay attention. This is the second way of doing it. And we agree to it. Now, what am I planning? There are 30 inputs, right? So pay attention. How many inputs are there? X1, X2, X30. 30 inputs are there. I'm planning to add hidden layer 1. I'm planning to add hidden layer 2. And I'm planning to add an output layer. So before I add it, please help me out with your expert opinion. Which activation function will be used here in hidden layer 1 for every neuron? ReLU? Okay. Which activation function will be used here in the output layer? Sigmoid? Very good. Which activation function should be used in hidden layer 2? Now, I know I am yet to explain the working of it. I very well know that. But we are just trying to understand how the things are connected. See, X1 is connected to all the hidden layers. But how many neurons are there? Let me also mention that. So here I am assuming that we have 32 neurons. Here I'm assuming we have 64 neurons and here 1. All of these is our assumption. All these things are assumptions. So X1 is connected to all the 32. X2 is also connected to all the 32. X30 is also connected to all the 32. Then here, this neuron is also connected to all the 64 neurons. 1, 2, till the last. This neuron is also connected to all the 64 neurons. This neuron is also connected to all the 64 neurons. And all the 64 neurons are connected to this neuron. And then finally I get this thing. So friends, if I say, let us calculate the total number of parameters. Total number of parameters is the total number of weights and the total number of biases in the network. Let's calculate. See here, 30 inputs and 32 neurons. So how many weights will be there over here? How will you calculate? 30 inputs and 32 neurons, everything connected to everything. So how will you calculate the total number of weights over here? What will be the calculation that you will do? 30 into 32. And what does that come out to? 960. So 960 weights. And also help me out. How many biases will be there in this each of the neuron? Total number of biases in this hidden layer 1? 32? Yeah, because every neuron has only one bias. So that's perfect. Plus 32 biases. Chalo, can you tell me the same thing in between this hidden layer 1 and hidden layer 2? How many weights are there? Tell me the final count now. Number. Tell me the final number, Amani. 32 into 64. That's correct. 32 into 64 comes out to what? 2048. Let me hear it from one more. Okay. Chalo, two of them confirmed. 2048 weights. And how many biases? Yes, 64, right? Yes, 64 because this layer, not this. 64, that's correct, right? For a moment, I was scared, Ramani, but you updated your response. So 64 biases. Also, could you tell me over here in between hidden layer 2 and output, how many weights are there? 64. Absolutely correct. 64. Correct. And how many biases? How many biases? One, right. Only one neuron is there, one bias. So over here, it is 960 plus 2048 plus 64 weights plus 32 plus 64 plus 1 bias. What is the final total of everything? Final total of everything? 8. Yeah, I got it from Preetham Aditya 3169. Okay. 3169. Perfect. So the number of parameters in this neural network is 3169. Yesterday, you remember we recalled ChatGPT 3.5. ChatGPT 3.5 had how many number of parameters? What did we Google out and found out? No. 175 billion parameters. 175 billion parameters. Okay. Now, one more thing I wanted to tell you that uh, this as per TensorFlow, I'll write it in blue ink. As per TensorFlow, there are only two types of layers. The first one is the input layer, and the second one, anyone recollects? One is the input layer, and the second one is the dense layer. Yes. Is there a hidden layer? No. Is there an output layer? No. There is no hidden layer and there is no output layer. So basically, what does TensorFlow say? That if you are using the activation as ReLU, you human beings call it as a hidden layer. According to me, there is dense only. So here also, if you are adding a activation as ReLU, it is hidden layer as per humans. Machines call it as dense layer. And if you add an activation like sigmoid, we call it as an output layer. But technically, it is only and only dense layer. There is nothing called as hidden layer or output layer. It's a very common convention used by all of us to call it as hidden layer, output layer. But as per TensorFlow, there are only two types of layers. Now let's get into creating this network. So what I say is, how will I create it? Let's create it using the second way, right? So I will create a network over here. Okay. Now let's start. Let's do it step by step. First thing what we want is the input layer. So tell me, this is the sequential thing and this is input. So can I say these two lines are good enough to say that my network's skeleton is ready in line number 2 and model dot add. So line number 3 basically creates this. Are you all with me? Right? So line number 1 and 2 create the things till this point. Input layer. Line number 1 and 2, actually 2 and 3. Line number 2 and 3 create this much. Okay. Then after this, now I say I want to add hidden layer 1. How will I do? Pay attention. I say model dot add. And I want to add a hidden layer, but there is nothing called as hidden layer. You just write it as dense only. So I'll come over here and I will say tf.keras.layers.dense. And then inside this, tell me how many number of neurons we plan to add. I assume that how many neurons we said 32. So the first parameter which I write is 32. Then after that comma activation is equal to, after that comma activation is equal to ReLU. Correct? Because I want the hidden layer, right? So we call it as activation is equal to ReLU. And I can give the name of my choice. Whatever name you want, you can give it. If I want to label this as Preetham, I can. My choice, no? This is optional. This entire parameter is optional. You give it or you don't give it, it's your choice. So we added this. And then we have to add one more hidden layer. So I will copy this line. I'll copy this line and I'll paste it. And what change will I make in line number 5? Yes, that's absolutely correct. So can I say that this one exactly creates a network like this? Ah, yes, name, sorry. Yeah, that's correct. This will be 2. That we forgot, na? Very nicely observed. Yes. So now can I say that this highlighted portion creates a network like this? Yes, everyone? Acha, so tell me one thing. Now going forward, of course, we'll be understanding the mathematics, but going forward, if I ask you to create any neural network of any size, would you be able to do it? Any neural network of any size, if I give you a figure like that and I say create it, yes, right. This is one of the very important skill that you learned today. Very important skill, right? So this is a very, very important skill because practically the theory part is less important as compared to the hands-on part. We will be looking into the theoretical part. I'm not saying no, but this is more important. Now, the thing is, wait a minute, Manu. Now the thing is, do we know whether this neural network will perform better than the previous one? Do we know whether this network will perform than the previous, better than the previous one? Any idea? Any hints? Honestly speaking, no one knows, not even a deep learning expert with 20 years of experience in this domain. Even he cannot even guess whether this would be better than the earlier single created perceptron. Right. There is absolutely no guarantee. There is absolutely no guarantee. So, just like in machine learning, you remember we had to do hyperparameter tuning. And for doing that hyperparameter tuning, we used the algorithms like what in machine learning? What algorithms we use for doing the hyperparameter tuning? To find out the best combination of hyperparameters, we played a raw lot. Yes, grid search CV. And there was one more. There was one more. Yes, randomized search CV. And among grid search CV, so let's call it like this. Grid search CV and randomized search CV. Among this 1 and 2, which is more preferred in the industry? 1 or 2? You can just type the number. Yes, number 2. That's absolutely correct. But again, what is the right set of hyperparameter? We don't know. Same applies over here. So we created a neural network. I will just display the model.summary and it is expected to show me 3169 parameters. Just like here, it is showing the total number of parameters as 31. Now it should show 3169. Let us check it out. Yes. So you understand what is model.summary. See, the name that we gave hidden layer 1, there is nothing, there is no record for input layer. The name that we gave comes over here. If you don't give that, then it will not come. See here, if I just remove it and if I run it and I run it, see, this is how the default name will be displayed. So it's your choice whether you want to write the name or you don't want to write it. Writing it is better. Did you all understand the significance of this name equal to parameter? So, hidden layer 1, none, comma 32. Correct, na? 32. Hidden layer 2, none, comma 64. So here, why is this number 992? Why is this number 992? 960 plus 32. 960 plus 32. Yes. 60, 70, 80, 90. Yeah. Total of this is 992. What is the total of this? 2048 plus 64. Is it 2112? Correct hai kya? Is it correct? 2048 plus 64. 2048 plus 64. No. Oh, sorry. 64. 2112. Yes, yes, yes. That's correct. My bad. And this is 64 plus 165. And then the total of this is 3169. That's absolutely correct. Now, we will just add a photo of this and I'll share it as well. We created, then I come down, another hyperparameter. I gave optimizer as Adam, right? But you know what? If I go to Google and if I say over here, optimizer TensorFlow, there are many other optimizers. If I click on this TensorFlow link, have a look at this. We have ADA delta, ADA factor, ADA grad, Adam which we are using, Adam W, ADA max, FTRL. There are so many type of optimizers that you can play around. Again, it's a hyperparameter. In fact, what we have not studied is if you click on this Adam class, inside this Adam also, there are so many further hyperparameters. I will talk about this in the next class. But there are so many things. All of these are further hyperparameters. In the same way, loss I settled as binary cross entropy. That is again a hyperparameter because if I click on loss function TensorFlow on Google, it will take me to the documentation. I click here and you see over here, there are so many loss functions. Binary cross, binary focal, CTC, categorical. Again, these are hyperparameters. Which one to use when? You have this, see, mean absolute error, mean square error from our machine learning, right? They also exist. Okay. So right now I'm not touching any one of this. I just ran this and I say model, what accuracy it gave me? The latest result which our neural network gave is this. Now what we did, see earlier with a single perceptron, with With a single perceptron, we got this result, right? Where I see the accuracy is 96 on train and 96 on test. Let us try to train it again for 100 epochs, but the number of parameters are more this time. So obviously the training time for this network will be larger because the network is bigger. Do you all agree that the training time for this network would be relatively larger as compared to the earlier one? Yes, because there are many weights and many biases, network is bigger, right? So I just click on this. Done. So now we say we are getting an accuracy of 100% and 97.3%. Look into the result, which is there in the chat box for a single perceptron model where I had 96.7 and 96.28. So do you all agree that this model is better? In fact, to validate our assumption, is it really a good model? We'll try it out. So here now the weights and biases will be even more. You see, these are the weights and these all are the biases. So now let us look into the accuracy. So I'll just run this. Yeah, it's good, right? It's stable. But looking at this, logically, if you see over here, uh, see, is our training accuracy or validation accuracy improving after around this? After 19 epochs, do you see either training or testing accuracy improving? After 19 epochs, do we see that? So that is kind of an indication that we are wasting our resources, right? We can reduce the number of epochs, and he is absolutely correct. Therefore, you should try step by step. So here, there is no need to go for so many epochs. That's absolutely correct. And let us look into the loss function. This model is actually overfitting. If you see this person, this is exactly like the Chatur of Three Idiots. As and when the number of epochs are increasing, he is becoming awesome on what he is studying, which is the training data. But on the testing data, he was awesome. But now we see that on the testing data, that's increasing, which means that he has become a faku. In the sense, on training, he is awesome. But when it comes to generalization, he is not able to generalize well. He is going more and more and more wrong on the test data set. And on the train data set, he is becoming better. So this loss function clearly tells us that this model is overfitting. So what I want to tell you is the rule which I said, that train and test difference less than 5%, test accuracy must be at least 80%, all good. But it's not easy to just conclude on the basis of these results. That is why plotting is very important. Although the accuracy is good, we want the loss function also to be good. If not, then it's a problem. Therefore, plotting is very important. So, see over here. If you see, see, this is the loss. This is the loss. It's a good loss function. This is the accuracy and validation accuracy. It's good. This is also good. See, I mean, of course, if you go ahead, it will further start overfitting, but the difference is very marginal. So all of these loss functions and the accuracy functions, they are good. If I come into this, tell me, are both of this curve good or bad, according to you? Is this good or bad? Because understanding this curve is very important. You know what is good? When both the things kiss each other. When both the lines are kissing each other, it's good. So basically you see over here and basically you see over here. After that, they are running parallel, continuously kissing each other. It's good. Similarly, if you look over here, if a point comes when they just keep on moving together, it is good. So these are good. If I look at this, tell me, is this good? Loss function? Yes. Ideally, it's not that good, but see, if you, one more thing I want to say, yeah, Ramani, that's correct. It's fairly good, I would say. You know why? I'll tell you why also. You should also consider mapping these values on the y-axis. How much is the difference? Is this difference really even 5%? Tell me, is the difference between train and test loss? Is this even 5%? No. So it is good. Hi, if this difference was more, then there is a reason to worry. But here, it is good as per me. Then look into this. How about this? Is this good? No, right? Because although they are going parallel, I am happy with that. They are more or less parallel. But if you see this is almost 75% accuracy, and this is 97% accuracy. The difference is more than 5%. So this is not a good one. Then, how about this? Is this loss function good? No. Then, how about this? Is this loss function good? Right? Yeah, they are very close to each other, right? It's good. Perfect. How about this? Is this accuracy function good? Huge difference. Though they are going parallel, no doubt about it, they are going parallel, but the difference is huge. That's correct. About this, no, right? Because the difference is very high. If I would have said this is 99 and this is 96, then this would have been good. Now you are understanding it. Yes, that's perfect. Look into this training accuracy. This is good, but there is a lot of noise. You see, it is just moving up and down a lot. There is a lot of noise, but it's good. But the loss function is not good because there is lot of variation. Although it's more or less continuously kissing the line, but still it is not a good because we understand that there is huge amount of noise. So we don't see a stability as such. How about this? No, that's correct. How about this? No. Now you understand how to interpret it. So I can close this. This is noise. That's correct. So here I can look for the predictions of the model. I can just flatten the predictions. Let us look at this accuracies. 97, 97. I can save the model if I want. So now, friends, going ahead, I did say activation function is nothing but the secret sauce of the neural network, right? So neural network, as we all understand, neural network is all about tuning the weights and biases. So if there is no activation function, the output of the entire neural network would be the linear function of the output. But here we introduce some activation functions. Now let's have a look at each of this. This activation function, which is having a shape like this, is called as a step activation function, which will either be off or on, 0 or 1. Then this is the sigmoid activation function. So sigmoid is S-shaped activation function. Then if you see, the third one is ReLU. So ReLU over here, if you see on the negative side, it is flat. And on the positive side, it flows as normal. So on the negative side, it is 0. And on the positive side, it flows as normal. So ReLU is like this. And tan H is this. So tan H goes in the range -1 to 1, like the sigmoid, which goes in the range 0 to 1. So tan H goes in the range -1 to 1. So sigmoid and tan H are one and the same. The only thing is tan H is in the range -1 to +1 and sigmoid is in the range 0 to 1. And this is a linear activation function. Yeah, so I was saying these are the various available activation function. So this is the step activation function, right? So this is the original concept behind the classification or the region bifurcation. Let me tell you that step activation function is not used anymore, right? So over here, you remember the output, which I said this can be either 0 or 1. It will be 0 if w dot x plus b is less than is equal to 0, and it will be 1 if wx plus b is greater than 0. So this is the step activation function. It is not used anymore. So over here, the idea was very simple. If the input becomes greater than 0, the output automatically becomes 1. In practice, this form is difficult owing to the abrupt nature of the step function. You know why? Because let's say, it's like, as an example, it's like I say that if the score that you get is greater than 150, let's say you get admission, else you don't get admission. So this is very harsh in nature, because if I say I got 149.5, I don't get an admission. I say I got 149.9, I don't get admission. I say I get 150, I don't get admission. I say I got 150.01, I get admission. So if you see, the nature is very abrupt. If you are here, you don't. If you are here, you yes. So it's very harsh in nature. So that is the problem over here. So it is not used anymore because of this only. Then this is the one. So the problem with the perceptron is this. So what we do is step function is made smoother, right? So sigmoid is what? Smoother version of step function. It goes in the range 0 to 1. And it is not harsh at 0. It is smooth, right? So this is the reason. And sigmoid is very similar to the logistic only. So it is denoted as 1 upon 1 plus e raised to minus of w into x plus b. This is how it goes. So we say sigmoids are very similar to the perceptrons. But now the advantage is even small changes in the weights and the biases cause only a small change in the output. Right? So that is what is the biggest advantage that you get over here. Then we also say that this was step and this is sigmoid. So the smoothness over here is there. So sigmoid function is nothing but a smoother step function. So the smoothness ensures that there is more information about the direction in which the weights should be changed. So mathematically, it is linked to the logistic regression, which we have already learned earlier, right? It is mathematically linked to the logistic regression. And see how it works. To understand its similarity, now consider over here that, see, what is the output that we get? W into x plus b. And what is the equation of the sigmoid? 1 upon 1 plus e raised to minus z. Now consider the first scenario. If w into x plus b is a very large positive number, then e raised to minus z is nothing but wx plus b, then e raised to minus z is approximately equal to 0. And therefore, the overall equation 1 upon 1 plus e raised to 0. So overall equation of the sigmoid value turns out to be 1. So when this is a very large number, sigmoid is 1. Consider the second scenario. If wx plus b is a very negative number, in that case, e raised to minus z is infinity, and therefore sigmoid is approximately 0. Right. So we understand that for very high value, the value turns out to be 1. You can see continuously 1. For very low value, it will turn out to be 0. And for a decent range, which you see somewhere over here to here, for this decent range, you get a nice curve. So therefore, we understand that it is only when Wx plus b is of a moderate size, there is much deviation from the perceptron model. Else, here, it behaves like a six-step function. Here also it behaves like a step function. So it is basically like this, right? This is where you see a variation or deviation. Here, it is constant. Here it is constant. So basically, this is normalized version of the step function. That's what we understand. Now, there is a problem with sigmoid. And the problem with sigmoid is that it suffers from the problem of vanishing gradient. Now, technically, we will discuss it later. But let me tell you, this is a very, very important concept. If you are applying for a deep learning specialist, then don't expect the interview to be over without anyone asking you about what is vanishing gradient. Let me explain you in simple terms what is vanishing gradient. So over here, as you can see from this picture, we have a sigmoid which squashes its input into a very small output range 0 to 1. So if you see over here, there remains because it is squashing into a very small range, it has very steep gradients. Basically, if you look at the slope over here I see we have very steep gradient or slope. But here, if you see, it is flat. Here, if you see, it is flat. So now, therefore, we say there is a large region of the input space where even a very large change in the output produces a very small change. Let me explain this to you. So if you actually look into sigmoid function. So let us look into this. 1 upon 1 plus e raised to minus x, I just have to put the value of x. If I'm putting the value of x as 0.73 and I click on sigmoid, you see the sigmoid value turns out to be 0.6. We know that sigmoid value will always be in the range 0 to 1. That's exactly how it goes. So here, the interesting thing to be noted is this part. This is where there is a steep slope, but here it's flat, here it's flat. I'll tell you how. So if I give a value at 0.73, I'm getting 0.67. 0.67 would be somewhere here, no? Here. Then if I give a value as 0.75, it is 0.67. If I give a value like 0.90, it is 0.71. If I give a value like 1.2, it is 0.7. If I give a value like 5.99, if I give a value like 6.99, so basically 1 only, na? 1. If I give a value like 10.99 only, if I give a value like 15.99, if I give a value like 30.99, if I give a value like 50, 1, which is again 0.99 only. If I give a value like 100, it's 1. If I give a value like 1000, it is 1. If I give a value like 10,000, it's 1. So basically, you can see that for any number above, maybe 10, or even if I say 5, for any number above 5, it is always 1. For any number above 5. So for any number above 5, it will always be 1. And let's say if I'm considering a value like -5, it is 0. If I consider a value like -3, it is 0.04, -4, 0.01, -5, it's almost 0, -6, almost 0, -10, almost 0, -100, almost 0. So kind of we see that for -5 and below values, it is continuously 0. And here it is continuously 1. And only in between the range -5 to +5, there is a steep slope. This problem is called as the vanishing gradient problem. And this problem actually increases as the number of the layers increases. And thus the stagnation of the learning of the neural network happens. And that is called as the issue with the sigmoid. And therefore, sigmoid is only used at the output layer and not at the hidden layer. Are you all clear with the issue of the sigmoid? Everyone, is that making sense? For higher values, it is either 1 or it is either 0. And for a center range of values, there is a steep slope, which is a problem. Yes, so that is what is the issue over here. So, yes, the issue exists for TANH as well. Very nicely said. That's absolutely correct. So, this is the TANH. And if you look into logically, you consider your sigmoid or TANH. I would say qualitatively, both are same. It is just that sigmoid goes in the range 0 to 1. TANH goes in the range -1 to 1. So sigmoid is quite similar to logistic regression. If x goes to infinity, the value becomes 1. And if x goes to -infinity, the value becomes 0. And TANH is a rescaled version of the sigmoid. So it's just that instead of 0 to 1, the value is -1 to 1. That's the only change over here. So now, hence we say, the steep slope is not a problem. The problem over here is for very low values, it will be giving 0. For very high values, it will be giving 1. But only for a certain small range of values, it will give you a range in between 0 to 1. So basically, instead of this, which is moving like this, they say it would have been better if it moves like this, smoothly up rather than this. So this instant up down is the issue. They want a more smoother function so that all the values are captured smoothly in the range 0 to 1. That is the thing, Anivesh. Right? So now the next thing is problem with the sigmoid is what we have seen. So the problem with the sigmoid is near zero gradients on both the extremes, right? So here it's zero slope. Here it is zero slope, right? So here slope is 0, slope is 0. Only in this range you have some valid slope. So we see that for both large positive values and large negative values, sigmoid values don't change much with the input. But ReLU has a constant gradient for almost half of the inputs. ReLU has a constant gradient for almost half of the inputs. But ReLU cannot give a meaningful final output. So if you see a rectified linear unit, right? So rectified linear unit, unlike the step function, sigmoid does not have the zero derivatives, which means on both the positive and the negative sides, the results of the large input values are flattened, whereas ReLU is flat only on the negative side. ReLU is flat only on the negative side. So if you look at sigmoid, sigmoid is actually doing like this, right? So see the sigmoid, basically, how does it go? If I try to fit in over here, it goes like this. That is how it goes. So you see over here, it's flat. You see over here, it's flat. On the other hand, if you are looking at ReLU, ReLU is better. ReLU is better. ReLU is flat only on negative side. So ReLU is flat only on the negative side. On the positive side, it's never flat. Therefore, I don't say ReLU is to be used in output. ReLU is therefore mostly used in the hidden layer, and of course they cannot give a meaningful output. They cannot give a meaningful output because they only keep the positive part and the negative part they discard. So we realize that the thing over here is ReLU. Basically, the function is fj of xj, which is nothing but max of 0, comma xj. So among these two values, whatever is the highest, it will take. So ReLU must never be used at the output mode. So if you are actually doing, let's say, for example, a cat versus a dog classification, we will always use either sigmoid or the softmax, because ReLU will take the values from 0 to any positive value. So even if you consider a regression problem for predicting the profit, ReLU can go negative also, right? So regression problem, see, if I'm predicting profit, can the profit be minus $100? Yes. So if it is minus $100, ReLU will make that minus 100 as 0. ReLU will make any negative value as 0. So ReLU is problematic. So ReLU is therefore popular and used only and only in the hidden layers. And they are working really good at hidden layers due to the fast convergence. But there is one problem. The problem with ReLU is the negative side is 0. So I say the problem with ReLU is the negative side is 0. See, this is how ReLU was. So negative side is 0. Negative side is 0. So they came up with leaky ReLU. What they did, they added a very small slope, as small as 0.01 degree, so that the negative side is not killed. And they call this function as leaky ReLU. So ReLU problem is nothing but, we call the problem as dying ReLU. And the solution which was proposed by deep learning engineers is you go for leaky ReLU. On the negative side, add a very small slope. Do you need to actually add it? The answer is no. You don't have to do anything. You just have to change the name. If you recall, we did Google for activation function. And here only you see leaky ReLU. You just have to spell it correctly. Rest of the things you need not even worry about it. Leaky ReLU, ReLU. If you know the spelling, you are good. You don't need to do anything else. Therefore, I'm explaining all this mathematics to you at a higher level. So leaky ReLU also, which layer will you use? Always in the hidden layer. Then the next one is the softmax activation function. So softmax also goes in the range 0 to 1. So softmax activation function is nothing but also called as normalized exponential function. So basically what it does is this function transforms a set of given real values in the range of 0 to 1 such that the combined sum is 1. So it's like this can be done as e raised to zk upon summation k is equal to 1 to k e raised to zk, or j is equal to 1 to k. So basically, softmax is similar to sigmoid, right? So sigmoid is mainly for binary classification, and softmax is for multi-class classification. So softmax is similar to sigmoid, but it calculates the probabilities over the n classes. So it is useful in multi-class classification problem. So basically, what it will do is, if I consider example of iris, let's say the current flower is versicolor or virginica or setosa. What will it do? It will predict all the probabilities in the range 0 to 1. So it says that the probability of this flower being versicolor is 0.20. This being virginica is 0.78, and this is 0.02. So if you find out the summation of this, it is 1.0, right? That's what I said, that the combined sum is 1. Perfect. And out of this is the max probability. Therefore, the flower is ideally virginica. So softmax does it this way. So if there are 10 classes, 10 probabilities, and it will pick up the highest probability. And the sum of all the probabilities will be 1.0. That is how ideally the softmax activation function works. So by default, the activation function looks like this. So basically, what is this? This is a linear activation function. So linear activation function is as good as your input is same as the output. as good as no activation function applied. So among all the activation functions, this is the only one which is linear. The rest all are non-linear. So basically in regression, when I said that you apply the linear activation function by default only we know that Wx plus b is linear. To make it non-linear, we applied various activation functions. So when I say Wx plus b is linear, that means it is already of this shape. So you're not applying any activation function. The output of linear activation function can be a large positive number or a large negative number, whereas other activation functions, the output was restricted. So linear activation function is useful when you want to output any value. So it's as good as saying no activation function applied. Right. It's as good as saying no activation function applied. And technically, these are the formulas for the activation functions. So over here, see, we all know if I'm considering this, this is the input layer. So quickly help me out with the inputs over here. So I want to know from your side, how many weights and biases are over here? How many weights and biases over here? Multiple choice question. I see two different responses. One of you needs to correct it. Sandesh or Ramani. One of you need to correct your response. Or others need to support one of these guys. Yes, that's correct. 12 plus 4. Here, 16 and 4. Here, same, okay. And here, yes. So, quickly tell me directly, the total number of parameters are how many over here? 61. Very good. Thank you very much. Now, consider the problem of a cat versus a dog classifier. So it's a binary classification problem. I know that here this is hidden layer 1, this is hidden layer 2, this is hidden layer 3. Here ReLU, 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 and here what? इधर क्या आएगा activation? Yes, that's sigmoid. Okay. Now consider that I have 500 images of cats and 500 images of dogs. All of these images are there in a folder. You have 500 images of cats and dogs. Okay. All of these are mixed. So total we have 1000 images. And I am creating over here just like our benign versus malignant. Here I have a cat versus a dog classifier. Now understand the things over here. In real life, weights and biases are randomly initialized. In real life, weights and biases are randomly initialized. And are adjusted further till they become perfect. So, so basically the weights and the biases are randomly initialized. So here you have weight 1, weight 2, weight 3, weight 4, weight 5, 6, 7, 8, 9, 10, 11, 12. And this is what you see over here. You have the following weights. This is what you have. And of course, we understand there will be bias here, 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 and here. So if I say, what is the operation happening over here? So what is the operation happening over here? This is x1, this is x2, this is x3. So here, w1 x1 plus w5 x2, w1 x1 plus w5 x2 plus w9 x3 whole on a ReLU. Am I correct? Is my calculation correct? Could you please confirm over here? This is what happens. Is that correct? Check it out. Then just confirm yes or no. Yes. Sorry. Yes, that's correct. Thank you very much for reminding. Plus B1. Yes. Plus B1. That's correct. Now, is it correct? Yes, superb. So let us assume that this gives the result 21. Assume. Let's assume that this result is 21. So now this 21 flows here. This 21 flows here. 21 will go here. 21 will go here. 21 will go here. And 21 will go here. So again, there will be some weights and biases over here. There will be weights, there will be bias. And this will keep on flowing left to right. A point will come when they finally reach here. So what happened over here, the same keeps on happening in every neuron. So you can understand that the mathematics, if you try to do it with pen and paper, is going to be way more complicated than you can think of, but this is how it will happen. Are you all clear with what kind of multiplication, addition, and activation function is getting applied throughout when I'm traveling from left to right? Is that making sense so far? Right? Yes or no? Yes. Okay. Thank you. Now, let's actually understand. So I said, I'm working on a cat versus dog classifier. I have 1000 images. That's my input. X1, X2, X3. In real life, weights are randomly initialized. So if you recollect, you remember this example where we initialize -2, and you solved all of this. So here also, this -2, I assumed. This bias also I assumed. And based on that assumption, we solved it. In fact, some slides back, this example of going to a Punjabi food festival, this also I assumed. And this also I assumed, where I later on replaced threshold by bias. But I assumed, and that my assumption, which I was talking about earlier, that was correct. So in real life, you have to assume only. In real life, we have to assume. So I have a cat versus dog classifier. Now, you know what, how it works? Listen to this very carefully. See, how is an image ideally? An image is something like this. If I talk about uh, in real life, an image looks like this. Pay attention very, very closely. As human beings, we look at pixels this way. These are pixels like us. But machine thinks of it this way. So as per a machine, black is 0. And as per a machine, white is 255. So the values as per a machine are always in the range 0 to 255. So when both of these things are drawn together, you can see over here, and all the other values are in the range 0 to 255, where 0 means black and 255 means white. So an image looks like this. So the next thing which I want to talk about is image flattening. So if you consider a very small 3 cross 3 image, the first thing that we do is we flatten the image. So 1, 1, 0, 4 to 1, 0 to 1. And then this is called as flattening the image. And then after flattening, we take the transpose. So 1, 1, 0, 4 to 1, 0 to 0. Are you all clear with this operation of flattening and transposing, everyone? How an image looks like and how you flatten and transpose. Yes, so if you are clear, assume this to be a image of either a cat or a dog. So images technically are nothing but pixel values. What do you do with pixel values? Flatten and then you transpose. Why are we doing it? You will understand it right now. So here I say, when you have an image, let's consider a small 2 cross 2 image. Pixel 1, pixel 2, pixel 3, pixel 4. The moment you flatten it, it becomes like this: pixel 1, pixel 2, pixel 3, pixel 4. And then when you transpose it, it becomes pixel 1, pixel 2, pixel 3, pixel 4. This is how it becomes. So when I take these 1,000 images, obviously every image you will have to flatten and transpose it, and it will become like this. So this is the first one, this is the second one, this is the third one. So do you understand that now if I'm considering the same images, so let's assume that each image is of size 3 cross 3. Assume each image is of size 3 cross 3. And we have 1,000 images. So the 0th image, once flattened, would be pixel 1, pixel 2, up to pixel 9. And what is that image about? So let's say that image is a cat. Then let's say the next image is of a dog. When flattened, let's say it's a dog. Let's say the third image, when flattened, looks like this. And let's consider it is again a dog. In the same way, this will go on till what? It will go on till 999, right? And then after that, we are actually doing the same machine learning story. Maybe I can divide this data into two parts where this is the training data. This is the testing data where I ask a model to understand the relationship between X train and Y train. Are you all able to understand more or less? I am trying to tell you that more or less, I am trying to tell you that all the data is the same. It does not matter it is image or your regular CSV file. I converted the 1,000 images in the same structured data format. And then I can feed this data one by one into the neural network. How? If I have to if I have to give the very first image, this is 0th one, what will I do? I'll take this image and I'll transpose it and it flows inside the neural network. If I have to give the second image, I'll take this image, I'll transpose it, and it flows inside the neural network. And so on and so forth. I will do it for all these things. Is that concept becoming clear? All data is the same. The same thing happens with video, same thing happens with audio. You convert it into the independent and dependent variable format. This is something very, very important. Only Ramani confirmed. What about others? Are you all able to understand this? Yes, input is x1 to x9. That's absolutely correct. Number of inputs will be very high. You are correct, because in real life, you take up your phone and just look into your image gallery. And once you look into the image gallery, could you check what is the number of rows and columns in any one of the image? If I take one of the image, my iPhone 15 image, which I am just checking, it is 4284 cross 5712. 4284 cross 5712, which is look at this, 24 lakh, no, 2 lakh 44,000. Nah, 2 crore 44 lakh 70,000 independent variables. You might get fainted. Have you ever seen so many independent variables in a machine learning problem? So that is the size of one image to process. Are you all understanding that deep learning is really very, very much big than what you can think of? What if the images are of different sizes? If the images are of different sizes, we have to convert everything to a standard size. Very important. You will have to take that additional efforts for converting every image into a standard size. And when you do that, so for example, if I am looking for images of cat, see, this image is rectangular. This is a rectangular but horizontal. This is third image, bigger size. See, all the images are of different sizes. All images are of different sizes. You have to convert everything into a standard range. Let's say you decide to convert everything into 1000 cross 1000. So what will happen if this is 1000 cross 1000? So if you have a bigger image, it will get cropped. If it's even bigger image, it will further get cropped. If it is smaller image, it will get less cropped. If it is more smaller than this, it will be padded. But everything has to be ultimately converted into a standard range. So there can be loss of data or there can be padding with zeros. Both of these things are possible, and you have to do that. So standardization is important. We will study that later on. This is very basic for now, but yes, we need to convert everything into a standard size in that case. Clear, Anivesh? Welcome. In fact, in machine learning also we did standardization. I hope you remember, all of you, right? I hope you remember we did cover min-max scaling, standard scaling. Over there also, we were doing standardization. Deep learning is not different. Next time when we meet, right, we are actually going to do a case study on image processing only. That will make the things more clear as and when we go ahead with it. That was an interesting question. So here, now we say, that's what we have. The next thing. So now, going here. So what we do is, I send over here the 0th image. There are 1,000 images. There are 1,000 images. So I'm sending, rather than saying 0th image, let me say first image only. Convenience. Yes. So I'm sending the first image. I know that image is flattened and then transposed. So let's say this is that first image which I am sending. So we know that when it flows inside, these weights and biases in real life are randomly initialized. So I know there are many weights over here, 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 here. And there are biases here, 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 here. So let us assume that this weight is 400. Assume. So in the same way, all other weights will also be initialized for explanation purpose. For explanation purpose, in this entire network, my explanation will be only with respect to one weight. We will not look at all other weights, because whatever happens with this one weight, similar operation happens with all other weights. So we know that now W into X plus W into X plus W into X plus bias, it gets performed, activation function is applied, and that flows ahead. Similarly, computation here happens, then here happens, then here happens, and then here happens. And obviously, it is going to give some prediction. Let's say the first image was of a cat. I am saying cat is 0, dog is 1. So the output of the network came out to be 1. The output of the network came out to be 1. But actually, it is expected to be 0 because this image was of a cat. But it predicted it as a dog. Can you tell me who is the culprit for me getting the wrong prediction? The output is coming wrong because of whom? The output is coming wrong because of weight and biases. The main culprits are the weights and biases only. If I have the right values of weight and biases, my output would be correct. So the most important thing in neural network is the weights and biases. So very nice. So friends, now it went wrong. No problem. Then what I said, okay, let first image over. Let's say I'm sending the second image. Let's say the second image is about a dog. So again, the same Wx plus B happens. It again flows here and it predicted it as a dog. Actually is also a dog. This time the prediction was correct. Don't be very happy It was just a luck. Our weights and biases are wrong. It was just a luck. Then I sent the third image. Let's say the third image was about a cat. So it predicted 1, but actually it is 0. In the same way, you send all the 1000 images. If you send all the 1000 images, do you agree that you will be getting a total of 1000 predictions? Correct or not? Right? If you send 1000 images, all of them going from left to right, this process is what is called as forward propagation. And you get 1000 predictions. Now, how do we quantify whether we are right or wrong? To quantify whether we are right or wrong, we try to measure the loss. One of the loss function which we know is mean squared error. If you remember the formula, summation I is equal to 1 to n actual minus predicted the whole square upon n. Do you remember this formula? We always aim to minimize the loss. We had solved all of this using Excel also. Yes. So if I have to calculate this, so how do I calculate it? I say that actual minus predicted whole square, 0 and 1. 0 minus 1 whole square plus 1 minus 0, 1 minus 1, 1 minus 1 plus 0 minus 1 whole square plus 1 minus 1 whole square whole divided by 1000. Are you all clear with this formula? Yes. Okay. Very good. Let's assume that the total loss came out to be 3000. Assumption. Are you all with me? Total loss came out to be 3000. That's an assumption. So, just to recap, what we did is we had 1000 images of cats and dogs. Each of the 1000 images are sent one by one from left to the right. I get 1000 predictions, 1000 actuals. These came because of randomly initialized weights and biases. And to find out how good we are, we use the loss function as the mean squared error. And we get the mean squared error over here, which is the total loss as 3000. Now, what is the best value of total loss? Can you guess? What is the best value of total loss? What is the best value of total loss? 0. Absolutely correct. So the aim is to go from, remember, now the aim is to go from total loss 3000 to 0. Now, if you are working in a corporate, I am pretty sure all of you will have some senior folk above you, which we usually call as your manager. Am I correct? Right? You will definitely have your manager. This neural network also has a manager. And by the way, this manager technically in neural network is an optimizer. You remember Adam and SGD that you tried out? So you know what is the duty of this manager? This is you. This is you. You were given a task, and because you are not that experienced as the manager. So let's say I'm your manager. Assume I'm the manager. I gave you a task and you have an error of 3000 because you are not as experienced as me. I have spent 15 years doing the same thing. So definitely I am better as compared to you. So you have a loss. What I do, I keep on staring at your work. how are you working? And I realized that you are having a total loss of 3000. You are having a total loss of 3000. Then what I did, acha. So I'm experienced. I am experienced and I know the things much, much better than you. I realize, acha, okay, these mistakes are happening because of the wrongly initialized weights and the biases. So I say, guys, let's now do backward propagation. And while doing the backward propagation, manager says, I will tell you, you went wrong because of the wrongly initialized weights. So manager will tell you the right way to adjust the weight and the biases. So manager says that Darshan, you know what, this 400, better you make it as 350. In the same way, in the same way, I also told you what all other weights and the biases can be adjusted. From my experience, I told you how to adjust the weights and the biases. But obviously, I'm not making changes everywhere. I'll only explain with respect to one weight, but all the weights and the biases are adjusted based on my experience. And then that completes our for backward propagation. All the weights and the biases are adjusted. So friends, what you just completed was one epoch, which is one forward propagation and one backward propagation. Now we have already implemented it multiple times. You implemented it, you ran it for 10 epochs, 15 epochs, 100 epochs. Some of you even ran for 800 epochs. So now you actually know what happens in one epoch. One epoch is one forward and one backward propagation. Okay. So I guided you that you make this 400 as 350. Done? Then you start with the second epoch. You again send over here the first image and you predicted over here, let's say 1. Actual was 0. Then you send the next image. You predicted over here 1. Actual was 1. Then you send the next image. You predicted over here 0. Actual was 0. In the same way, you again kept on sending all the 1000 images. So you'll be again getting 1000 probabilities. And you have the corresponding actuals as well. You once again calculate the total loss using this formula. And let's assume that this time you got a total loss of 2613. Tell me, I was your manager. Did I help you to become better in the second epoch? Did I help you to become better? Yes. With my experience, I adjusted the weights, and in the second epoch, you got a loss. But is my goal of zero loss achieved? No, no. Obviously, I am a manager. I'm not God. I don't know the 100% perfect values, but I am becoming better and better. So I say that, okay, so this is the loss that you are getting. I said, let's once again do the backward propagation and once again adjust the weights. So manager said that, you know what, this 350, you make it as 325. In the same way, you adjust all the weights and the biases. I'm again explaining only for one. Done. Then my epoch number 2 is over. Then you start with the third epoch. Again, you keep on sending first image, second image, third image, right up to the 1000 images. You get 1000 predictions, you get the 1000 actuals. You again calculate the total loss using this, and let's say this time the loss came out to be 2500. Did I again help you to become better than the previous one? Yes. Okay, very good. So I say, let's once again do the backward propagation. And I said, let's make it as 250. Huh? I said, let's make it as 250. From 325, I made as 250. Third epoch over. Third epoch over. Let's get ahead with the fourth epoch. Again, I send all the images. I get 1000 predictions. Next, I get this. This time, it became 5,595. Now tell me, I'm in the fourth epoch. Was I able to help you to become better or not? No. I can also commit mistakes. I can also commit mistakes. But then I realize, acha, okay. So maybe this 325 to 250 was a very drastic reduction. So now the manager said that, okay, let's make it as 275. In the same way, all others are adjusted. Your fourth epoch is over now. You start with the fifth epoch. Again, you send the images up to here. You get the 1,000 predictions, 1,000 actuals. You calculate the total loss. And this time the total loss came out to be 2,400. Was I again helpful? Yes. This story keeps on repeating till the number of epochs that you had put in comes to an end. So basically, every epoch is like you are being given a book. You are being given a book, and every epoch is like studying this book one time and giving exam. So if I say you have 100 epochs, you have studied this book 100 times and have given the exam on this book 100 times with the aim of becoming better with every epoch. We have already seen in implementation that just increasing the epoch does not necessarily mean that the accuracy increases. So overstudying is also a problem. That is also one thing that we have realized. You remember it, right? You have actually implemented and checked it out, right? Yes. Overstudying is also a problem. So basically, the thing is, just like machine learning, somehow you have to find a sweet spot where you can settle down. And what is the sweet spot? The sweet spot is exactly what we were looking at, the loss and the accuracy curves, right? A perfect loss and validation loss curve, a perfect accuracy and validation accuracy curve, where we are satisfied that our results are good, is considered as the sweet spot. And that is how a neural network is trained in real life. You can't even think of solving one single problem of a neural network with pen and paper on your notebook. There are so complex calculations, you will 100% go wrong. But for a machine, it is just a repetition of the things. If I am doing a binary classification problem, listen to me. If I am doing a binary classification problem, then which activation function will you give in the hidden layer? And which activation function will I use in the output layer for a problem like iris dataset? Setosa versus versicolor versus virginica. It is Softmax. Because iris is a multi-class classification problem, and sigmoid is used in which scenario? I know it's used in the output, but in which scenario? Right, sigmoid is used in this. Which is the default go-to optimizer with respect to the number of neurons that we add in the hidden layer? With respect to the number of neurons that we add in the hidden layer, tell me what is the usual uh, number of neurons that we should keep on adding in each hidden layer? Number of neurons in each hidden layer should be double power of 2. Yeah, that's more perfect. It should be increase in the power of 2. So if this is an input layer and this hidden layer has 32 neurons, then this should have 64 neurons. This should have 128 neurons. This should have 256 neurons. And maybe at then you can have an output layer. Right? Yes. So it should be always increase in the power of, sorry, it should be always increase in the power of 2 raised to n. or it can also be decreased in the power of 2 raised to n. So by that I mean to say that in the input layer, after that, if you are having a hidden layer, if you go for 256 neurons, this can be 128, this can be 64, this can be 32, and then it can be your output layer. So you either increase or either decrease. Follow one of the strategy. Some of them will recommend you increase, some of them will recommend you decrease. Anything is fine. We looked at various ways of building the neural network. First, you create a model and then keep on adding layer. tf.keras.layer.input. Shape is 30. Name is input layer. Now, what was the rule to give the name? Or was there any rule to give the name? So can I name the first layer as Preetham? But we will always try to give the names which are intuitive in nature, which actually tell what is that layer is about. Okay, here. So we do this. One more important thing I want to tell you. I don't know if you noted it, but it's time for me to highlight it. Mm, see, you know, TensorFlow, we are using the TensorFlow framework. So ideally, it should be TF. Then I want to use the TensorFlow ka layer. So TensorFlow dot layers dot input. When I want to use the TensorFlow's dense layer, TensorFlow dot layers dot dense. TensorFlow dot layers dot dense. TensorFlow dot layers dot dense. My problem is, what is this guy doing in between? Who is this and why is it even required? Did we discuss that? I don't think so. I told you this. No, right? Yes. So now you listen to a very, very short story of few lines. So basically, why Keras? That is the question. Because TensorFlow says even I can do that. So that's the major concern which I am looking into. TensorFlow alone can do it. In fact, TensorFlow is a framework by which company? Google. Very good. So when TensorFlow was initially launched, so Google launched the very first version of TensorFlow, TensorFlow 1.0. Now 1.0 means 1.0, 1.0.2, 0.3, many layers came. Just like here, it's 2.19.0. So here also, many layers came. Okay, then the problem was over here, friends. The coding of TensorFlow was difficult. So tomorrow, if you come and tell me that I am not from a Python background, then honestly speaking, doing the coding in TensorFlow would be a nightmare for all of you. You will not understand the code only. It is that difficult. In fact, I have seen TensorFlow code. If I go to ChatGPT and I say over here that you are an expert in TensorFlow framework, solve the breast cancer classification problem using a neural network created using the framework 1.0. Let us look at the code because what we understood was 2.19.0. Basically, 2.0 is what we understood. Look at the 1.0 code. I had taken some sessions on it and then it got replaced. It's difficult. Have a look at this. tf.placeholder tf.32. We are creating a tensor first of all of this shape. That is no rows, but 30 columns because 30 columns are there in our breast cancer problem. Similarly, one more for Y. Similarly, one more you are creating for learning rate. Similarly, one more you are creating ahead for training. Then this is the weight initialization technique, bias initialization technique. You have to do everything. Today you are not doing anything. What you did last time with respect to the creation of the network is this. Where did you initialize the weight? Where did you initialize the bias? You did nothing. You were just relaxing. Have a chill pill. TensorFlow was doing everything in the backend for you, but here you have to do everything. No mercy. Then look at the code. Weights initialized, biases initialized, and then we add an activation function. First layer there. Then these are the second hidden layers, weights and biases. These are the third hidden layer. Then this is the activation function, right? You see over here, you have to actually do that W into X plus B. दिख रहा है ना? W into H, that is the X plus B for the third layer. Here, W into H1, W2 into H1 plus B2, second layer. W1 into X plus B1 for the first layer. Then this is the loss function. You have to write the loss function. Today, what you did for writing the loss function? Lazy people, what did you do? You just have to spell it correctly. You just have to spell it correctly. And what you had to do earlier, accuracy. Then you fit that optimizer. Then this loss. Then you set it. Tell me, how many of you would have dropped from the deep learning track if you would have learned this style of coding as compared to the TensorFlow 2? It is difficult, right? Do you agree that 1.0 is difficult? It's not easy. In fact, for me also to take a very basic problem, it's like a nightmare. Just for taking that linear classification problem, I would have required 4 or 5 hours, and after that also you'll be like, oh my god, it was a very, very heavy class. This is TensorFlow 1.0. Right. So that is what we understand. And then all of a sudden, Google was not doing anything. All of a sudden came you know, we say na khuda ka nek banda. So all of a sudden, someone realized that this is a big problem. This is a big problem. So one person invented a layer which is working on the top of it. So what was the job of this layer is the job of this layer was that it said that I understand it's very, very complex. So it says that, hey, you know what, you whatever inputs you have, you give it to me. I will ask you in a very simple format. This is the input. You want this as the output. Tell me how many hidden layers, etc., etc. And I will convert it into the danger format, which is required by the TensorFlow. And then TensorFlow will be doing the computation. It will again return back the result in a danger format. This API said, I will take that result and then I will return it back to you in a easy format. So as a developer, our job was very easy. This was not invented by Google. This was not invented by Google. But this framework started becoming viral, just like you might have seen, right? If any Instagram influencer or YouTube influencer, he starts becoming viral, or any daily soap serial, let's say even like Tarak Mehta Ka Ulta Chashma, start becoming viral. Then what happens? Film stars or some others come into that TV show for advertising their movie, or film stars for increasing their movie audience, they offer some small roles to the Instagram influencers in their movie so that more audience is being reached. In the same way, this TensorFlow 1.0, where it was wrapped with the Keras API, not by Google, but by some person as an open source library. And they started becoming very, very popular, and Google realized it one day. And the day when Google realized it, Google actually hired that particular person. So the person who invented Keras API was hired by Google. Google integrated officially Keras API into TensorFlow, and they rebadged TensorFlow as TensorFlow 2.0. And therefore, you have to write every time pf.keras.layer because it is an API layer which runs over here. Are you all clear with it? Why.keras? I could not tell you everything on the day one. Step by step, I'm just unwinding the things. Very good. Developed by Francois Chalot. I used to ask this question, Sandeep, earlier, but this time I did not ask it because I myself had forgotten this person's name. Good, you found it out. Thank you very much. So, Keras is invented by Francois Chalot, not Chalot. Okay, Chalo, that's nice. So if you want, you can just take a screenshot of this so that you know what is the history, or I will also share it better. Those of you who want it, they can save it. This can be some of the questions which may be asked in the interview. People like me ask such questions to understand how much people know the background of the things, right? Many of them might even not be knowing this. Those of them who start learning deep learning in the last several years and then get into the industry or get into the teaching business, right? Training business. So they don't even know these all things. They have never worked on TensorFlow 1.0, right? So they would not know it. As simple as that. But today you need not even think about TensorFlow 1.0. Never, never, right? It's always about 2.0. So that's one thing you can just relax about it. Okay. Then we compile the model with the Adam and the loss function and the metrics. Then I say model.fit. So as you can see, I'm giving X-train, Y-train, epochs as 100. Validation data mentioned over here. X test, Y test, and we used to train it. You also played around. You also played around with this. Now I think I gave you some time where you played around with the various combinations. This is a probability value, and this is about whether a person has benign cancer or malignant cancer, where we had two types, benign and malignant. So this is predicting the probability. So we saved the model. We know we save it as Keras, and then we loaded and checked it. So what I do is, see, let us do it quickly. I won't be typing the code for it because again, this is not a part of the outline, but let's be a little bit smart. I'll be using the Copilot to do that, or maybe if I already, the one which I have is for the image processing problem. Like, yeah, the one which I have over here, I'll just show you that. I'll just show you that, and then we'll do it for hours. So I'll demonstrate this to you when we cover this use case. So for now, which is that use case? Kaha chala gaya? Ha, app.py. Open in integrated terminal. Streamlit. Run app.py. Have a look at this. Image classification problem. That's the next use case that we have to study today only. No, this is not the next use case. It is next to next use case. So coding part of it we will look into later. So we are asking it to upload an image. So I'll upload this image, and it was taught in the second day. So I'm just uploading this image. What is this image of? It's a very tall, small and tiny image. If you see, it's a very, very tiny image. So yeah, tell me, What is this image of? What according to you is this image of? Okay. So, okay, yeah, I think it's in the chat box. Right, night shirt, suit, t-shirt. Yes, it's, yeah, it is like a girl's top, maybe. Let's see. Let's see. Okay, so here, yeah, it is a shirt, by the way. It is a shirt. So basically, listen to me, yeah. Technically, the last layer that you have over here is a softmax. So what does softmax do? Listen to this very, very carefully, yeah, because softmax is what we are going to see it in the next problem. So softmax is going to predict 10 probabilities, because in this class there are 10 classes. Because there are 10 classes, it will predict 10 probabilities, but the 10 probabilities would be predicted in such a way that the total of all the probabilities is 1.0. So if you see over here, what is the probability of shirt? 94.83. What is the probability of being a t-shirt? It is 0.05, that is 5%. What is the probability of it being trouser? No, no, 0, 0, 0. So always remember the output would be such that the total probability will be 1. So you will always get 10 probabilities because you are using softmax in the output layer, and total of all the probabilities would be 1. But more than that, we are concerned with which is the highest probability. So basically, this neural network is trying to say that the probability of the uploaded object being a shirt is the maximum. Let's try one more. What is this as per you? What is this? This one. No, flip flop, sleeper, chappal, sandal. No, it's not a sandal. So, yes, open. We uploaded it and it is predicting it 100% it's a sandal. And then, what is this? Boots, shoe. Let's check it out. Ankle boot. Yeah, that's the actual name of the class. Yes. So it is predicting it as ankle boot with 96% probability, and as a sneaker with 2% probability. So this is the deployed version of the same. Okay, so I'll not get into this code at the moment. You just saw how it is deployed. I'll come down and press Control C, and let us actually open our Simplilearn folder. So simply learn this one, and morning deep learning, and yeah, no, did I delete all these things? 17th August was our last session. Okay, today is 23 August. Yes, so that's perfect. And we will have to download this notebook. We don't have a choice. File, download, because I deleted it from my thing. Done. So what I do is I will now run this, and I'll clear all outputs. I will run all. Obviously, we have to run it, right? Then only I will see the results. So the training part will take a minute or so, depending on how much we have trained it inside this. Okay, it's 100 epochs. I think it's done. Super. So yeah, we saved the model as well, and it is giving us a warning. So we updated the model as a Keras model. Okay, I delete it, and then I say over here, I get into Copilot directly because I don't want to type on the code. It's an additional topic, but I will explain you the code. So I say I'll add one more context of the files and folder, which is this. So two contexts added, and I say deploy the model created in the current notebook using a nice Streamlit app. Create the which is error free. Let us check it out. We got this. And right click Streamlit run app.py. It will ask me for 30 values. Yes, because there are 30 features, right? It will ask me for 30 values. All this 30. And when I give all of this 30 and I click on predict, it will predict the probability. So, and if I click on predict, prediction is benign. And yeah, this is just extra text. Now let us look into the code. You understood the output, na? Output was clear to you all, right? Basically, you are accepting 30 values and clicking on the predict button, and then it is predicting it is a benign cancer or malignant cancer. That's it. See, I just changed one of the values and it became malignant, right? Okay, perfect. Coming over here to the code, I have myself not gone through the code, so we import Streamlit, TensorFlow. For loading the data set, we have this. And then we have the tf.keras.load model. We are loading the model over here, loading the data set, loading the feature name. So for that, the data was loaded. So 30 features are there. We need the names of that. So for that, we loaded it. Then we gave it a title, breast cancer app, which, yeah, breast cancer classification app, and then enter the values. That's what you see over here. Then you can see over here, I have created a user defined function, which is having an empty list. It will go on through the features one by one, 30 features, and it will create 30 input boxes. That's what we see over here, right? Mean radius ka input box, mean texture input box, and so on. 30 input boxes, which are having plus minus. So this is the one. So number input, minimum and maximum value, default value is 0.0, and it will go on till 4-digit rounding off. Keep on appending that value, and once that value is there, all these values are obtained, then take all those values and convert it into numpy array, because originally in the dataset it was there in the numpy array format. We have seen that, right? So the data was, how was the data? It was in the sklearn bunch utils format. If you see that, which is more of like a dictionary, but like a numpy array only. So you convert it. So when I give a call to user input features, these all things are ready inside the input data. If you want to see the intermediate results, you can also do that. Then I say scalar.transform array scalar.transform. You created an object. Nana, this is wrong. Na, this is wrong. Because I told you at that time that whichever scaling technique we had used, we have to download the scalar model as well. So this is wrong. When the scaling is done, when I downloaded the model, I would say model is equal to this. And I'll also add one code that Save the scalar. Import joblib. Scalar dot. No. Import pickle. Pickle would be good. And yeah, use that. Then I say update the code to use the ideally whatever was used, the same thing should be used, right? So loading that and we say scalar, it loaded or not? Yeah, scalar is loaded and I need not fit on the cancer data. I say okay, let me see first. We accepted the input and then see directly scaling on this. That's perfect. Accepted the input one by one in a loop. And then if the button is clicked, yeah, we say if the button is clicked, then call the model.predict. It will give the prediction. I'll round off the prediction, then convert it to integer. Then I'll look for the target name of the class and it will predict the prediction and it will predict the probability. And SC dot mark down 3 hyphens. So that will be this. You see this 3 hyphen will draw a line and model linear classification, which is just a message, right? This is just a message that we are writing. I want to do this. That's what I wrote. Finish. And yeah, that is what. So let us confirm it once again. I saved it. So if I just directly click on predict, yeah. Okay. So the probability of it being benign is 0%. It should ideally tell the probability of malignant, but that's okay. I think we understand what we did. Okay. So what I'll do is over here in our D3, where I create a first folder, which is called as deployment. I'll just say, I'll add all. Now, question by Amit. Okay, sir, will there be any examples in the future classes where we use input from the JSON file or device logs to make predictions about the device? Ideally, no. But I don't think so. There is anything great to be done over here. Amit, if if you think about it, this is something which you can do it by yourself right now also. We are reading from a CSV file. You have to read it from a JSON file. Ideally, if you are ideally if you're reading it from a real device, then first of all, maybe using your IoT, right? Maybe connecting to the Raspberry Pi or anything. You will just have to establish a connection with that device, and that device will be sending you the input at regular intervals in the form of JSON. So that is not a part of deep learning. That is just a part of normal developers coding experience, where even if I go to Chat GPT and if I I'll just play around this. I'm not going to do it, of course, but just to give you a path, right? So, so basically, so Here, in this task, the first thing is we will have to establish connection with a IoT device, maybe using Raspberry Pi. Write a code to establish connection with Raspberry Pi so that I can get the details fetched from it periodically. Get me the Python code. This is what you will have to do, Amit, first of all. So you will be having a hardware device, you connect that to your computer, then this code will be used for connecting that device to your computer so that it is sending you the details at regular intervals. So you install the Paramiko module, then you have to establish connection. Standard code, right? Nothing great. Then you establish a connection with the Raspberry Pi where you look into these all things. Connection established, try fetching one data and you get it, right? So this is the basic thing. And after that, can you show a demo of how the output of this code will look like? See, this is how you establish a connection and you get this data in the JSON file. So this data is what something you will be getting periodically. So what will you do? That let us say I have given a call to the device and I have fetched the data for the last 10 hours, which consists of around 10,000 records in the JSON file. Now write a Python code to read that JSON file and then create a basic machine learning model by dividing the data into X and Y and then train test split, then scaling and then modeling and then predicting to find out the accuracy on the train and test data. So basically there is nothing new in your problem. We had already read the data. You want to read the data from the IoT device. That's not a part of our course to establish connection with any hardware devices. But see, you use the read JSON function from the path wherever the data is there. Then you need to normalize the JSON file. All of this, concatenate together. Then you need to divide the data into X and Y. Then you need to do train test split. Then scaling. Then you apply logistic regression. And then you get the output. So are you understanding it, Amit? You are not doing anything new over here, except the fact that you have to establish connection with the uh, uh, IoT device and ensure that the connection is successful so that the data is getting fetched into a variable which can be saved as a JSON file, and then you just read that JSON file just like using read CSV of pandas. We were reading a CSV file, you'll be reading a JSON file, and after that the process remains the same. So this has no relation with deep learning or training of the neural network or even training of the machine learning model. The only difference is initial way of fetching the data is different. Do we need to do PCA? I don't know, Manu. It depends on what is the data rate. When is PCA used? When you have too many independent variables. I didn't even check what are we getting as a input in the independent variable. So based on that, we will have to take a decision. This is just a dummy thing to explain amid the approach. Now you can explore further. So if there are too many independent variables which we are actually using, then probably PCA, else not required. You know that very well. Right. Then the next question, can we do the same activity in Colab? This is what Sandesh is asking. What others have to say on that? Can we do the same activity in Colab? You all are surprising me. Wait. I think, wait a minute. I think there is some confusion, guys. I think you are answering different. Wait. When he was saying, can we do the same activity in Colab, he was referring to the Streamlit deployment. Can we do the same activity in Colab? Creation of the app.py file and then running it. Yes. Because Colab file can only run the Python notebook .ipynb. And for Streamlit, if you notice, we are using the py file. Plus, you need a terminal for running it, which Colab does not support. So you cannot do that in Colab. Okay. Then one more question. I guess this was asked by Shanu. Yes. Sir, so far we have developed models on fixed or static data set, but in real time, uh, data keeps on updating. So how frequently we retrain the model? Manu, I'll come to you. I would like to see that in case if I'm missing something. So ideally, the life of a machine learning model is minimum 6 months to maximum 1.5 years. It depends. It purely depends on what is the size of the data. So I was saying, it purely depends on the size of the, not the size of the data, sorry. How frequently you retrain a model purely depends on the sensitiveness of the data. For example, if you look at a data like Google Maps, they need to predict in real time. If you are looking at a banking model, see, for example, we all know, very good question, by the way. We all know that long time back, how our parents used to copy in the school. If there is an exam, and let's say if they have to copy, huh? So how they used to copy in the exam? What was the most important medium used by them? Copy, perchi, chits, yes, or maybe asking the neighbors, right? Seeing back over back, right? That's correct. And then consider going back to the time when Nokia 331100 was launched, right? The Nokia phone, Nokia 3310. At that time, people were using earphone just like it was shown in the Munna Bhai movie, right? Munna Bhai MBBS. Remember, na? I hope you have seen that. You are not that small that you have not seen that movie. Right. So students are evolving. Then what is the latest thing used by the students to copy? What is the latest thing? Yes. Hey, how can they use GPT in the exam? Mobiles are not allowed. You are becoming too advanced. Mobiles are not allowed in the examination hall. In the examination hall, when you are writing an exam, where there is a supervisor moving there. Yes, smart glasses, good one. Bluetooth headset or smartwatch, right? Nowadays, you see everything on the smartwatch, which you can scroll and see if it is allowed. Right. So basically, what I want to say is we are evolving. We are evolving. In the same way, consider the domain like banking. Long time back, if a customer has to default a payment, there were some tactics which were used, right? Just like I'm sure you might have seen the web series. Uh, what was that? Harshad Modi wala web series, wherein that Pratik Gandhi is there. So, Scam 1992. Yes. So in that web series, we know that he just used one of the system rule to get the best money out of it, right? A loophole in the system. And then it was BR, right? BR receipts, correct, banking receipts. And in the same way, so that was one way of defaulting the payment. Then, obviously, when banks came to know about it, that rule was amended. But then, in the latest scenario, Nirav Modi defaulted a big payment and ran away from the country. So basically, people are becoming smarter day by day and learning newer and newer ways of doing the fraud. So today, if I create in 2025, in August 2025, if I'm creating a model to predict whether a customer is going to default a payment or not, and if that model is created, let's say with an accuracy of 90%, after 6 months, there is no guarantee that the model will still perform with 90% accuracy. Because in this 6 months, people understand, acha, okay, this technique is now getting caught by the machine learning model, and we have to come up with something new. So maybe the model, which is or which was 6 months back 90% accurate, turns out to be only 87% accurate after 6 months. And after 1 year, it turns out from 87 to be just 85% accurate. After 1.5 years, it turns out to be just 80% accurate. Now your client has to decide, is that acceptable? What is the rule? We need a model which is at least 80% accurate. So if the accuracy is dropping and dropping and dropping further, why is that dropping? Because there is a drift in the data. Correct? There is a change in the data. There is a drift in the data. And therefore, the accuracy, the real time accuracy of the model is dropping. And that is the time when your customer, your stakeholder will decide whether to retrain the model or to wait. Are they okay with it? Because retraining means it has to again get back to the data scientist team who had trained the model. So they will have to again retrain the model. So again, they are going to charge for it because they have to again do the feature engineering. They have to again analyze the latest real-time insights and then come to some conclusion. This is how it works in real time. And yeah, this is the answer to your question. So how frequently you retrain it depends on these all factors. Is that clear now? But usually the life of a model is 6 months to 1.5 years. After that, it becomes difficult. Image classification. There are still many things in the neural network creation which I have yet not explained you. Yes, but we will understand it in this notebook, right? We can do it on that notebook also, but we'll take it just for a change, right? It will be boring if we keep on continuing with the same thing. So just for a change, we will do this thing. So import TensorFlow as TF, and we'll look into the version of TensorFlow. That is fine. Yeah, this version looking is not important. Oh, yes. How can I forget? If this works over here, that's going to be a game changer. I never checked if any feature like that is allowed. So where were you asking about talking about terminal being there? Command palette this, insert this. Where is that terminal? Look into the bottom left. Okay. Terminal. So, now the thing is, if I open up the app.py, that doesn't open. That doesn't open. So the problem है ना, if let's see, I'll try uploading it. You never know, right? And right, and here I say pip install Streamlit. Let it do the thing, and then if it runs, then I say Streamlit run this. If it runs, fingers crossed. Oh, it ran. It ran. It ran. Congratulations. Let's see. Let's see. Fingers crossed. But this should work. It didn't open any local host. I'll copy this, right click, copy, and I'll try to manually paste it. This is a game changer. A game changer, no game changer. This is not working here for sure. At least this one is working or not. Fingers crossed. Let's see. And meanwhile, I'll try the third URL also. So yeah, if it's a remote server, then where is it running? This is certainly not working. And so that can be a good invention. I have a Jupyter notebook through which I have saved a deep learning model in the format using the Google Collaboratory. Then I created a so that I can show the deployment using the. Is there any way I can run this in Google Collaboratory? If yes, give me step by step details. This is not working. This is also not working. If this works well and good, na. If it doesn't work, doesn't work. Basically, if this works, that means there is no need to go for VS Code ever. So put your files in Colab. In Colab, open a new notebook. And after that, uh, either upload this or your model via the left pane and mount the drive. Okay, mounting the drive is one thing, and then put the app.py, install the dependencies, import Keras, this. It is there, but it is not that seamless. Port number and all. Option B is ngrok. I used this long time back. I don't remember it really. Long time back I used it. So basically what happens is, if we get into this process, then it becomes more confusing while teaching. Better is VS Code. Ngrok is definitely good, but better would be VS Code. So for Ngrok, you need to do pip install this and this. Get your ngrok key. You better try it in offline only. Common fixes and this. Fine. But one thing is for sure, it is not straightforward. You need to do one additional step, maybe ngrok or this Cloudflare as we got a suggestion. So it is better that we stick to VS Code. And next important thing, in the industry, everyone uses VS Code only. They VS Code, Eclipse, right? They will end up using the IDEs and no one is going to use Colab for real-time projects. So it's high time that you use that you use VS Code or other IDEs rather than using Google Colab only. Colab is very good for learning, no doubt about that. But obviously in real life, it won't be used. Yeah. So I'm importing TensorFlow. And then now we are actually working on the image processing. So if you pay attention, so we as human beings, we see any image like this, pixelated. Machines see it like this in the form of numbers. And these numbers are always in the range 0 to 255, where 0 means black and 255 means white, and any number in between 0 to 255 is a shade of gray, because I'm only talking right now. In fact, this entire week we'll be talking only about the black and white images. We are not talking about the color images. Then in the next week, we get started with the color images as well. So over here, I was talking about the same thing. So if you see over here, this 0 is black and this 255 is white. Or see, this is how machines see it. 0 is black, 255 is white. So basically, if I try to combine the output of how humans see versus how machines see, this is how the interface looks like. So this is kind of a human face. I know it is pixelated, but this is how the data looks like. So images are like this. Okay. Then now the problem that we are working on is the MNIST dataset. So the thing about MNIST data is, see, this is a classification problem. Listen to me very carefully. We have a dataset right now, and the best part is, see, um, we are here to understand neural network. So just like we had the lowered breast cancer, which is a built-in dataset, exactly in the same way, this MNIST is a built-in dataset. It already has 4 parts ready. So you don't have to do the train test split. So what is there in this 4 parts? Listen to me. We have an image. Let's say this. And we have a label, which is what is this image about? Image. And what is this image? So basically, someone has written it on a black paper with a white pen, and that photo is captured. And what is that image? Then we have one more photo like that, like let's say this, and then we have the then we have the actual label to it, which is here. And so on, we have many images and their labels. Let me tell you very clearly, you know how many images are we having like that? 60,000. Yes, 60,000 images are there. So obviously labels would also be 60,000 na, common sense ki baat hai. And that is only in the training data. So this is for the first time you are working with such a huge data. And what about the testing? You have 10 images over here, which is again not correct. 10,000 images, and we have the 10,000 labels. You understand this? So friends, here the independent variable is not a column but a image. And the dependent variable is what you see at the top, 5, 0. It's basically a classification problem because there are some idiots who write numbers like this. What is this number? It's difficult to figure out. What is this number? Right? So there are some people who don't write it properly. Problem is not those people. The problem is uh, we are working on a image classification task. Yes, so when I say image classification, we are here in the process of classifying the images. So we are going to make a machine understand the relationship between image and label for not one or two, but for all the 60,000. And once that is done, you are going to ask it to predict on this 10,000. You are going to ask it to predict on this 10,000. So obviously you will be getting the 10,000 predictions. So here technically I have the 10,000 predictions. I have the actual. I compare it, and what I get from this is the test accuracy. In the same way, I can also ask it to predict on the test data. So I'll be getting 60,000 predictions, and I'll be also getting the 60,000 actuals. Then, of course, we'll be comparing that, and what we calculate is what we call as the train accuracy. So essentially, if you look at it, our problem is the same. If you look at it, our problem is the same. I'll share it with you, and because this is the first thing, so I'll just add it in the image as well. So yeah, this is what we have. So technically, if I talk about it, we say this is our problem statement. I want you to read it. I want you to read it. Now it should be clear to you. So the CNN part is not right now what we are going to do, but that will be the fashion MNIST, right? Over there, we will be working on the CNN part as well. So we'll be working on that part over there. So here I say, let us actually get started with it. Now, see, the reason for choosing this data, let me tell you that, in real time, you will be having a data separately in the sense in real time. Let's say if you are working on a problem statement, this is a weather classification assignment. Have a look. In real time, you will have the data something like this. So you will have something in the train and you will have something in the test. So in the train, let's say, if I'm doing a weather classification problem, you will have a problem like this. Let's say there are only three types of weather right now with me. So you'll have two images, a train image and a test image. Or you can only have one particular folder where there are total 1000 images all mixed. Here, this is still sorted. You have the train images and the test images, or it can be just a single folder inside with all the images are there. So here it is little bit more sorted. So we have a folder called as cloudy image. So inside that, you have this cloudy. You can see the cloudy images that we have, right? We can see that over here. Cloudy images. In the same way, you have rainy images. In the same way, I have sunny images. So this is just like in MNIST, it was a digit classification problem. Here, the problem is on the weather classification. But the problem, you see the challenges over here. Every image is of a different size. So you will have to do that pre-processing to convert everything to a standard size. In the test image also, in the test also, you have cloudy folder where you have the cloudy images of different sizes. In really, you have the rainy images of different sizes. In sunny, you have sunny images. So machines want the data to be of everything of the same size. So these all are challenges. But in MNIST, we don't have those challenges as such. The reason we don't have that challenges is in MNIST, every image is of a standard size 28 cross 28, 28 rows and 28 columns. So if this is, let's say, as a demonstration purpose, if this is one of the image, it looks like this. So ideally, see, this is actually, whosoever created this image, it is wrong. It is wrong because which color I said is black? Which color is black? Oh, sorry, which number is black? 0, right? Yes. And white is 255. And if you look into our images, the text is written in white. The text is written is white and the background is black. So that means you agree that the background is all 0, 0, 0, 0, 0, and here there are some values either 255 or maybe little closer to 255. But here his background is white and the image is black. That's okay. Technically, what is correct? Technically, black is 0, white is 255. That is correct. So over here, so technically this is correct. So here, numbering wise, it is. So here, if you see his numbering is correct. Black, 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 black. But here it is 255. So that's correct. Numbering wise, it is correct. But the image, ideally, the background should be black and this should be white. But this is wrong. But this is correct. So basically, the author of the image is wrong. I cannot create such an image. So I just randomly took it. Did you understand this? Everyone clear with this? Yes? Very good. So this TensorFlow is already having this data just like our just like this linear classification problem in the sklearn had this breast cancer data. In the same way, TensorFlow has this MNIST data. So here, did we import TensorFlow? Yes. Now I want to load the MNIST data. So I said MNIST is equal to tf.keras.dataset.mnist. I like to print MNIST. You will not see anything. And then after that, if I actually print type of MNIST, it is of the class module. So here you see this. So type of MNIST is module. So basically nothing is there. But I told you MNIST is having these 4 things already ready. Xtrain, Ytrain, Xtest, Ytest. So the way to load these 4 things is also very, very standard. Here I say Xtrain, Ytrain, Xtest, Ytest. This is the very standard way. You use the MNIST ka load data function, and then I will like to print the shape of Xtrain, Ytrain, Xtest, Ytest. So as you can see, printing the shapes, what is it saying? It says Xtrain ka shape consists of 60,000 images. Each image is of 28 cross 28. So all these images are perfectly square. So no reading of the data from the external images like I showed you in this. So here we had to read all these images. So you have to use the computer vision library to read the images. So these all tension is gone for now. In the Ytrain, 60,000 labels. Then in the Xtest, you have 10,000 images, each of size 28 cross 28. And then here I have the 10,000 labels. Okay. Now, if I show you, if I print Xtrain, sorry guys. So I was saying, see, if you look into Xtrain, this is what you see, right? Okay. Let us look at Xtrain of 0 because this is very big. Xtrain is 60,000 images. We will go mad. This is, so I say, show me 0th image. So this 0th image should have what shape? This 0th image should have the shape 28 rows and 28 columns. You see that it's there. And if I say that, okay, let me see the 0th image. This is what you see. Now you'll be like, but Darshan, see 0 is black, 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 black. Somewhere in between little higher values. This is 28 rows, 28 columns. So if you see carefully, friends, first row, second row, Just like that, we have 28 rows, and each row consists of 28 values. So obviously, we are not interested in looking at these numbers, but I am definitely interested in looking at what is this image. So is there a way I can see that image? Yes, you can see that image. So what will I do is I want to plot the zeroth image of extreme. So I import the matplotlib module. Then I say I want to I want to I'll also like to show you my Y train. What is that image about, right? Before I plot that image, extent of 0 we saw. I look at what is the zeroth image about. It is about the number 5. So the zeroth image is about the number 5, but we are yet not seeing the image. I like to see that image first. So you see, this is that image. How did I print it? Let's look into the code. We imported matplotlib. Then I say plt.imshow. So what is imshow? So basically, it is a function to show the image. In very simple words, you want to plot the image. It's there in the form of pixel values. So it is a function that is used to display the image. It takes 2D array, which is exactly what we have for grayscale images, or 3D array as well, and it renders the image. So then it is printing something extra. That's okay. I don't want to read it. So if you see over here, plt.imshow, so it is showing this image. And axis, I'm turning it as off. If I turn on the axis, see right now there is nothing on the axis. If I comment that code, you see this axis. Now what will we do with the x and y values over here? It's an image, right? Better we turn it off. There is no harm in keeping it, but better we turn it off. Plt.axis off. Plt.show is for displaying the image. And plt.title, I say label, and it is a format specifier. What will be replaced over here is y train of 0. What is y train of 0? Y train of 0 is 5. So label colon 5 came. Acha, you see anything fishy in this image? Anything fishy in this image, according to you? Yes, it is colorful. And I did say all these images are what in color, what in nature? Are they color? No, they are grayscale. You know what? You know what? The problem is not the images. These images are black and white only. Basically, the IMShow function by default displays a heat map. So you need to write CMap is equal to gray, and your job is done. Also, the image is very big, so I will like to write plt dot figure fixed size is equal to 2 comma 2. Yes. Uh, let's try displaying this images then. So I say, let's try plotting the 111th image. So I do that. This is 3. This is 53,458 image. And this is 9,998th image of the test data. So you can see over here how it is. Right. So this is clearly making us understand what kind of data is actually there over here for inferencing. Okay. After this, the next thing that we need to discuss is we saw the images, and now the next important thing over here is machines don't like big numbers. Or I can also do one thing, let's plot a 4 cross 4 grid of images from X-train. So labels from X-train. plt dot figure 8 cross 8. Then I say plt dot plot 4 cross 4 And here, no, these are not random images. Yeah, that's okay, but I think so. You can see over here, it is just plotting first 8 images, image and their labels. You can see how the quality of the image is, right? So basically, this is plotting image 1, 2. You can see over here, right? Extrain 0, extrain 1, extrain 2, and so on till extrain 7. First 7 images are plotted using the subplot function, just randomly plotting. If you want to do that, then now you see next thing. The next thing over here is, these images, even if you look at extrain of 0, pay attention, this is important. These images are are having very high pixel values. Pixel value which is going from 0 to maximum 255. Machines don't like big numbers. Machines don't like big numbers. So now, now we are getting into normalization of the pixel values. So why normalization? So what does normalization does? It basically rescales the pixel values which is in the range 0 to 255 to the range 0 to 1. And how does that happen? Well, the idea is very simple. All the image pixels are in the range 0 to 255. When you are dividing 0 by 255, it is 0. And when you are dividing 255 by 255, it is 1. And all the values between 0 to 255 will be becoming between 0 to 1. That is the main idea behind it. So the idea is to ensure that each and every pixel value is divided by 255. The idea is to divide each and every pixel value by 255. So they say that it is important that neural networks are given normalized values for faster convergence. Normalized inputs help the model to converge faster. Similarly, we have improved stability and better performance. So the thing is, how do you do it? It's very simple. Xtrain is equal to xtrain upon 255. Xtest is equal to xtest upon 255. This is just like scaling. Specifically, which technique scales the values in the range 0 to 1? In machine learning, which technique used to scale the value in the range 0 to 1? Right. So min-max scaler. Min-max scaler is a normalization technique, and standard scaling used to scale it mostly in the range -3 to +3. So -3 to +3 was your scaling technique. So that is scaling. This is normalization. There is a difference. Scaling brings the mean at 0, just like standard scaling. Normalization brings any range to a normalized range of 0 to 1. That is the difference. So min-max, that's correct. Okay. Now, so we do that. Now that the pixel values have changed, I don't think so there will be numbers anymore. For example, these images will also change. Let me randomly try executing this. See, this is how it was looking. Now, how does it look? Still looks the same. Let us look at this last image 6. See how it looked. It still looks the same. Basically, normalization is what? Something which is so big, you are just making it small. So it is like saying that this point came here, this point came here, this point came here, and this point came here. So everything has proportionately become smaller. Everything has proportionately become smaller. That's the most important thing. Everything has become smaller. So the object still looks the same. Therefore, the image before normalization and after normalization is the same. So then, after that, the next step would be to building the model. So now, I would say over here, let us build or instantiate the ANN model. So now, on TensorFlow or Keras import sequential. Now, one very important thing, very important thing. See, right now, if you look into our images, this is how the data is right now. Look into this yellow ink. On the x-axis, you are having images. And on the y-axis, we are having the label. So now the concern is, how will the machines establish the relationship between the images and the labels? Machines don't understand images. Machines only understand numbers. So the thing is, how to establish this relationship? So over here, the idea is very important. So have a look at this. When you have an image which is just 3 cross 3 in size and you say flatten it, do you understand what has happened in the flatten? Do you understand the output, input and output? Do you understand the difference? What has flatten did? Right? Yes, 110 flatten, 4 to 1 below that. Exactly. 3 cross 3 to 1 cross 9. Right? Now, what is the length? 1 cross 9, right? Yes, that's correct. 1 cross 9 is the length. But in MNIST, we are not having the images of the size 3 cross 3. What is the size of every image for us? Yes, 28 cross 28. So tell me, friends, when I flatten it, what will be the length of the output? Very nice. Yes. 1 cross 784. 1 cross 784. Now, ideally, see, this is how they have shown you flatten it. But let me tell you that initially, when this image is flattened, it looks like this, chapta. And then you create a transpose of it. So ideally, this is flattened, which will have 1, 1, 0, 4, 2, 1, 0, 2, 1. And then this is the transpose of it. This is flatten and this is the transpose. Remember this, huh? So earlier this happened. So how many images are we having in the training data? 60,000. Now understand the bigger picture. So imagine this to be a 28 cross 28 one. So right now, when I flatten this, we know that it becomes like this. So this will be of length 784 comma. This will be of length. Every image. This is the 0th image. When you flatten it, it will be like this. Let's not look at this part as of now. When you have this image, when you flatten it, you are having. So when the 0th image is flattened, it will look like this. When the first image is flattened, so when I take the first image, which is again of 28 cross 28, when I flatten it, it will look like this. In the same way, I have 60,000 images. So when I keep on flattening it, I will have 60,000 things like that. Right? This is the last one. And obviously, we have the dependent variable, which is what that image is about. We have the dependent variable, which talks about what that image is about. So like this first image was about 5. Next, it was 0. And the last one. So basically, now if you technically think about it, This is independent variable 1, 2, 3, right up to independent variable 784. Is that making sense to all of you? So this extrain, can I say that this extrain is now 60,000 rows and 785 columns? Can I say total size of this yellow and pink box is 60,000? Is it 60K cross 785? Correct? After flattening every image, 60,000 cross 785. Now let's put a little bit of recall on the memory. You have worked with so many problems so far, even the PCA one. You see over here, the number of independent variables over here is the highest. 784 independent variables. But the best part is, these images are now converted into a standard form. That is the best part. And obviously, on the test data also, we have 10,000 images. So you will be having the 0th image, first image, so on. You will have 10,000 images. And obviously, you will have corresponding 10,000 labels as well. Right? So the dimension of this, tell me what will be the dimension of this red content of the red box? Yes, 10,000 cross 785. Very nice. Yes, you all are getting it perfectly. 10,000 cross 785. That's absolutely correctly said, everyone. So if you now notice that our data has once again become like a standard machine learning problem. Yes or no? We have converted this data into a standard, and you know what, friends? This is what we end up doing with every problem. With every problem. In fact, even when you work with, let's say, a speech data, or you work with a audio data, or you work with a video data, any type of data you work with, you convert it into this format only. Everything and always gets converted to this format. That is one of the very important thing to be noted over here. You'll always have the things converted to one standard format. So over here, forget about TensorFlow. We will now try to solve the problem using logistic regression. So I say, let's continue. No, not logistic regression. You will have to go for decision tree classifier. It's a multi-class classification problem, right? Logistic is mainly good for binary classification. Building the ML model using the, so here we say sklearn.tree import decision tree classifier. Then I say create an instance of decision tree classifier. Max depth, I will play with it. And then I say decision tree, I want you to reshape the data to 60,000, 28, 20. See, till this point of time, we have not flattened. Till this point of time, we have not flattened. So if you see right now, if I just check. Now, have a look over here. My original shape, when I say extrain shape, it is 60,000 images of 28, 28. If I say extrail dot reshape and giving the 60,000 images and each of 28 cross 28, I am asking it to reshape. So it is becoming 784, exactly the way we wanted it. So therefore, I say decision tree classifier, do this net full. Then I say Y prediction on the train. All the test. Accuracy score for the train and test. We can see over here, I'm getting a decision tree model with an accuracy of 89% and 86%. That's good. Let us try to build the model using not the sequential API, but let's say support vector classifier. So create an instance of it, fit on it, predict on it, and just check the accuracy. Don't we need a 98% accuracy? Why don't we need 98%? Of course we need it, but we are not getting it now for now. We need it, but the thing is we are not getting it. And anyways, we have to implement this using a neural network, right? This is just one example. You can see the time it is taking, right? We'll be doing it using neural network only. Just wanted to confirm. See, after taking so much effort, we are able to get a 97% accuracy. That's good. So we understand that in this way, we can implement any other model as well if needed. That's not at all a problem, right? We can implement any other model as we need it. So now it is the time to do the same thing, but using a machine learning model. Oh, sorry, not a machine learning model, using a deep learning model. Deep learning model. Yes, sorry for that. So now it is the time for doing these things using a deep learning model. So, but we saw that the same thing can be done, but this is a very big problem. 784 columns. In fact, I remember if you are really having that high amount of data in such scenario, in our machine learning classes, I told you that it is better that we go for PCA. But here I didn't go for PCA or anything. And yes, we still see this working, and these are the results over here. Now, this is, yeah, this is what we have so far. And now it is time for us to build a neural network. So I am doing this. And now look at the process. So model is equal to sequential, because we have already imported sequential, which is like a placeholder. Then model dot add input layer. So input is of shape 28, 28. Every image is of shape 28, 28. That is what is given. After the input image comes, I am calling the flatten layer, which I never called earlier, but now you know what is flatten doing. In fact, a machine learning doesn't have flatten or something, so we had to do this jugaad of reshaping it to 28, 28, and reshaping it to 28, 28 was nothing but flattening it. But in deep learning, We flatten it. And then we add a hidden layer of 128 neurons. And then I'm adding another hidden layer of 64 neurons. And then I am adding an output layer of 10 neurons. So there will be 10 probabilities which are coming. Activation is softmax. You know that very well. And this time, if you compare it with your breast cancer classification problem, which had only 30 independent variables, this problem has 784 independent variables. Far more big and scalable. Okay. After that, what was the next step? I forgot. After this build or instantiate, what is the next thing that we do? What is the name of the step? Compile, then train, and weight biases. No, not weight and biases. Compile with optimizer, loss, metrics, and check the summary. Okay, yeah, we can check the summary and then we'll compile. Ideally, I was expecting compile only, but yeah, model.summary, we will check it. How many are there? So model.summary. So model is there now. What model is not defined? So ye kya hai? I don't know why. So yes, see the number of parameters that we are training. First, you are flattening it, so no parameter. It is just taking the image and making it flattened. Then a hidden layer. So how many? This number is coming. How is this number coming? This number is coming because of multiplication of 784 with 128. What is 784 into 128? 784. It will not actually come into 128. 784 into 128 is 16,68,352. 16,68,352. If these many neurons are connected, so this into these are the number of weights. So it should be same now. Yes, very nice. So if this is the input layer, which consists of 784 inputs, and if this is the hidden layer, which is consisting of 128 neurons, that means everything is connected everywhere, but there will be 128 biases as well associated with these neurons. So this value plus 128. So 352 plus 128, is it 480? In this value, if I add 128, is it 480? Sorted. Very nice. We are good. So that's one thing. 128 into 64 plus 128 plus 64. 128 into 64 plus 64 is 8256. 64 into 10 is 640. And 640 plus 10 neurons ka 10 biases is 650. So the total of this is 1,09,000. These are the parameters on which this neural network would be trained. So the next step is to compile the model. I'll not change it. Optimizer is Adam. Loss is sparse categorical cross entropy. Metrics are accuracy. And then it is the time for us to train the model. R equal to model.fit. Xtrain, Ytrain, validation data is being passed, and let's say I'm training it for 15 epochs. No, I kept it the same, no? Earlier it was binary cross entropy. No, yes, that's correct. Yes. See over here. I'll tell you. Good question. Good observation, I would say. See here. Earlier the problem was binary classification. So I used the binary cross entropy. If it is multi-class classification, let's write a note, right? So I say loss function. Our earlier problem for the breast cancer classification was a binary classification problem, and hence we use the loss function binary cross entropy. For multi-class classification problem, we will use the loss function categorical cross entropy, because binary classification is binary cross entropy. Multi-class classification is categorical cross entropy. But if you actually look into our MNIST data, you see our MNIST data consists of lot of zeros and very few ones. That is 0 to 1 or 0 to 255. If I consider, it consists of lot of zeros and less of values which are near to 255. So this matrix has lot of zeros. This also has a lot of zeros. This also has a lot of zeros. So basically, here, if you look into this, look at this. On the left hand side, you have a dense matrix. A dense matrix is the one which has hardly any zeros. But on the right hand side, you see a sparse matrix which has lots of zeros. So in the same way, when you are solving a neural network problem, you go for this. Therefore, you'll go for a sparse categorical cross entropy, because in our matrix, most of the values are zero. So therefore, we go for sparse categorical cross entropy. Else we go for only categorical cross entropy. So here, for breast cancer, binary classification, binary cross entropy. For the multi-class classification, we use the categorical cross entropy. And for MNIST classification, since most of the pixel values are zero, we use sparse categorical cross entropy, which is effective than categorical cross entropy. Yes, I think this should answer your question, Manu. Everyone have a look at it. Right. Are there any other options for other use cases? No. These are the only options that one should use. But there are many more loss functions available. So if I go to loss function TensorFlow, see, many are available. If you go to ChatGPT and ask which to use in which scenario, it will give you some scenes. But the generic rule says use the one which I recommended, because here, see, there are so many activation functions. So hit and try is good, but by default, everyone uses these rules only to get started. And they don't play more with the loss functions, but rather they play more with the activation function, neural network layers, hyperparameters of the neural network, etc. So, yeah, that's how it goes. Then, secondly, we misunderstanding epoch in the result. We misunderstanding epoch in the result. Sorry, I didn't understand what are you saying over here, Manu. Understanding epoch in the result. You mean to say this part of understanding, no? This one. This one, no? Yes. Interesting question. Yes. Last time we discussed it and we left it in improv in between. I remember it now. So now, see, in real life, if you look at this, what is the size of this weather data set? 29 MB. The size of this weather data set is 29 MB. Let me show you one more. I'm going on to this railway track. What is the size of this data set? Look into this. What is the size of this? This is railway fall track, right? Yes, you see this 2 GB. So look at this is basically there are only two types of images from defective tracks and non-defective tracks. Have a look at the defective tracks. Defective tracks. Defective tracks. And have a look at non-defective tracks. So this is a binary classification problem. And you see over here, because of the size of the data is 2 GB, my MacBook is very powerful, is what I realized, because I have a 16 GB RAM. But earlier I had MacBook Air which had 8 GB RAM. Now consider a scenario where the size of the data set is not 2 GB, but the size of the data set is 6 GB. So can a 6 GB data be loaded into a 8 GB RAM? What are your thoughts about it? A 6 GB data, can it be loaded into a 8 GB RAM? What do you think? Yes, no, possible, not possible. What are your thoughts on it? Can you load a 6 GB data into a 8 GB RAM? Difficult? Yes. If I look into my memory, 16 GB. So we started with the ANN for the MNIST image dataset using the TensorFlow. It was almost 50% done. First thing we imported, we all know what is the problem statement over here. It is a multi-class classification problem. Independent variable are nothing but the images and the dependent variable is nothing but the labels. So obviously you have to understand the relationship between image label, and in this way, you have 60,000 images, 60,000 labels in the training data. And in the testing data, you have 10,000 images and 10,000 labels. So this was the problem statement. The way to load the data set was very standard, which is this tf.keras.mnist. Then we look at the type of the data set, which is a module. Then for actually getting the data, you need to use the load underscore data function, and the data set is directly available into 4 parts: X train, Y train, X test, Y test. So, and that is what we are getting: 60,000 images, each of 28 cross 28, 10,000 images, each of 28 cross 28. Then, if I look at the shape of X train 0, it is 28 cross 28. If I look at the shape of Y train 0, it is 5. Okay. Then we just plotted one of the image which is X train 0 and CMAP equal to gray is very important. Only because it is black and white image, else it is not required. So we see that image, and at the top I have also given the title, which is nothing but the actual label of that image. Plot the 111th image. Import matplotlib.pyplot as PLT. And yeah, this is the one. This is some more images. So this is X-test ka image. Then I'll delete this. That's not required. This is normalization. Now, in images, you don't do scaling. You will not divide the images in the range -3 to +3. You always normalize it. And that's exactly what we have done in over here. So normalizing the images in the range 0 to 1. Done. Then after normalizing, I'm just checking whether the data still looks the same, and it does. We had seen that yesterday. Here also I tried to look one more image. Now the next thing what I told you is whenever you have a 3x3 image, we flatten it. So basically this will be here, this would be here, and this would be here. So this becomes basically a flattened one. And if this is an image of MNIST, instead of 3x3, it will be 28x28. So when you flatten, it becomes 784 comma, and you have 60,000 such images. So obviously this is the first flattened image, second flattened image, and this is the 60,000 flattened image. Similarly, in the test data, you have 10,000. So now we clearly have the data as we had during our machine learning time. We have the data as we had it during our machine learning time. So here, this was x dot reshape. And then obviously we tried to do that using the machine learning model. So machine learning model, we had to reshape this and then fit. And SVM is going to take a lot of time. We know that. Then after that, we came into the process of building our model. So here we say from TensorFlow.Keras.models import sequential, from TensorFlow.Keras import input and import dense and flatten layer. What is flatten? We understood, right? So you will directly use the flatten layer. You don't even have to flatten it by yourself. So you should know the right class. Then model equal to sequential, which is a wrapper. Then keep on adding. I'll add the input layer. My shape is 28, 28, which actually becomes 784 when you flatten it. So this is where the flatten happens. And then I'm adding a dense layer of 128 neurons. Then I'm adding another dense layer of this. I told you, you increase it in the power of 2 raised to n, or you decrease it in the power of 2 raised to n. And then we are having a final layer, which is 10 neurons. So basically, understand over here the process. So you have input layer. Fine. Initially, you have the input layer. So input layer is going to be a long vector of length 784. Then you flatten it, of course. Okay. So flatten is what is going to make every image like this, and then we make it like this automatically. Then I'm adding a dense layer of 128 neuron, which means there will be a hidden layer 1 added. There will be a hidden layer 1 added of 128 neurons. So obviously consider this as the input, this as the input, till this as the input. And this will be your neuron. Consider this. So obviously this is connected here, and this is connected here. This is connected here and here. Right. Then no, if you can't, you cannot. There was a time where you can, but now it is obsolete. Earlier you could, but now you cannot. Layer by layer only. Okay. Then I'm adding one more hidden layer of 164 neurons. So there will be one more layer over here, hidden layer, which is of 64 neurons. So obviously, then you are adding one more hidden layer of also one more layer of 10 neurons. So now I am actually adding one more layer of 10 neurons. One, So, and this. Okay. So now listen to this. This will give us some output. This will give us some output. This will give us some output. This is very important. This is important over here. So I was saying all of them are giving some output. This will tell what is the probability of the input image that you have given. What is the probability of it being 0? This will tell that whatever is the input image that you have given, what is the probability of it being 1? And this will tell whatever is the input image that we have given, what is the probability of it being 9. So this is something very important. Huh? So the last 10 neurons, we know that they are softmax, right? So this is how they will be doing it because it's an output layer. So it will tell what is the probability. So here, see this 64 neuron thing done. And this finally output layer of 10 neurons, activation equal to softmax. And that is exactly what is going to help it to figure out. So this is the neural network that which is what we have created. And then ultimately out of all of this, we choose the one with the maximum probability. So when I choose the one with the maximum probability over here, it will tell us. So Sandesh, we discussed this rule and Manu also answered it. You can either increase it, you can either decrease it. We have seen it in the earlier time. There is no 100% correct rule, but either increasing or decreasing, one of it is an ideal solution. Either increase or decrease. You choose to. It's basically hit and trial. Yes. So see, this is the network. So one important thing that you need to remember over here, important thing that you need to remember over here is you get over here 10 probabilities and the total of all of these probabilities is 1.0, 1.0. And hi, I told you that I showed you the fashion MNIST streamlet. You remember, no? There were 10 probabilities coming and the highest one we have to choose. Yaad hai na? Yesterday only looked. Yes, that's exactly what happens. And this is the neural network that I have chosen. I'll just take a screenshot of this. So I have added it over here. You can just skim through it. I'll give you a couple of seconds, maybe 10-15 seconds. And in case if you have any questions, you can let me know. Then, so looks like there are no questions. That's good. So we understood we created this architecture. Then ideally model or summary, I'll prefer to have it later on before fit. So then I say model.compile. I didn't execute this cell. Acha. Okay, done. And then model.compile, our favorite optimizer, Adam, loss function as we saw. And we do that. Here also weights and biases to be assigned. Raj, आज नींद हुई क्या? Did you sleep nice? Looks like this is your very first class. What kind of questions are you asking? I'm disappointed. Do we ever have to assign weights and biases in a neural network in TensorFlow 2.0? Yesterday only we saw, na, there was no need to assign it, Raj. You forgot or what? Okay, I'll tell you. If there is a confusion, I'll tell you. In TensorFlow 1.0, you had to do all these things. In TensorFlow 2.0, this assigning happens automatically. So, this optimizer assigns, no, the neural network is assigned random weights, and then optimizer slowly and steadily in during every backward propagation, it will adjust the weight, making it more and more better based on its experience. And in fact, in this notebook only, I will actually show you, all of you are not only Raj, this is for everyone, that what all are the various ways to initialize weight and how easy it is in TensorFlow 2.0. You don't have to manually do it, but you directly have techniques to initialize the weight. Just like this is a technique to add a hidden layer. This is a technique to add a flattened layer. In the same way, for initialization of the weight also, there are several techniques. That is also what we will study. But you don't have to do it by yourself, the initialization of the weights and the biases in TensorFlow 2.0. So we are relieved from all these things, Raj. Is that clear? Perfect. Welcome. If the output is going to give 10 probability and the max has to be chosen. No. Okay, max has to be chosen. I'm trying to understand what the softmax did. Should it not give? No. Softmax doesn't give the max probability. Never. See here. Softmax will always give 10 probability. See, machines are not interested to solve your problem, Anivesh. मशीन्स जो है ना ये आपका प्रॉब्लम सॉल्व करने के लिए नहीं है. दे आर डिजाइन टू गेट सम इनपुट एंड गिव सम आउटपुट. So Softmax has a simple role. I will take in input, and if there are 10 classes in the output layer, I will give 10 output. If there are 5 classes, I will give 5 outputs. Basically 5 probabilities. If there are 20 classes, I will give 20 probabilities. And the sum of all these 20 probabilities will be 1. So that is what Softmax does. In fact, if I even look into Softmax activation function, see ये देखो, this is how you get the output. So if there are 5 classes, this is what you get. देखो 5 classes है राज, ये output आता है. ये देखो, जो भी scores है ना उसको probabilities में convert करता है 70, 80, 90, 100. Output ऐसे ही आएगा. This is the way the output comes. It will always come this way. See this. Okay, perfect. So your see the understanding is very simple, Anivesh. As I explained you during the theory classes, Softmax will give us probabilities. And if there are 5 classes, it will give you 5 probabilities. 10 classes, it will give you 10 probabilities. So this is what it will always give us. Then I say model.compile. Then model.summary. And yeah, I want to know how I got this number. Tell me how the calculation gave us this number. ये number कैसे आया? Just explain me, because how is this calculated? Only I want to know that. Very nice, Sandesh. 784 into 128 plus 128. Perfect. Yes, that's perfect. Guys, good. 784, Pritam. That's wrong, na? 784 into 128 is not going to give you. Plus 120. Yeah, that's correct. Chalo, we understand it. Good. Then I am training the model. Did I explain you what is batch size yesterday? Okay, that's why I saw this. That's why I was confused. Perfect. Actually, there is There is one more deep learning batch which is happening with PW Skills, which runs 4 p.m. to 7 p.m. They are little ahead of you. So they have completed their CNN yesterday. So I know I get a little bit confused, and if I ask you such kind of questions, you know, please don't have that opinion that instructor itself doesn't know what he has taught. I get confused at times. Okay. So model.fit, X-train, Y-train, we have gone through that. So when you take the break, all 7 days you are teaching. That's very correct. I work on all the 7 days. I don't take breaks. I don't take break at all. But you know, when I need, I take a break, else I don't take a break. So, but next week, fortunately, I'm free because next week is Ganesh, right? So, next week there is no training. So, if you see carefully, so I'm gonna relax the next week. Though I have a lot of pending work, but next week, if you see, I'm relatively free. I directly have a session in the evening, Monday, evening session. 2 sessions in the evening, 4 hours of training. Tuesday, only 2 hours. Wednesday, I'm free. Thursday and Friday, 2 hours. So next week, I don't have anything in the morning. But since I think if you look carefully, since I guess that's little dangerous, huh? If you see since 5th of May, I have not taken a break. 5th to 9th, I had a full day training with the evening session also. This week also, this was 5th May से लेके continuous, it's working. Oh, now I realize actually I'm working too much, na? Right from 5th May, June, July, August, 4 months without a break. Ah, yes. Saturday, Sundays are always full. My Saturday, Sundays, you know, how is my Saturday, Sunday? I have your session from 9 to 1. And then after that, there is another session from 1 p.m. to 4 p.m. There is another session from 4 p.m. to 7 p.m. And the last session by Simplilearn, which goes from 4 p.m. to 10 p.m. Till last week, it was going till 11 p.m. So basically, there is absolute no gap, zero gap. मतलब ऐसा नहीं, there is a gap in between the two sessions. So Saturday, Sunday is very hectic actually, very hectic. Or I will say it is like a torture only. I just work. Actually, and no break for eating food also. So in fact, now also, what I usually do is when I give you the break at 11, I quickly go and have my breakfast. So that is the kind of things. So thank you, Manu. But anyways, I mean, that's okay. But next week I'm going to relax. So, chalo, coming back to the point, sorry for taking you away. This training was happening, so I could do that little leisure time. So, coming over here, hmm, nothing, I work by choice. Thank you very much, Shweta. So, here. So, I was saying we can see over here 86%, 95%, and at the end of 12th epoch, it is 99 and 97, and the loss should ideally reduce. So it went from 0.49 to 0.013. This went from 0.13 to 0.09, and this is done. And yeah, the last one. Then after that, something that we have done. So this is all saved inside the variable R. I'll plot the loss and validation loss. So R dot history loss, R dot history validation loss, and this is epochs and legend and everything is good. So what do we understand? Is it a good network or something is fishy according to you, or all good? Think about our understanding from the previous week and then answer. Not good. No, diversion loss is increasing. Very nice observation. Very good. Gap is increasing. Yes. That means instead of 15 epochs, if I train for 30 epochs, it's going to increase like this, right? One going flat and one going up. So that gap is increasing. That's very perfectly identified. Then let me also plot the accuracy and the validation accuracy. Accuracy is good. Gap is not constant, right? So what do we conclude over here? What do we conclude over here is, I can actually write it at the end only, that observation the accuracy is pretty high and the testing accuracy is also stable, while the training accuracy still has a scope of increasing. With respect to the loss function, we observe that the training loss has become stable while the testing loss is gradually increasing. This means that the model is becoming more and more confident on the training data set and relatively less confident on the testing data set, and hence the loss is increasing. This is an ideal scenario of overfitting, where we see the model is predicting confidently wrong outputs. Yes. So, yeah, we just made a note of everything. Chalo. Then, after that, we evaluate the model on training data set and testing data set. So, we see over here, we get this. So, training accuracy is 99.6 and testing accuracy is 97. So, that's very good, no? But training accuracy greater than the testing accuracy? Training accuracy is greater. That's correct. No, training is greater than testing. Yeah, of course, that's good. I don't know, I was confused a little bit. Yeah, that's perfect. This is perfect. So, yes, so that's perfect. There's no issues over here. Now, after that, do you remember something which we studied called as the confusion matrix? Ah, just to recall for all of you, I'm not teaching it, but just to recall, I love to take this example for the COVID always. So 50 people actually don't have COVID, and the test also predicted they don't have it. That is true negative. This is true positive. 100 people actually have corona, and the test also predicted that they have corona. 5 people actually have corona, test predicted they don't have corona. This is false negative. And false positive is 10 people actually didn't had corona, test predicted they have corona. Among these TPTN, FPFN metrics, which is the most dangerous in the corona scenario? TPTN, FPFN, which is the most dangerous? Ah, yes, very nice. Yes, chalo, good. So everything is here. So your capability to predict all unseen data is good. You guys are not overfitting. Okay. Then after that, I say, yeah, we have done that. Then it is the time to predict. Now, Anivesh or Raj, who asked that question? One of you, I don't exactly remember. I think Raj. Yeah, I think Raj. Anivesh asked related to weights and no, I think Anivesh only. Softmax का question किसने पूछा था? Softmax probability, artificial neural network output goes to the Softmax. Anivesh. Okay. Now you'll get the answer to your question, Anivesh. Little more details on it, right? Yes. Thank you. So now I want to predict on X test. So I say y predict is equal to model.predict on the X test. And if I actually show you y predicted, now pay attention. Y predicted का output देखो. Anivesh and everyone, of course, it is for everyone. Anivesh asked this question, so I am calling him. But this is more importantly for all of you. So when I say y predict, so understand over here that how many images do I have in the testing data? How many images do I have in the testing data? 10,000, Nishant, 10,000, right? So for every image, how many probability outputs will I get? There are 10,000 images. For every image, 10 probabilities. So for every image, so when you send your first image, uh, when you send your first image, second image, so on, so forth, till your 10,000 image. So here, when you send your first image, you get 10 probabilities. When you second image you send, you get 10 probabilities. When you send your 10,000 image, you get 10 probabilities. Yes, Raj, as you said. So we will be getting an output which is 10,000 rows and 10 column. I will actually first, even before showing you the output of y predicted, I will show you the shape of y predicted. Do you understand why are we getting it? Don't get confused, right? We all are understanding why are we getting it now. Are we interested in really looking at so many values, or we are interested in the prediction? Of course, we are interested in prediction. तो अपने को करना क्या है? What do we want? See, logically, I want the maximum probability from here to be chosen out. I want the maximum probability from here to be chosen out. So on and so forth, maximum probability from here to be chosen out. So basically, I am interested in 1, 1, 1, 1 output. Correct, everyone? I'm not interested in 10,000 outputs. I'm not interested in 10,000 cross 10. I'm only interested in the 10,000 outputs, which are actually the highest probabilities. Not interested in all the probabilities. So if I actually show you y predicted, it's a big lengthy thing. See, 10 outputs, 10 probabilities. So, and if I show you y predicted of 0, you can see over here 10 outputs are here, and This is a NumPy array, right? So if it's a NumPy array, see, total is 1. You take any image, 110th image, probability ka total is 1. Are you all with me so far? Very good. Perfect. Now we will have to choose the maximum probability. इससे तो काम नहीं बनने वाला. So I say my y predicted is equal to np dot argmax of y predicted axis equal to 1. We have already studied this argmax function, which returns the indices of the maximum value along the axis. So just to recall the syntax, this is what is the one. So this function is useful for converting our probabilities by selecting the class with the highest label. So I'm saying that in every row, select the highest probability. So NumPy, when we started NumPy, it was very difficult for me to tell you where NumPy is really helpful, but now this makes sense. So now when I show the shape of y predicted, see it is 10,000 comma. And if you say that, okay, show me y predicted, see, there are 10,000 probabilities. It says that in the test data set, the first image is of number 7, second is of 2, then 1, and the last 3 are 4, 5, 6 respectively. So, Anivesh, are you with me now? Is that 100% understood? Anivesh and everyone, right? Is this concept clear to you? Yes. Perfect. So, in fact, you know what? When I was using sigmoid in the earlier problem, how many number of neurons I gave? Remember, make me remember in the last problem of linear classification, cancer wala, how many neurons I gave in the output layer? 1. You know, that output 1, I could have used 2 also. I could have used 2 neurons also. So obviously, if I'm using 2 neurons, then I will have to give the activation as softmax. So what will happen? The upper neuron will tell me the probability of the person having benign cancer. Lower neuron will give me the probability of the person having the malignant cancer. And the total of that is 1. So if there is a 30% probability of having benign cancer, the malignant cancer will be 70%, total is 1. And among the 2 neurons, which is the highest one? Let's say lower one, so the model will predict it is malignant cancer. You can solve any sigmoid problem using softmax, but why is it required? If one neuron can do it, then why to go for 2 neurons and then get into the process of choosing the maximum? It is unnecessary, increasing the computational complexity. So softmax is nothing but generalized version of sigmoid, and sigmoid is nothing but just a binary version of softmax. Are you getting the mathematical understanding behind the two? They are one and the same only technically. Understood or not? Ha. Then it's fine. Very good. Okay. So here, now what I want to do is I want to plot the confusion matrix. Import cbon, import matplotlib, plt.figure. We get a confusion matrix created. Y-test and this. I'm converting it to a heat map, and this confusion matrix is getting plotted. Annotation is equal to true. Format is D. And then X label is predicted. Y label is actual. Title is confusion matrix for MNIST classification. And show. It is too big. So the thing is, first let's understand what do we understand. So remember, we have 10,000 images in the testing data. So it says that the number which was actually 0 was predicted as 0 970 times. The number which was actually 1, so images of 1 were predicted as 1 by the model 1128 times. So on, the image of 9, which was actually 9, was predicted as 989 times. We had to make the model even better, but for now, I'm just completing the notebook. Now, what I want to do, also, if you see, can you tell me which is the highest number in this confusion matrix except the true positives? So diagonal don't count, except diagonal, below or above the diagonal, below the diagonal or above the diagonal, not the diagonal. Which is the highest number? 25? Let me see, where is 25? Here. So basically, this is the number 6, the images of 6 are predicted by the model as 5. So basically the model is highly confused in between 5 and 6. Correct, na? This is what it says. It is highly confused in between 5 and 6. And not highly confused, total 10,000 images are there, but among them, highest is over here. Next highest, 14. 14, yes. So next highest is between 4, predicted as 9. So see, how come people write 4? You write 9 like this, and 4 you write like this. Or some people write 4 like this, and some idiots in a hurry write 4 like this. So it looks as 9 only, because the horizontal line of 4 is not stretched as it should be. And that is the confusion. Looks like that. I'm just guessing. And then, as you said, this 11, 6 and 4 are also confusing. Then, and so on. So what I will do is, so out of 10,000 images, I can say that if I have to find out how many misclassifications are there, if I want to find out how many misclassifications are there, so can I say that I will be finding the total of these two triangles to find out the total count of misclassified images? Right? Yes. So to find out the total number of misclassification, we will be doing it this way. Chalo. But of course, we don't have time to do it this way as well. So now what I do is I will first say that np numpy dot where all the prediction, sorry, where all is the actual, not same as prediction. So you know what? These are the indexes where the images are predicted incorrectly. So basically, a upper triangle and lower triangle image indexes are listed down. And if you see carefully, if you see carefully, the actual output is here. See. There is a tuple. Listen to me very carefully. There is a tuple, and inside that there is a numpy array which I have highlighted. Do you all notice that? Inside a tuple, there is a numpy array. Understanding now? Ha. So what I want to say is, I will select the zeroth element inside the tuple to exactly get the numpy array. I'll select the zeroth element, which is this part, which is the numpy array. See, there is no bracket around it. So what will I say? I understood this code. So I will say that let's find the indexes of all the misclassified images, and misclassified indexes is equal to this. I'll print it. Let me also print the total number of misclassified images. So which is nothing but the length of this array. See, if I find out the total number of items in this array, I'll find out the total number of misclassifications. So I'm saying that, let me see that. So out of 10,000 images, 202, 225 are misclassified. Out of 10,000 images, 225 are misclassified. Are you all with me? Did you understand the code? Very good. So now what I want to do, listen to me, one last thing. I will now randomly pick up any of the image index. I repeat, I will now randomly pick up any of the image index and I will plot it to see why has the model predicted it wrongly. Is there some problem with the image itself, or my model is bad? Because overall my model is having a good accuracy, na? If you see overall on the test data set, it is almost 98% accurate. So only 2% mistakes. So here it says that 225 misclassifications, 225 out of 10,000. It means the model, if I actually multiply by 100, it is just 2.25% mistakes. Out of 100%, only 2.25% mistakes. So 100 minus 2.25, which means the model is 97.75% accurate, which is exactly what was told over here. Are you understanding the game? How the calculations are working? How is 97.75 coming? It is coming from this calculation. Understanding, everyone, how it came? That's important. That's why I told you half of the notebook is left out yesterday. There are many things that we have to understand. Now what will I do is, I am going to take your exam. I am going to see how good you are in predicting. You are a human, right? Let's have a human versus machine competition. So now I am going to randomly pick up any one of the index, and after that I will be plotting that image. So I say plot some randomly misclassified image. So I say I is equal to numpy dot random dot choice. So obviously it will be randomly choosing any one of the index from the misclassified index, which is this. From here, it will be randomly choosing an image, and after choosing an image, I will be plotting it. So I give a figure. I say show that x test of I, and then I'm giving a title, true label and predicted label. Axis I'll make it as off, and I'll show it. You see over here, I have given the title with true label and predicted label. True. So the model is good, much good than us. But when it gave the model a Hindi, and if we rotate the labels, now wait a minute, you are talking about rotating the label, but confirm, confirm. So here, see, we got this, we got this. Now what am I doing? Now it's your, I'm just copy pasting the code. So whatever was code over here, I copy pasted. So it will once again select one random image and it will plot it. Now I am going to play with you. Chalo, bata, what is this image? You all are blaming the model. No, it is not good. So tell me what is the image? Three. Three. It is three predicted as two. But see, ideally, it is the model's mistake, or it is the person who wrote the number. He did not write it properly. Whose mistake it is? Person's mistake, right? Bad handwriting of human, exactly. Bad handwriting of human. It is, how can you break the model wrong? Yeah, we can easily detect it as curly braces, as Anivesh said. Once again, what is this? 4. And what the model might have predicted according to you, that also guess, you tell me 4 comma what? 4 predicted as what? You write 4 comma this, actual and predicted. Write it in this format, actual comma predict, sorry. So see, I will write it in this format, actual comma predicted. Let me see, what do you think the model might have predicted? 4, 9, 4, 6, 4 predicted as 9. Let's see. Let us see. It is 4 predicted as 9. And again, it is a human mistake only. It's again a human mistake. Now let us try to understand. Did you notice that all of us are getting the different result? Ideally, all of us should get the same result. For example, if I am the one who creates the model, I will go and tell to the client that I am getting an accuracy of 97.75%. Someone will go say, no, we are getting an accuracy of 98%, use our model. Someone will say, no, I'm getting 99%. Someone comes and say, no, that's impossible. There is no way you can get an accuracy more than 96%. And every time we execute our code, in fact, you executed it only once, you execute your code once again, it is changing. It should not change. So, you know why is it changing? Let's understand the process of forward or backward propagation. So in real life, whenever weights are initialized, whenever weights and biases are initialized, you remember I had told you while I explained you the forward and the backward propagation that the weights are randomly initialized. And then when we start training, optimizer in every epoch keeps on adjusting the weight during the back propagation. You remember it? So from random, it goes to best. So everyone's random set of initialization of the weights are different, and therefore everyone's output is different. If I am setting the weight, let's say as 400, one of the weight, let's talk that there is only one weight and one bias. So if I'm setting the weight and the bias as 400 and 200, and you also do the same, then you will also get the same output. But here Our initial weights and biases are different, and hence this issue. Are you understanding what is the reason behind it? Initial adjustments of weights and the biases are different. So the culprit lies over here. So now, first of all, from this code, I'll get the unnecessary things out so that I don't end up running the code again. So here, basically, the problem is when we are starting and creating this, all our weights and biases are randomly initialized. So for same reproducibility, you will have to set the weights and biases to be same. So the way we do that is by setting the random state. So I am setting the seed value. Seed value can be anything, just like the random state parameter of our train test split, which was used for shuffling. This can be any value. So you can give any value. I'm giving the value as 1, 2, 3, 4, 5. I'm importing OS and random. This number, I'm converting it to string, and I'm dumping it into operating system's environment variable. This is not required because we are not using GPU, but if you are using GPU, then it becomes important. So random dot seed set as 1, 2, 3, 4, 5. NumPy's random seed also becomes same. TensorFlow's random seed also becomes same. And now it is done. So I have just set the random seed over here. Now what we will do is you can copy this code which I have shared just above. Just above, you can find this thing in your notebook. Build or instantiate the ANN model. So above this, you add it and then clear outputs, restart and run all. Now I want you to check and let me know, are you getting the same results now like me, 218? And the training and testing, you just if it is tallying, you will just give a thumbs up. Don't type anything in the chat. Just restart the kernel. Don't forget to restart the kernel. Okay, let me look into the results now. So 90 uh, little bit varying, na little bit varying. Misclassification 218 and 263, 241, 215 and okay. If that is the case, let me rerun it. I just reran the notebook and I got 218 again. I got 218 again, and let me see my results. What I got. Let me check. Where is my code here? 97.82. Yeah. See, 99.56. बराबर है. If I run it once again, 11, 12, 13, 14, 15. 97.82, 19. Huh, so it's locked and here 218 only. I'm getting 218 only. You all are getting different things now. Let me save it and actually wait a minute. Let me also actually consider so much bars on the Zoom. I'll create a folder called as temporary. Inside that, I'll upload my notebook and I'll open it. I'm doing it in collab only. That's why I'm doing it in collab. Let me also see. Runtime, change runtime, T4 GPU, connect and run all. Let me see what am I getting in collab. 97. Let me now see where is my result. 97.82. Is there any need to type anything? I didn't ask you anything now. Wait. 97.82. This is 97.94. 99.56, this is this, and the misclassification count 206. And if I run it again, there is some small setting, which has changed, and that is the reason for this. And 206 only. And this results, yeah. So basically, it is locking on a system. I'll tell you what is the reason for this. The reason for this is here the TensorFlow version is 2.19.0 and the same when I am running it on my VS Code, it is 2.19.0. So what is probably different over here is the non-deterministic GPU kernel. So for that, what can I do is I just restarted and run all. I made some small changes, not very sure whether they will work because the GPU is the one which is playing around. 99.56, 97.82 with this new settings. Let me just check it in our collab also. So the results which I have pasted earlier are my VS Code results. So if you can see my VS Code results in the chat box. 99.63 and this is 99.56, 97.94. Yeah, this is not the same, and the total number of misclassifications over here I get is 206, and in my VS Code the total number of misclassifications is 218. So basically, VS Code is not giving the same results as this. And the reason is GPU. So what will I do is, see here, I am saving it. I'm just going to Google Collaboratory. One last try. And here, instead of runtime, I'm changing the runtime to CPU. GPU could be one of the reason for it. And I run all. Yes. So Manu, I hope you got the answer to your question. Now, basically, see, Manu trains his neural network in his system. He gets 98% accuracy. He reports to the client, I get 98% accuracy. Your project gets approved. But in real time, it is giving only 97% accuracy. So Manu got it wrong. But our system configurations are different, your and your client, and because of that, the output is varying. We want a constant output. That's exactly what we are trying to achieve. That is the main reason we dockerize and do all these things, and kind of that's only what I'm trying to achieve. So basically all our libraries and everything should be of the same version. At least my collab and your collab results should match. That's what I think. Right. Okay. So this is what, and see now one last thing. See, I tried running it in collab with CPU and I'm getting this. Huh? No, no. See, you access the one which is there in the temp folder. Access the one which is there in the temp folder. I have made some changes. So, are you getting the same results as mine? The one which is there in the day 4 card temporary folder, using this, are you getting the same results as this notebook? If yes, then we are aligned. 263, yes. If yes, then we are aligned. So basically, the problem is the GPU used by Collab is different than my system, and therefore the things are changing. So if the GPU used by me and my client is the same, I'll be getting the same accuracy. That was the main culprit behind it. So if we both are using GPU, then we still will get the same answer. Basically, the environment must be constant, else the results will change. Minor changes are there, but environment must be constant. I hope that makes it sensible to all of you. Right? Is that now clear to you? Your environment must be constant. Your GPUs must be same. Your framework must be same. The version of the framework should also be the same for the results to come. Then your initial weights which are assigned will be matching. Else it may not match. So I ran it again. I'm still getting 263. That means it is all good. So here. Now the thing is, see everything we did, this was good. And what I wanted to tell you, one important thing I wanted to tell you over here, I said I'll come back and let you know after the break. I actually forgot about it. mm, hey, something I wanted to tell you. Huh. Yes. So now, see, because of this, what happens? Our weight initialization, the weights which are randomly initialized, now they are the same. The weights which are randomly initialized, now they are the same. Right? This is one thing that we realize over here. Now, friends, after this, the next thing that we have over here is that, you know what, friends, look over here. Now I'm going to Google, and if weights are to be initialized randomly, let me tell you that many people invented their own weight initialization techniques. Many people invented their own weight initialization techniques. So, if I go to weight initialization techniques and TensorFlow, and if I open up this, pay attention over here. These are the weight initialization techniques. So there is a person or there is a scientist named as Glorot. He invented his own weight initialization technique called as Glorot normal. Normal because it is going to choose up the random weights, but from the normal distribution. In the same way, in the same way, Glorot has also initialized his Glorot uniform. So you know what? See, I click over here, I go to Chat GPT, I paste this. You are a TensorFlow expert. Tell me the weight initialization formula for Glorot normal and Glorot uniform. Now look at this. Fan in, fan out, all these things will come. So here, see. So basically, you know what they say, that basically what these people said, that use my weight initialization technique, your model will be able to converge faster. There is no guarantee, but they proved on with help of some synthetic data that their weight initialization techniques are better than randomly initialized values. So they said that I will be choosing the weight from the normal distribution using this formula. So all the weights of the neural network would be chosen in the range 0 to 2 upon eta in plus eta out. You know what is eta in plus eta out? Basically, if I'm talking with respect to my neural network, where is that? So if I'm talking with respect to my neural network, which is this one. So over here, see, look at this. In this hidden layer of 128 neurons, can you tell me how many input lines are there? How many input lines are there to this hidden layer? How many input lines are there? Exactly. 128 into 784. And out of this hidden layer, how many output lines are there? How many output lines are there? No, it's not 128. 128 into 64. Yes, 64. See, it's going to 64 neurons. Every neuron is connected to every other neuron, Sandeep. So it is 128 into 164. So listen to me now. So basically, I am telling you that these all lines, the total of these all lines is called as the eta in, and the total number of these all lines is called as the eta out. So for every layer, the number of inputs and the number of outputs is called as eta in and eta out. So now if you see over here, friends, here, see, it says that for every layer, I'll be randomly choosing the weights, but in the range 0 upon 2 plus eta in plus eta out. So how many number of input lines are there plus how many number of output lines are there? So number of inputs and number of outputs. So whatever is the result of this value, between 0 to that, with the mean of 0 and variance of that, we will be randomly choosing the weights. Wasn't this the neuron? What was not the neuron? It was, of course, the neuron, no? But n is not the neurons. N is the number of input units. That is the number of input lines to the neuron. Don't get confused over here. We are clearly talking about the lines. And Glorot also invented his Glorot uniform, or also called as Xavier uniform technique, which uses this formula. So all the weights will be chosen between this range. You need not calculate it. This is just the small mathematics. Are you all clear with me? Again, we are randomly initializing, but in this range, and they say that if you follow this, your chances of reaching the convergence point are relatively faster. कोई guarantee नहीं दे रहा, no one is giving a guarantee. But yes, this is the one. Similarly, see, this is the formula. So I was saying, yes, in our example, this no need to calculate. And in the same way, let us say, hey, normal, okay? In the same way, tell me the formula for. So hey normal is this, and hey uniform is this. So basically, for everything you have a formula. If you go to Google, you will easily be able to find that formula on some blogs or somewhere, or if you go to ChatGPT, you will find it. No one is going to ask you these formulas in your interviews, but you should know that everyone has invented their own technique, and at least one formula you should know that, okay, I remember one of it, and rest of them are more or less similar, and they basically choose. It's important that you mention that we calculate some weights in a certain range, and then the weights are chosen in such a way that the average is 0 and the variance is this. You should be able to tell out this much. This much is expected in the interviews. So now over here, time for us to actually implement it. So here, I'll just ask you the default, right? Which is the default technique used by TensorFlow 2.0 for weight initialization? It is actually nothing but our Glorot only. You see, Glorot uniform is the default technique. So if you don't specify every layer, be it hidden layer or be it output layer, all of them are chosen using this formula, Glorot uniform. हाँ राज, थोड़ा सा रुको बेटा, मुझे सिखाने दो. Your question will be automatically answered. Give me some time. So yes, Glorot uniform is going to be the default technique that we use. So by default, it has used the Glorot uniform without even us letting know. So can we change the technique? Of course, yes. Which technique you want to change? Tell me. Should we go for hey normal, bolo, or Likun normal? Let's go for this. Okay, Likun normal. Let's go. So I'll open this. Look at the process. I'm going to show you the process because I will not be showing you to do this thing or how I do this thing for all. I'll show it for only one. Process remains the same. So if I'm going on Likun normal, I opened it and come down. See over here. It says create an object of Likun normal, and in the hidden layer there is a parameter called as kernel initializer. Set it to this initializer, but we have to import Likun normal. So where is this Likun normal? Here, copy it. I go over here, and then obviously weight initialization is in the neural network, so I'll come here and write it. So I say from TensorFlow dot Keras dot initializer import Likun normal. Then you create an instance of it. It says you create an instance of it like this. Initializer is equal to Likun normal. Any more parameters inside this? No, that is what it is. So I'm creating a Likun normal over here. And then after that, what it says that in the dense layer, use this. So in a dense layer, I'm using this. Now I can also add the same thing here as well. And here as well. Your choice now. See, by default, every layer's kernel initializer was what? What was by default every layer's kernel initializer till the earlier scenario? Glorot uniform. But now everything is hey normal, right? So see now whether this will be helpful or not, I don't know. I don't know. So basically we understand that this is one more hyperparameter that you can try out. So I'll just run all, clear output and run all. So see you got a tick, that means it executed successfully. It's training. See it actually, if you see, it was going up but it is coming down. Let me try training it for more epochs then. So instead of 15, I'm training it for 40 epochs. Now, it didn't help now. So what am I doing is, first of all, I'll go and restore it. Increasing the number of epochs was not a good idea. I run on. Now I would like to tell you that if required, now I'm pretty confident that you can change the weight initialization technique. I don't think so. That's going to be a challenge for any one of us. So weight initialization won't be a challenge at all. Okay. Apart from default, what is the most popular? Uh, See, honestly speaking, most of the people don't do the weight initialization, and it's a good question. So I would say over here, apart from default, this the one which I use, right? Likun normal and Likun uniform are good. Hey normal, hey uniform are good. And yeah, Glorot normal and Glorot uniform. These are the three most popular ones. Rest of them, even I don't ever use it for any of my project. So to say Glorot normal, Glorot uniform, hey normal, hey uniform, Likun normal, Likun uniform. And that, you know why Likun? The Likun I say over here is because Likun is the inventor of the convolutional neural network, which is the next technique that we are going to study. So that's good. There are two variations of glorot. No, it's basically one is a class and one is a function. They are one and the same thing. Why they have mentioned it twice, not very sure, but they are one and the same thing. This is a very interesting concept. This has changed the deep learning a lot. Dropout, a simple way to prevent the neural network from overfitting. So, a very important technique. And did you see this name? This technique was invented by an Indian. A huge round of applause. Dropout was a technique invented by an Indian, Nitish Srivastav. And let me show you who is he. Yes, really nice. Nitish Srivastav, if you go to his LinkedIn profile, right, he is the one in the US, co-founder and CTO at Vayu Robotics, ML for Robotics and Autonomous Systems. He has done his PhD from University of Toronto and he was working at Apple for 5 years. He completed his PhD in February 2017. Right. You see, he has mentioned worked on dropout, Boltzmann machines, sequence to sequence video, transfer learning. Okay. See, PhD completed in 2016. He did his master's also from here. And is he an IITian? Yes, he is a B Tech. So he's obviously a brilliant mind. B Tech IIT Computer Science. Very nice. Acha, meanwhile, can you please help me know who is the godfather of deep learning? Jeffrey Hinton. Array, look into Manu's response. What is Manu saying? Jan LeCun. Did you hear it? This name sometime in the past? Did you hear this name, Jan LeCun, sometime in the past? Yes, just a minute back. The LeCun weight initializer. He only invented it. He is also one of the pioneer of deep learning. So if you look at Jan LeCun, he is the chief scientist at Meta AI, 65 years old. He is the one who invented it. Okay, you know what? This Jan LeCun, listen to this. Jan LeCun is a PhD student of Jeffrey Hinton. जेफरी इंटन के पीएचडी स्टूडेंट है. Yes, and Nitish Srivastav was also a PhD student of Jeffrey Hinton at University of Toronto. So basically, the bright mind, right? Obviously, Nitish Srivastav is very smart, but it was Jeffrey Hinton's brain also in this paper, right? Great minds, and great God, right? So he got Jeffrey Hinton. That in itself was a very good thing. So what is this paper? So we should go for PhD to Toronto and invent dropout also. That is also important. Right. Then it makes sense. No, I am not that smart. I am just an instructor. These are very smart mind, very smart mind. They can actually solve the entire neural network problem using a pen and paper. They know the in and out of it. I I may not be that good, but obviously they are investing day and night in doing the same thing. So if you also start doing it, you will also be able to master it. Okay. So now coming to the thing. See, studying is good. Not studying is bad. Studying is good. Not studying is bad. Over studying is also bad. Do you agree with the third line? Overstudying is also bad. Just imagine. है ना? Yeah, it's like overfitting. Yes, it's like overfitting. You end up ratifying everything. So let's say if you have a exam 3 days after, you are studying today, studying tomorrow, studying day after tomorrow, and then you are going for the examination, but you never slept. So you go to the examination hall and you go to sleep because you were too tired. I repeat, because you were too tired. Since last 3 days, you have been consistently studying and studying, so you were too tired. Just like yesterday, not yesterday, day before yesterday, I slept at 3 a.m. I got free at 10 p.m., but I slept at 3 a.m. Yeah, and just yesterday I slept at 4:20 a.m. And today I actually, the inner fact is today I got up at 8:55 a.m. and 9 a.m. I was with you. So so obviously I was not able to control the sleep. But nine, just wake up and come for your lecture, right? But what am I telling you? Overstudying is bad. Overstudying is bad. Nitish Srivastava actually said the same thing. Now understand the concept. It's based around the same thing. Overstudying is bad. So basically, look over here. What he said is when you have a neural network, you do the forward propagation, send all the images, predict, calculate the loss. Then while the back propagation, optimizer adjusts the loss. And this is the process that you keep on doing again and again, right? So this is the process that you keep on doing again and again and again and again and again. So let's say this forward and backward, instead of drawing the diagram like this, they have drawn it like this. That's okay, na? So let's say this forward and backward propagation happened for 50 times. That means each of these neurons were working during the forward propagation as well as the backward propagation. They didn't get rest, so they got tired. Nitish Srivastava said what? Nitish Srivastava said that Darshan, let's say epoch number one is going on. Huh? Let's say epoch number one is going on, and let's say you have total of 400 neurons. Let's give rest to randomly 100 neurons during the epoch one. Randomly choose any 100. So during the forward and the backward propagation, that 100 will be given the rest. They will not work. Forward and backward propagation done. Then in the second epoch, some other 100 will be given the rest. Done. In the third epoch, some other 100 will be given the rest. This will go on for all the epochs. So basically, every neuron will get some opportunity to rest. Are you understanding the overall concept? Every neuron is getting some opportunity to rest. Or basically, every neuron will not learn in some of the epochs. Let's understand the concept. So here, listen to this. This is the forward propagation. This is the backward propagation. But you know what? We have added over here a dropout layer. We have added over here a dropout layer. We have added over here a dropout layer. This dropout layer is 0.4 probability. This dropout layer is 0.6 and this dropout layer is 0.4. Wait a minute. Can you tell me what is 40% of phi? 2. Correct. So now listen. I am talking about epoch. Let's say epoch 1 is going on. So in epoch 1 you go from here to here. while you are doing that, out of this 5 neurons, 40% of the neurons will be deactivated. It is like in your bedroom, if there are 5 LED lights, you are using only 3 and 2 of them are turned off, which means the button of those 2 are not on, just like this. Similarly, out of these 5 neurons, I have kept the dropout as 60%. You can choose anything. Right now, here they have kept it as 60%. So 60% is 3 neurons off. And here again, dropout is 40%, 2 neurons off. Now, which 2, which 3, and which 2 will be off? Anything. Random. Random. Any neurons can be turned off. So I'm talking about epoch number 1. Let's say this is off. These are off. And these are off. So whichever are off, you see that those lines are also not connected. Ideally, the lines remain, but current will not flow through that. So just to avoid confusion, he has just removed those lines. Are you able to understand the figure for now? Is the figure clear? Yes. So what will happen is now forward propagation will happen in the epoch 1 with all of the available connected lines. You will get the prediction, you will compare it with the actual, and then from this you will compute the loss, and then you do the back propagation. During this back propagation, only the neurons which are active and the lines which you see, only those weights and biases are adjusted, rest of them are not, and that's how your one forward and one backward propagation is over. Epoch 1 comes to an end. Are you all clear with epoch 1? Sandeep, you have a question? I'll explain it once again. Let's understand the first epoch. Now, you understood that we have randomly turned off 40% of neurons from here, 60% from here, 40% from here. We do the forward propagation, and only the connected lines are the weights which are initialized. Using that, you predict, you calculate actual, then you calculate the loss. After loss is calculated, then you get into the back propagation. What happens in the back propagation? Weight adjustment. In the back propagation, weight adjustment happens. Which weights will be adjusted? Only the weights which are connected. So these black lines, these ones, and the biases of this neuron, this neuron, this neuron, this, 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 this. During the back propagation, only the weights and the biases of the connected neurons are adjusted. So basically, whichever neurons are crossed, neither their weights nor their biases are active. So only the available ones are adjusted. That completes the epoch 1. So basically, whichever neurons are crossed, they are relaxing. They are not doing anything during the complete epoch 1. Is that clear to you now, Sandeep and Shweta? During the epoch 1, only the connected lines and the neurons are active. Okay, very good. Then after that, we go on to the second epoch. Now in the second epoch, these dropout values remain the same. 40, 60, 40. They remain the same. So this time, 40% of these 5 neurons will be deactivated, which means any 2 neurons. Which 2 will be deactivated? Any 2. I did say na, any 2 of the neurons will be deactivated. Literally any 2. It can be any 2. It is also possible that it again deactivates these 2 only, or maybe some other 2, or maybe this with some other. But any of the 2 neurons will be deactivated. इन पांचों में से कोई भी 2 न्यूरॉन डिस्कनेक्ट हो जाएंगे. कोई भी. सेम भी हो सकता है, अलग भी हो सकता है. मिक्स भी हो सकता है, बट ये पांचों में से दो न्यूरॉन डीएक्टिवेट होंगे, बिकॉज वी सेड 40% ऑफ द न्यूरॉन्स विल बी डीएक्टिवेटेड, सो आउट ऑफ दिस 5, 2 will be deactivated. Similarly, out of these three, out of these 5, 3 will be deactivated. Similarly, out of these 5, 2 will be deactivated. Whichever are deactivated, those weights and biases are not connected. So we do the forward propagation, we do the backward propagation, and only the connected lines, weights and biases are adjusted. Then we go on to the third epoch, and so on and so forth. Let's say if we are training it for 15 epoch, the same thing will happen. So basically, during each epoch, some neurons are getting time to rest. In this scenario, I can say during each epoch, 2 plus 3, 5 plus 2, 7. 7 neurons are getting rest during each epoch. Correct? During each epoch, 7 neurons are getting rest. Any 7, but 7 are getting rest. So basically, our entire brain is not getting used. Some random part of the brain is getting rest, and other is getting used. Then after that for next epoch, some other random part of the brain is getting used. Some neurons are getting rest. So your brain is getting time to sleep, or neurons in the brain are getting time to sleep. So basically, that is avoiding the network to get tired or overlearn the things. Or I can say, too frequent weight updation is also a problem. Too much frequent bias updation is also a problem. So this is kind of a way to control that. Looks like this will result in loss of data, but actually it turns out to be very helpful. Are you understanding the overall technique? Will reducing the number of very good question. I was just waiting for someone to ask this question. See, Parul, let's say, very very good question. Like, every time someone asks it. Let's say I'm assuming over here, Parul, let's assume over here that we have uh, 5, 10, 15, 16. So, Parul, we have 16 neurons over here, and out of 16, how many are getting rest? 2, 3, 4, 5, 6, 7. 7 are getting rest. Agree to this, Parul? In every epoch, out of 16, 7 are getting rest. Right? Now, instead of that, what Parul is suggesting, that let's say, Darshan, if we are having a neural network which has 7 neurons only, and we don't apply dropout, basically none of them are getting rest. So that means, Parul, all the 7 neurons are used in the forward and the backward propagation. So let's say if this forward and backward propagation, Parul is doing it for 100 times, then Parul, all the 7 neurons are going to get tired in all the 100 epochs. So they are not getting rest. This is the smaller network, whereas this is the bigger network where some of the neurons are getting rest. That's how the concept is different. So you are using a powerful brain but giving rest to few of the neurons. And here you are using a small brain. So this is like the brain of a child, and you are exerting him a lot. This is a brain of an adult, but you are giving rest to some of the parts. That is how dropout is different. Getting the difference? Very nice. Very important question. Huh? What it about making the neural network uncomfortable? It is not having any emotion, Amitoj. It's like, I actually remember my college days when people used to say, don't make a girl uncomfortable. So it is about making a neural network uncomfortable so that it does not memorize by training the data. Ideally, yes, that's exactly what I have been saying so long. That's exactly what I have been telling it since last 10 minutes. You have to give rest to some of the neurons so that they don't memorize the thing. They don't overfit on the data. They don't learn the data as it is or mug up the data, but rather they get some time to rest. That's the idea. Is that clear, Amitosh? Actually, for a moment, you took me back to my college days. When the rest is not given, can we assume that it will? See, Sandeep, and all of you, if you overthink about it, you will never ever able to survive in deep learning. This is one way of handling overfitting. There is no guarantee. There is no guarantee here also. I said it will handle. Maybe at times, based on some business problem, it doesn't. So whether it will impact or not, who am I to say? I am no one to say that. It depends on the business problem. But it is one of the technique. You tell me. I told you that if you are increasing the neurons in the power of 2 raised to n, or you decrease the neurons in the power of 2 raised to n, your chances of reaching a good solution are higher. And here I actually did the same thing. I decrease it in the power of 2 raised to n. Kya fayda hua? What is the use of it? My network is still overfitting. There is no guarantee anywhere. There is no guarantee anywhere, Sandeep. So you don't democratize each and every concept that okay, Darshan sir said it, so this is only what will happen. Nothing. Nothing like that. Anything can happen. But what am I saying? The chances of that to happen are relatively higher. That's the only conclusion. Right? So what you are saying may also happen. No guarantee. But my concept is likely to give you little more confidence. So when you are overfitting, try using that. Maybe your problem is solved. Exactly. Like in exam, if you know that chapter 1, 2, and 3 is going to contribute to 80% of the syllabus, and chapter 4 and 5 is only going to contribute to 20%. So you decide that no, I will only study chapter 1, 2, and 3, and I'll skip the other two. It's just like being smart. That's it. One more question. Won't less neurons mean more epoch needed? No, absolutely not. There is no guarantee, guys. I don't understand. What is the problem with you, Rao? You are you are trying to memorize a neural network. Amit and Sandeep, you are actually trying to memorize a neural network, but this is not the scenario. In real life, there is no guarantee. So, less neurons means more epochs? No. In fact, let me, let us go and ask the chat GPT. So let's say I'll confirm you, right? You are a neural network expert in TensorFlow with 20 years of industry experience. If a neural network is overfitting and if I use dropout, then in that case, dropout randomly disables a fraction of neurons, right? So this is the first question. When the rest is not given, can we assume that this will impact the validation loss? So you can assume that the dropout, when tuned correctly, helps to decrease the validation loss and this. The rest you mentioned, actually rest means it actually took the term rest. That's wrong actually because of me only. So when you when uh, some neurons are deactivated, disabled, right? So during training, dropout only disables this. This prevents the co-adaptation of neurons and makes the network more robust. So during inference, this is not applied. TensorFlow scales this. So yes, does it help in reduce overfitting? Yes. Which means validation loss tends to decrease, less overfitting. That's what I told you. Validation accuracy also improves. So in short, adding dropout can make the validation metric look a bit noisy, but over enough epochs, it stabilizes. Do fewer neurons means more epochs are needed? It says with dropout, fewer neurons are active per batch. This does slow the conversion somewhat since the capacity per training step is reduced. In practice, you may need more epochs or higher learning rate to start reaching the same training performance. But the extra training time is worth it because final model generalizes better. A well-tuned dropout rate, which is, this is one point I wanted to tell you, 0.2 to 0.5 is a common value, gives you better thing. Industry takeaway, dropout makes training slower, but more generalizable. That means overfitting reduces because the model is able to do good on the unseen data. You will often trade a bit of training efficiency for a much better validation performance. If the training is too slow with dropout, alternatives include weight decay, data augmentation, which is the next topic, early stopping. So, coming out over here. Now, how do you add a dropout? Very simple, very simple. So, dropout is also one of the layer. And dropout can be added anywhere. So let's say after this flatten only, I can actually add a dropout layer. And then after this, so it's not mandatory that you add it everywhere. And if you want, you can add it also. So let's say here I'm keeping 0.2, here I'm keeping 0.4, and then again I'm keeping 0.2. Is there any perfect value to that? No, but usually 0.2 to 0.5 is what you should play into. See, this is the earlier one. This is the earlier one. Accuracy and loss. So let's see what we get because of dropout. This is the old one, which I just shared in the chat box. And I'm eagerly waiting for a new one.
Wanted a few minutes on the Keras tuner. I will do it. This is not the right time for Keras tuner because see, we have to also understand advanced network like convolutional neural network. So once that topic is over, then going for Keras tuner is going to make more sense. So I'll be taking it at that time, right? Uh, don't worry, cool. And I think by that time, even you, I'm pretty sure, I'm confident that you also might be able to figure out your concern. So, but yeah, we will be doing that. It's just that Keras Tuner has received an update. I think essentially, I don't exactly recollect, a little confused. Either Keras Tuner is deprecated or it only works in the latest version. One of it is true. One of it is true. I'm not very sure. Either it is deprecated and no longer available. I think this is what I'm more strongly confident about. And the second thing is maybe it works only with a specific version. So you have to install that version of TensorFlow. So I think you might be having issues like that. Right. So one of it is, so we'll have to figure it out. But anyways, I think I already have that mentioned in my notebook. We'll talk about it later. So my advice is whenever there is some such change of version or anything, it is advisable we either, it is advisable that we either go for doing that exercise in Google Collaboratory. That is one thing which I highly recommend. Why to change our original setup in the VS Code or to create a virtual environment and achieve that task. Okay. Yeah. So and by the way, you can also do grid search CV inside the neural network. So I can just given this deep learning expert. I want to apply grid search CV algorithm on the MNIST data set to be done using a artificial neural network. So grid search CV can also be conveniently applied. Yes. You can see over here, MLP hidden layers. Mhm. I would prefer to go ahead with the implementation with TensorFlow and the library TensorFlow for downloading the MNIST dataset. The implementation which I want you to follow is little different. So model hidden layer, hidden units, hidden layers. So here if you see, right, the number of units to be tried out, 256 neurons, 512 neurons, hidden layer 1, 2, dropout I have given, optimizer and all these things. So here in grid search CV, estimator is equal to CLF. So CLF is nothing but the Keras classifier. And the model is build model, which is created over here. So here we'll be passing the parameters as and when we go ahead. So first sequential, then input, and then I'll be going through hidden layers. And inside that, I'll be going through the addition of the hidden layers. So first hidden layer which will be added will be of 128 neurons, right? 256. Then 512. Then after that, if dropout is there, we will also add dropout. So basically, I'll show you because it's a interesting one. I'll show you the architecture properly, and let's do it inside this only. Plus grid search CV. Let me look into the shape. No problem. So no, it's fine. It's something which is relevant. I think grid search CV, I can show it to you. It can be applied on this data set. And the code is anyways available, so it won't take a lot of time, Manu. So we'll just do it quickly. That's completely fine. Now everyone see, as usual, we have loaded the MNIST dataset. Okay, there is nothing new over here. MNIST dataset is perfectly loaded, and I don't wish to explain any of this code over here because you know it in and out. Then, I don't know why is it giving this. I already have an implementation of it, but I was little optimistic on this implementation which ChatGPT shared. Actually, I was expecting only grid search CV. Anyway, the grid search CV, randomized search CV, that's not a problem, Manu. That's okay. Actually, I should revise my prompt. I'll say avoid using this one, Keras. Where is that gone? Just use the normal ANN along with grid search CV with the help of a user-defined function like build model. And I am actually restarting the session. No, we can actually use the user-defined function to have method parameters like def build model, and then we say hidden layers is equal to h underscore 1 underscore 2 underscore 3 comma, then split the on underscore and build a network in that way for every layer.
I was not expecting it to take so long. You know, it's a very common practice. I'll show you. Mhm. No, it's not working good. So I'll take it later only because it is investing a lot of time, but I'll show you. It's practically very conveniently possible. Mhm. What was we? Hmm. Have a look at this. I told you, no, I'll be doing it specifically during the convolutional neural network time. Yeah, so this is a basic model which I created. If you see sequential, then input, then convolution, which I have not yet taught, convolution pooling, but this is what you know. Flatten, dense, dense. This is what we all know. But what I did after this, so this is the approach which I was talking about, which, this is like the grid search CV. So what am I going to do is, I'm going to give the layer configuration C underscore 2 underscore 3 underscore 121 and this, and D is for the dense layer. So what it will do is it will basically take up these values one by one. So this is the layers config. So when I say for layer in layer config, it is going to go through this one by one. So first time I say for layer in layer config, so it will be going through this first. So for C in this, because obviously there is a thing, so if C is available inside this, then I say split or underscore. So after this is splitted or underscore, it becomes like this. So it is going to add a layer of convolution, as you can see over here, with the parameters kernel size available in config of 2. Sorry, filters available in config of 1. So this is 0, this is 1. Index 1 is 2. So this number will be 2. Then kernel size will be config of 2. That will be 3. Strides will be config of 3. That will be 1. Pooling will be config of 4. That will be fetching this number. Strides will be config of this, fetching this number, and so on. So let's give one more shot. So I say I want to do the hyperparameter tuning on the MNIST dataset using the TensorFlow library. The hyperparameter tuning has to be done using the below style, but do not use CNN. We will be using the dataset which is downloaded directly from the TensorFlow library. Generate the updated code. We'll just invest around 2-3 more minutes. If not, we will go ahead. I think it should be done now. No, actually, it's not good. I think let us skip this. It's actually not good. We'll talk about it later. I will get a perfect implementation of it and then we will talk rather than unnecessary investing time on it. Let's ignore this. I will save this notebook and yeah, this is good, I would say. And the remaining things, we will start on it as and when we go ahead with the later part of the things. So for now, we completed with our artificial neural network for the MNIST dataset. And then now today actually we get started with the um, mm, we didn't did I give you a task for fashion MNIST dataset? I think I did not give it. And I actually want to show you one more problem. And that is what I'll be doing it very fast. And I'll show you why it fails. And then we will be getting into understanding the next advanced architecture called as convolutional neural network. So I repeat, everyone, Now I'm implementing, or basically I'm going to show you that how machine learning was not very powerful and deep learning solved the problem. Specifically, artificial neural network solved the problem which machine learning was having, and it gave us very good results just by going for deep learning instead of machine learning. Now I will show you what is the drawback of this artificial neural network, how it fails, and how advanced architecture like convolutional neural network. See, today we are going to learn this advanced architecture called as convolutional neural network. You know what does this architecture do? See, listen to me very, very carefully. In a single minute explanation, which will take around 2 hours for me to explain this architecture, but in a single minute explanation, I want to tell you all that this particular architecture is not going to work like an idiot that we have been working so far. Why I say we have been working like an idiot is because if you recollect our earlier one, if you look into our notebook, right? Specifically, let's look into this notebook. So, see, in our cat versus dog classifier example that we had seen, I assumed every image to be of size 3 cross 3, as you can see over here. And looking into this 3 cross 3 image, when you flatten it, you know it very well that it will, when flattened, right, when this 2 cross 2 is flattened, it becomes 1, 2, 3, 4, 4 pixels. So obviously when this 3 cross 3 image, each of this 3 cross 3 image, we have 1000 images, image 0, 1, 2, 3 up to 999. When each image is flattened, it will have 9 pixel values. Are you aware of this? I hope you recollect this, yes or no, right? So now let me talk about the stupid thing that we are doing or we were doing. The most stupid or the idiotic thing that we were doing over here is what are we doing essentially? If you see over here, हम क्या कर रहे थे? We were ideally asking the neural network to understand the relationship between this side and this side. Next time, we were asking it to understand the relationship between this side and this side. Then, relationship between this side and this side. Then, relationship so on and so forth. Let's say if I'm only talking about training data set, then it was between this side and this side. Right, this is what we had been doing. Now, what is the problem in this approach, Darshan? There is a big problem. See, tell me, as a human being, forget about this neural network. As a human being, if our course is over today, and if you see me after 6 months somewhere on the street, how do you recognize it is me only? How does your brain recognize, oh, this is Dr. Darshan who taught us? How? In a logical way, no technical explanation. How do you figure out, oh, this is Darshan? I have seen it. I have seen him. He has taught us deep learning and this memory. Okay. And what is exactly in your memory? So what is your memory storing? Recognizing the image, recognizing the picture. So what do you recognize in my picture then? When you see me after 6 months somewhere on the road, what do you recognize in my picture? Shape,
pattern, facial characteristics, skin tone, absolutely. So now you are actually coming to the crux of it. Yes, you recognize so-called features. Features in a very simple way. You are recognizing features. And based on the features you are, so your brain, when your brain looks at me today as well, your brain has kind of extracted features from my face, and the features from my face are saved here. The features from my face are saved here. So what can be the features from my face? Example, some of you have already written it, but what can be the features from my face? Eyes, okay. Specifically right eye, left eye. You never know, my left eye is squinted. Nose, shape, eyes, and length, okay. Then hair, eyebrows, yes. Any marks, very good. Skin color, forehead, okay. And face cut, lips, beard, yes. And what can be more features? Jawline, yes. And ears, okay. Troubling you little more. Chin, voice, okay. Goals, yes, agreed. And what can be some more features? That's okay, Nishan. Body, no, I'm only looking at the facial features for now. Double chin, okay. Fat on the face, oh my God. Okay. Size and shape of all mentioned. Hairs, haha. I That's good. 90% through. Eyebrows, yes. 90% through. I'm just expecting one or two more few points. Hairstyle, okay. The last 10% you are missing. What more do you extract from a face? Teeth, okay. Go little deeper. Now you are looking at all the high level features. Eyes, nose, hair, eyebrows. Go more deeper. Pupil color, okay. Total head. No, go more deeper. You are going outer. I want you to go inner. Edges, okay, that's good. Edges, expression, and go more deeper. When you are at a distance of just 5 centimeter from my face, I'm sure you will not be able to see my face when you are just at a distance of 5 centimeter from my face. But what will you see? Wrinkles. Yes, wrinkles on my face. And now tell me such low level features. What more do you see when you are very, very near to the face? One is wrinkle, pores, mole, pimple, smell. Shanu. Facial features, pimples. And yes, you nailed it now. Now we are we are good with this. Now, friends, are we doing something like that in this scenario between the independent and the dependent variable? Are we doing the understanding of the features with respect to the label? No. Here, Here in between this red box and the pink box, honestly speaking, we have been working on it like an idiot.
We have been working on it like an idiot. What were we doing or what are we doing? We are just trying to understand the relationship in between the pixel values versus the dependent variable. Pixel values, which is the dependent variable. Pixel values versus the dependent variable. Till the last one. So we all know how the things have been working over here. We all know how the things have been working over here. Right. We all know how the things have been working. So basically, that was a very idiotic approach, to be very honest, understanding the relationship between this and this. And that is the reason our neural network technique that we have been using so far is ideally not a great technique. This is the reason it is not a great technique, because you are simply, you are simply understanding the relationship between the pixel numbers only, right? They are pixel numbers versus the label, pixel number label, so on and so forth. And that is why it doesn't turn out to be that powerful. You know what should we ideally do? Ideally, instead of here, we having pixel 1, 2, 3, 4, 5, 6 up to 9. Logically, this must be a feature related to, this pixel 1, it should not be pixel 1, 2, 3. It will be feature 1, feature 2, feature 3, where this should be feature 1. Let's say this is how the nose of a cat looks like, because we're in a cat versus dog classifier. How does the nose of a cat look like? How does the nose of a dog look like? How does the nose of a dog look like? And so on. This can be, how does lips of the cat look like? How does the fur of the cat look like? And in this way, instead of having just 9 features, you can extract 900 features. And our next architecture, convolutional neural network, focuses on exactly that. We will not be applying artificial neural network directly, but before that, we will be extracting features and then we will apply the artificial neural network. So here, if you see, right. So now here, have a look at it. The same thing I want to show you. So if you recall, this part is our normal artificial neural network. If you remember, we were creating an input layer. Till the previous session, we were doing the same approach. We were creating an input layer. And after creating an input layer, we were flattening it, then hidden layer or hidden layers, and then the output layer. But now, if you see, I have added after the input layer a convolutional neural network layer. So here, if you carefully see, here, what am I saying? I'm asking convolutional neural network to extract 32 features. And then this pooling has some significance right now. Let's not discuss into that. I'll be talking about the architecture. At that time, we'll discuss all of this thing. But let's say, this convolution and pooling go hand in hand. So I apply convolution. I ask it to extract 32 features from every image and then do pooling. Then I again ask the convolution to extract 64 features from this image, then do pooling. So total features extracted from every image are 32 plus 64. And these features are then flattened and then you give it to the hidden layer 1 and then you give it to the output layer. So this is a very smart and an intelligent move that we are going to understand. Very smart and intelligent move. Now, before I start with the architecture, I just want a heads up uh, from you. Did you understand have you understood what are we going to study in the convolutional neural network architecture, which is there in the blue box?
These two lines, this for understanding these two lines, we are going to invest 2 hours of our time. Yes. The code is super simple. Are you all clear with this? What is the thing that we are going to learn in our today's class? Right? Rather than understanding pixel relationships, how to extract features. Yes, how to extract features and give that feature further to the artificial neural network. Rather than giving the flattened pixel values, you extract 32 plus 64 features or more than that, and then flatten it, and then you give it to the hidden layer 1 and then to the output layer. This is the thing that we are going to study in our session. Okay. But is that even required? Because I think last time also when we tried out, we were getting really fantastic accuracy. So let us check it out. So here, I am talking about a new data set. I don't remember if I discussed it earlier or not. So I would like to hear it from you only. That did we ever discuss about the fashion MNIST data set earlier? How come some of you are saying yes and some of you are saying no? That's a little confusing for me. Acha, okay. I remember. I just showed you deployment part of it, if I'm not wrong. Am I correct? But I just demonstrated the deployment part, but I didn't work on this data set. I get it. Right. Now I remember it. Thank you very much. So, friends, now see, MNIST data set was considered to be too easy. So, they came up long time back with the fashion MNIST data set. So, what is fashion MNIST data set? It's not digits like 0, 1, 2, 3 in the images, but here rather you have actual images. And these are again black and white. In We'll be moving on to the color images in the next use case. We will start properly from the basics. So here, these are all black and white images. So I'm going to the VS Code, the problem statement. So fashion MNIST dataset, as we all understand, it's again a dataset consisting of 70,000 images of 10 different categories, as you see. And this is what we are trying to understand. So it is the time for us to import the TensorFlow library. Let me load the fashion MNIST dataset where I say we have already imported TensorFlow. So fashion MNIST is equal to tf.keras.datasets.fashionMNIST, and we have loaded it, and then xtrain, ytrain, xtest, ytest, and I'm going to print the shapes of the training and the testing data. As you can see over here, and once it is printed, I can just randomly copy the code now. So if I look into any image, it will by default be having the shape 28 cross 28. It's just that it is black and white. And just to look into the zeroth, it's so see, what is the zeroth image? The zeroth image is 9. What is 9? So you will have to go over here and see, okay, it is ankle boot.
if I say what is y train of second image, or let's say what is y train of 230-second image. So the 230-second image is 6. What is 6? It is short. I don't have time to do all these mappings. So I am going to create a list of the labels, and I will say what is labels of 232. So I get it properly. What is uh, labels of 0? You see, it's ankle boot. So rather than going for it, I'm gonna take this approach. Are you clear with it? How quickly I'm able to access this rather than printing 0, 9 and then going to this image and mapping. I'm gonna follow a little smarter approach. Are you all with me? Did you understand what I did right now? This is important, huh? Yeah, this is important. We'll be using it towards the end as well. Right. Acha, you can also keep this image open. Okay. So now what I want to do, I want to plot the 0th image. So here I see plt.im show 0th image CMAP is equal to gray, and while in the title, in the title I have said label is something, and what is that something? I put in format labels of y train of 0, and plt.figure pic size is equal to 3 cross 3. So you see over here, this is the image and that is about ankle boot. If I have to go for 110th image, then this is about bag. In the same way, if I have to plot the 110th image of the test data, only this part would change and this part will change. And this is a pullover. Fine, chalo, we understand it. Then the next thing that we do is we normalize the images. I can take it from here only. So that code does not change. So I normalize it. I'll get rid of all these things because we know it very well now. Okay. And after normalizing, I'll try to print one random image. And we can see that we get it over here, pull over. That means everything is good. After that, what is the next thing that we do? We set up the seed values so that all of us get the same result. So this is what I'm doing it over here. Then I actually build or instantiate the artificial neural network. So can I go for the same artificial neural network? Yes, of course I can go. I'll not set the things and all. Question is diving, but 255. Good practice or acha, dividing. Dividing by 255, is it a good practice or can we use min-max scalar? See, ultimately, you use a min-max scalar or you divide by 255, it is one and the same, Sandeep. So one of the very standard practice which is followed in images across is dividing by 255 instead of going for min-max scalar because it is really fast. Min-max scalar does not have any drawback as such, but see, first of all, understand the thing. Sandeep, the complexity would be more if you think of applying the min-max scalar because first, ideally, you have it in the form of image. So first you will have to flatten it and then after that you apply the min-max scalar. But in deep learning, we already have the flattened layer and we are able to do the scaling before that only. So it is more convenient to divide by 255 and then apply the flatten as compared to flattening and doing it later, right? So first you flatten it, then you apply min-max scalar and then here you have to take care of all these things. This is a more uh, popular approach as compared to the older one. So it is highly recommended that we use this instead of the earlier one. I hope that makes sense. Perfect. Welcome. So what am I doing? I'm not doing any great changes. This is the same neural network. You can see I'm copying it from the notebook ANN MNIST image classification. This code I copied and I pasted in this fashion MNIST. So we are having a sequential layer. Then we are adding input, then flatten 128 and 64. Okay. Then after that, I'm going to compile the model. Model.compile. Optimizer is Adam. Loss is sparse categorical cross entropy. Metric is accuracy. Model accuracy, as you saw, this is what we have. We have 1,09,386 parameters. Then I'm training the model. Well, by the time this is getting trained, let us look at what we got earlier in 15 epochs. So earlier in 15 epochs, what you got is also there in the chat box. I'm getting 99% accuracy and 97.5% accuracy on the MNIST dataset. What about this fashion MNIST? More or less same images. You see over here, the accuracy became 92.79 and the validation accuracy became 87.43. So, no, it decreased, not increased. The earlier one was MNIST and the latest message is fashion MNIST. So ideally, accuracy decreased from 99% to 92%. And validation accuracy, yes, validation accuracy, no problem, but understanding, right? It was 97%, now it is 87%. So do you all now agree that if you compare the MNIST data set with the fashion MNIST data set, do you agree to the fact that fashion MNIST data set is a even more difficult data as compared to the MNIST data? Does that make sense that fashion MNIST is a more difficult data set to work upon as compared to MNIST? With the same network, you see it is not able to do the things as good as required. Plus, if you see, the model is just good. By just good, I mean to say that if this validation accuracy goes little lower, it's gonna overfit because this is the value 92.79. See? In fact, it is actually overfitting because the difference between train and test is more than 5%. Do you see that? The difference between train and test accuracy is more than 5%. So it is actually overfitting. I was saying it is about to overfit, but the fact is it is actually overfitting. Oh my God. Okay. Let us plot this. This is what you see. Oh, ho, 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 ho. You actually see it's overfitting, right? Bad, 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 really bad. Okay. Accuracy. You can see that the scope for the training accuracy to increase, but the testing accuracy has become stable. So, to evaluate it, I can see that and checking for overfitting conditions. If number one, the test accuracy must be at least 80% and train accuracy minus test accuracy should be less than 5%. So here we can see over here, we have the train accuracy and the test accuracy 87 and 91.43. So this is 3.9. So it has taken the best value from this. And this is what we have got. So model is not overfitting. This is what we understand. But you also see the difference, right? So model is not overfitting. And I will, yes, percentage difference is what I will print. And I will also print the training and testing accuracy. In fact, this is what let us print in all the cases. Yeah. So that's perfect. So we see the difference, percentage difference. We see the train accuracy, test accuracy. In fact, the percentage difference is better if we print it later. Control X. Yeah. Train accuracy, test accuracy, percentage difference. And you see over here, the model is not overfitting. Yeah, I just printed it just to be on a safer side. And then I go ahead and I will straight away ask it to do the Y prediction. This is exactly the same thing. And okay, Y prediction is not defined because we didn't do that earlier. So, right. So that's perfect, 10,000 rows. And we got the shape of it. Plotting the confusion matrix. And okay. From sklearn.metrics. Perfect. And hey, why do I see a duplicate label? It's already there. I don't know. Nowadays, Copilot doesn't work as good as expected with this recent update. I don't actually see it working good. Hannah, it slowed down. No? You also noticed it, right? Even I'm noticing it in last 10-15 days. Yes. And this is not the expected performance. In fact, it doesn't even recommend. If I don't even think it has slowed down, I think it doesn't recommend. It's not that great. So, see, now it's forget about slowing down. It is not even recommending. From sklearn dot cursor is good in this case. See, absolutely no recommendation. I don't know what I was doing. Okay. It feels like I unnecessarily deleted the code. Give me a moment. Yeah, sklearn. Sorry. Yeah, whatever it is, but see, it is not even able to go ahead with it. This is bad. And here, that's fine. But see, it should work seamlessly, right? As simple as that. I mean, it doesn't. Performance is not great. So restarting VS uh is like training it once again. No, practically doesn't make sense. Okay. Then after that also you see there is absolutely no progress. In creating a plot of this, we have the confusion matrix. We import Cbon, heat map. Yeah, X-Tix, Y-Tix labels. predicted and true. Yeah, now it's perfect. And title. And PLT dots. I think 10 cross 10 is too big. Yes. So if you all observe, which is the highest number of misclassification? It's the same problem. Which is the highest number of misclassification? First you tell me the number, na? What is the number? 207, yes. And 207 is a quote. Okay. Quote is the biggest number of misclassification. This is what we see. And actually not quote, actually quote getting confused as pullover. Okay. And the next highest number looks like, from the color darkness. Yes, 158, right? Shirt and t-shirt use confusion. Perfect. Coat versus pullover, shirt versus t-shirt. And then shirt versus pullover is another confusion. Then t-shirt versus shirt. Then I also see pullover versus shirt. I also see coat versus shirt and so on. Okay, fine. This is very similar to what we have seen. Now, again, I'm finding out the total number of misclassified images. There are 1200 misclassified images over here, and in the previous one, it was only 225. You understand the difference, right? Here it was 225, and here it is 1275. So the error rate is 12%. The error rate is 12.57%. Earlier, the error rate was 2.25. So the error increased by 10%, which means it has definitely concluded itself as a difficult problem. And then I would like to, with actual and predicted labels. So here, title, predicted and actual given. And you see over here, true is dress predicted as a shirt or a top. In fact, actual is dress and predicted as this. Okay, now it's time for you. You already have this image. I had shared with you all this image. You can keep it open. And time for you to go ahead with it. Yeah. What do you think it is? It's a difficult problem. I just want to see whether we as humans are able to predict it. So what according to you it is? You can refer the image shared in the chat box and give your opinion. Okay, Anivesh says quote. Long quote is not even there in the target variable, Manu. What is the point in sharing that image with you? If you recollect, this image is shared with you, right? Right now in the chat box, the link of that. Where is the long dress? Coat, pullover, dress. Let us see actually what is there.
Dress. Oh, it's a dress. And those of you predicted coat, sorry guys, but you are overfitting. Let's try it again. Yeah, now. Shirt, pullover, shirt. Many people are saying it's shirt and pullover as well. Oh, it's a shirt. It's a shirt. So we clearly understand that you all are not as accurate as you were during the MNIST image when I gave you. Over there, you were far more accurate, which means this is certainly by default a difficult problem. This one, dress. Many of you are saying it's stress. Short, okay. So we have some challenges over here. Let us see it. Oh, it's a dress. Congratulations. It's a t-shirt predicted as pullover. What do you think it is? I'm actually looking for some other images as well. It's a t-shirt. T-shirt. All with t-shirt. Even I think it's a t-shirt or a top. And yeah, that's awesome. That's perfect. I'm actually bored with these images. Yeah, what do you think it is? Tell only the classes which are available. Sneakers. There is no shoes over here. Don't tell me anything which is irrelevant. Shoes है ही नहीं तो कहाँ से देख रहे हो? I have shared that image with you all. Sneakers, right? Yeah, it's quite evident, and it has predicted it as a sandal. I don't want this. I don't want this. I don't want this. Yeah, see, this is the dress predicted as a trouser. I don't want this. Yes. Tell me what is this? Yeah, this is quite straightforward. You see, it's dress, and it's actually a dress. And now, see, I did it. Now, what am I doing is to convince you that it's not a that easy problem as you are thinking about. I want you to turn on your GPU and check out on this problem. Are you able to get a good model just like MNIST? It's there in the drive, and you already have the link to the drive. So I want you to check on this and tell me if you are able to get a model better than what I have got. Something which is really very good. And reply me over the chat box if you are able to get good, so that we are good to get started with the convolutional neural network, which makes you convincing why are we actually going for CNN. And I'll be just back in 2 minutes using the washroom. Meanwhile, you try it and let me know your results. A good model. Try doing the hyperparameter tuning. This is not official breakup. Okay. 87% and difference is 4. Okay. And then before that, Rahul has also shared 87 and 3.65%. 87 and 3.94%. This is what Nishant is saying. But anyone getting a test accuracy around 92, 93 at least? Because earlier we had 97%. I think at least 95% is something that we should aim to achieve. The test accuracy has 95%. Are you able to get it? It should 15 epochs. No problem. That also you can change. You can you can change epochs, you can change the hyperparameters, now add more hidden layers. You can add dropout. Are you trying adding dropout? Try adding dropout. And just remind me, did I talk about the early stopping last time? Yeah, I think yes. I did talk about the early stopping, right? Try increasing the number of epochs to around 50 and try early stopping as well. See what works. So 45 epochs. Can you share that overfitting wala result, Anivesh? Rather than sharing this, because that will perfectly give us the right result. The results of model.evaluate, the one which we actually got here, this cell's result. This is more accurate because it will pick up the best training and the testing accuracy. Anivesh and Aditya, could you do this, please? Okay, no problem. Share the latest result. That's fine. That's fine. So I'll just go through it. Yeah, sure, no problem. So here what you got, let me just check. 90 and 88. Okay, it was 88. And here also for Anivesh also it was 97 and 88. Okay. 2 minutes more. And then we move ahead with the introduction to CNN. Okay. 87. Okay, Prashil, noted. So model is not overfitting. That's good. But it is not giving that great results on the test data set. And this is one of the biggest drawback which I wanted you all to realize. You try one or two more iterations and try to make it awesome. And tell me if you are able to get somehow. I don't. Let's forget that target of 95%. At least are we able to get a test accuracy of 90%? Try out for that. Another 2 minutes, and then we move ahead when you get convinced. So, yeah, you try it out. I'll just be back. Earlier, actually, I went to the washroom, but surprisingly, all the 3 washrooms were occupied. I just wanted to go and have a short biological break. So, just give me 1-2 minutes. I'll be back. Meanwhile, I want to see your updated results. 91 and 87.5. Raj, it would be great if you share the results for this cell, right? This one. And now we are completely convinced. We are completely convinced that if you recall your artificial neural network, okay, Raj also got 88. I get it, Raj. So now we all are completely convinced that in artificial neural network for our MNIST,
when you had a image 28 cross 28, you flatten it to make a vector of 784, comma. So your data set ultimately was like this, where you had independent variable 1 to independent variable 784. This was going from 0 to 69999, and this was going from 0 to this. This was your train test, and your model was fitting over X train, Y train. So over here, what you do is when I say you are ideally fit over X train, Y train, here we understand relationship between pixel values and numbers. Ideally, it must be relationship between features and labels. In fact, here also earlier I wanted to write labels only. I just realized I wrote it numbers. So pixel values should ideally be this. And let me tell you that CNN actually does, or I can say CNN actually makes this possible. That is something very interesting to be seen about it. How? Let's unwrap it. So now, let's understand. About me? No, that is just a standard slide. So, but anyways, I'll update it. This is 16 there, and let me say, tell you that this is quite old, but that's okay. Then over here. A convolutional neural network is a neural network which has convolution. So it means that if you want to really understand CNN, you must first understand what is convolution. So let's get into this. At a high level, this is how the figure for convolution works like. So starting with the very first thing, is convolution mysterious? The answer is absolutely not at all. First of all, stop treating this as something like a mysterious thing, which most of the people do. See, but as per our discussion, right from machine learning, I want to take the dumb as possible approach. Definitely, convolution can be complex because it is one of the very uh, central operation in the signal processing and computer vision, but in fact, it's quite simple. There are only two requirements. Can you do the addition? Can you do the multiplication? If this is what you can do, then you can understand convolution. So let me ask it to the class that are you aware of these two things? Addition and multiplication? Yes. Then to you understand convolution really very, very easily. Then you really understand it's very easily. If you're not clear with this concept, then you will have to go back and revise it. What is plus? This plus basically, you need to understand how to do this and you need to understand how to do this. If you don't know that, you can go and revise it. Else you will not be a right candidate to understand convolution. Okay. Now, let's first try to understand convolution without mathematics. Just qualitatively by examples. Have a look at this. I have a image, let's say, a image which I am planning to upload on Instagram. And on that image, I am applying a filter, which is also called as kernel, right? Technically, that filter is also called as kernel. And the output after applying the image looks like this. So could you please elaborate in one single word what was the effect of applying this? When you compare the input with the output, what was the effect of applying this? Blur? Awesome. Yes, I am 100% convinced with you. This is called blurring. Wow, you're understanding convolution through examples. Have a look at one more. I have an input image and I have a filter or a kernel, which ideally in real life looks like this. By the way, a little bit of mathematical understanding, which I'll talk about later. But in fact, this filter or kernel in real life, these are nothing but the weights of the CNN. How we will understand it after 1 hour. But remember this, these are nothing but the weights of the CNN. So network is going to learn that. No one knows it. But anyways, if you now compare the input image with the output image, can you tell me in single word what has happened once again? This is definitely not blurring. So what according to you it is? Darkness, okay. Not actually what I was expecting. Sketch, little closer. Depths or outline, even more closer, I would say. So start thinking about what Gopi has said. Contrast, no. Start thinking about depths or outline. See, uh, don't get into technical part. Don't get into technical. For a normal user, what will you call it as? The input image when transformed to the output image, what do you call that operation as? Just like earlier, as a normal user, we said it's blurring. So here, outline, okay, blackboard image, I can say I'm convinced. Outline, okay. Any more thing, any more closer name, black and white. Okay, it is not actually a black and white. If you recall the black and white images of fashion MNIST or the digits, the image actually looks as it is. This is not black and white. Though it is black and white, but it's not actually pure black and white. It's something very close to black and white. Ah, Gopi, you nailed it. Gopi nailed it. Yes, is absolutely correct. This is an operation of edge detection. Do you all agree? Do you all agree? Edge detection? Yes. Right. Yes. So I want you to have a look at this. See, when I was learning, when I was doing my engineering in the final year, there was an optional subject, and the subject name was image processing. Over there, we used to be given the images purely in the pixel form, and we used to, and they used to ask us to apply operation. So apply blur operation, and there were various types of filters available. Like this is a simple blur one, box blur, this is a Gaussian blur, and many other types. So if I actually take you through this, I'll show you with the help of example. So in the labs, we had actually coded all of this. This happened somewhere in the year 2008, 2009 in C language, not in Python. But anyways, I have got this. I'm running this. You see the input and the output image. Left side is the input image, right side is the blurred image. Then similarly for sharpening, this type of filter is used. I run it. And left side is the input image, right side is the more sharpened image. Then unsharp mask. We'll go on a break very soon, just another few minutes. So this is unsharp mask, and in the same way, edge detection. So over there, this was one of the favorite problem. Teachers used to say this will sure shot come in the exam. One was the Previtt operator, one was the Sobel operator. These are nothing but filters, right? Invented by the person Sobel. And this was his kernel or filter. We will just apply. This is edge detection. This is for edge detection. And yes, no black and white, no blackboard, perfect edge detection, right? Now you understand it technically. So here, that's what we understand. Now, so what do we understand so far? So far, we understood that convolution is nothing but an image modifier. This is our very first perspective on convolution. It is nothing but a feature transformation on an image. Now the question, what is making one convolution operation, which is blur, different from another operation like edge detection? And the answer was what? What makes one convolution different from another? You only tell me, what have you realized? Who was responsible for yes? It is the kernel or the filter. That's an absolutely correct answer. And obviously, you might have a question. Then Darshan, quickly tell us, how do we actually design the filter? Because I'm very dying to kind of apply this. I would say, hold on. We will see it later after some time. Right? तो थोड़ा सा hold on, and we will be seeing it later after some time. Okay. Then after that, one last thing, and then we proceed on a break. I want to talk about the mechanics of convolution. Now, today we all know how an image looks like. So an image, let's consider this image. I'm going to call the dimension of the image as n cross n. And this filter I'm going to convey by k, which is k cross k. Obviously, I understand images are not always square. Images can be square also. It can be rectangular also. Like, for example, that's how our television is. And that's how our phone is. But for now, we are assuming that we are working only on the square images. So here I am having a input image of size 4 cross 4 and a kernel of size 2 cross 2. That also I'm assuming it to be square. And understand over here how these things are happening. Now, what am I going to do essentially is I am actually going to take up this filter and I'm going to place it here and I'm going to do some operation. After that operation is done, I am going to move this filter here. The same filter, I'm going to move it here and I'm going to do some operation with these 4 numbers. After this is done, I'm going to move the filter further ahead and I'm going to do some operation. Now the thing is, can I move it further ahead? No, because it will go outside. So I will not do this, but I'll come down and I'll do that operation. Then I'll do it here. Then I'll do it here. Can I go further ahead? No. So I'll come down and do that operation. Then I'll do it here. Then I'll do it here. Can I go further ahead? No. So I will stop. So basically, you realize that it is being done here, 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 then here, 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 and then here, here, here. Let's do it now. You see, this is the filter, this is the image. I will be doing multiplication of this because see, these are the corresponding matching values. So you know what will I do? I'll do a very simple operation. 0 and 1 are matching, 0 multiplied by 1 plus 10 and 0 are matching, 10 multiplied by 0 plus 20 and 0 are matching, plus 30 and 2 are matching, 0, this is 0, this is 0, this is 60. I write my 60 here. Next, I'll move this filter ahead. So now the filter which was at this position has moved on at this position. So I have consider a sliding movement of just 1 pixel. And now I again do the operation 10 into 1 plus 10 into 0 plus 30 into 0 plus 30 into 2, I get 70. Then I repeat it further. 10 into 1 plus 0 into 0 plus 30 into 0 plus 20 into 2, I get 50. Now I cannot go further to the right. From here, I went to here. And from here, I went to here. Now I go down. 20 into 1 plus 30 into 0 plus 10 into 0 plus 20 into 2, I get 60. Can I say, guys, try the rest yourself and you will be able to do it? Yes or no? Just answer me that. Yes, then you only do it. I'm not doing it. If you have so much overconfidence or confidence, do it. I'm pretty sure you will be doing it. It's a very simple operation. Just, this is the final answer. I didn't include it over here. And this is your convolution operation. This is your convolution operation. But there is one interesting thing before we go on a break I want to talk about. I don't know how many of you realize, do you see any small drawback of this? If you compare the input and output, can you come up to any small drawback? If it comes quickly to your mind, if you compare the input and output, yes. The Correct answer is given by Nishant and Shanu and Sandeep. This input image, which was n cross n, kernel, which was k cross k. Let's actually call just as n and just as k. So input image was of size this, kernel was of this, and this is of size 3 cross 3, which means it is smaller than this. And you know, this is computed like this, n minus k plus 1. So this is 4, this is 2. You can check it out. 4 minus 2 plus 1, which is equal to 3. And that is what is the answer. So that means my output image is becoming smaller in the convolutional neural network. Right. We will just pause over here. Fine, it is becoming smaller. We have made a note of it. So the only way one can figure out whether it is working good or bad is from your words, right? If you don't speak out, then how will it be clear? So, yeah, that's important. So with all this understanding, I am going ahead. So here, we understood the mechanics of convolution. We also understood that the input image is big and the output image is small. This was 4 cross 4. This is 3 cross 3. And the filter is responsible for it. So yeah, that's what I wanted to say. Now we talk about mode. Now, what is mode? Mode is exactly not the day mode and the night mode. Mode is exactly what you just studied. So over here, the mode is valid. Valid is basically when the input is n, kernel is k, and the output is n minus k plus 1. So over here, this is exactly what was the valid mode, where the input is big and the output will always be smaller. Input is big, output will always be smaller. Now you say, no, Darshan, I actually want the output to be of the same size. No problem. They have found out a solution to that also. They say that if you want the output to be of the same size as the input, then you do padding. Padding in the sense, add imaginary zeros around the input, something like this. So if your input image, if you see right now, the input image is 5 cross 5. But what did I do? I padded zeros and the image become 7 cross 7. So padded zero means you add zeros around the sides and it became this. Okay. Now the input image becomes 7 cross 7. And if you see the convolution filter, it's actually moving from here, right? And the output is again 5 cross 5. Now output is not 7 cross 7, output is 5 cross 5, but it matches exactly the input one. It exactly matches the input one. And that is exactly where I say, see, and it will start from here. It will come here, see here, then move. And that's why these values are being plucked out. So here input is n, kernel is k, and output is also n only. So that's an important thing that we see. Input is n, kernel is k, and output is also n only. And if you want the output image to be even more bigger, you also have the full mode where we could extend it further by adding further more zero layers. But it is not very common these days. So it says that if the input is n, kernel is k, if the input is n, kernel is k, output is n plus k minus 1, which is 6 minus 1, which is, so this 4 cross 4 image, 2 cross 2 kernel, and 5 cross 5 output. But it is not very common. So to summarize, the modes that we have learned so far, I say for the input image n, kernel has k. There is a valid mode which gives the output smaller, and that's typical. There is same mode which gives the output of the same size. That's also typically used. And there is a full mode where the output is bigger and it's not very typical. This is what we understand. So overall, Raj asked for a quick recap. We don't actually have time for it, but since he requested, we'll just quickly skim through it. So first we understood convolution needs addition and multiplication. Then we understood convolution without mathematics, where we figured out that it is uh, nothing more than image modifier, where it was blurring here. And in the next scenario, it was edge detection. Then after that, we understood that the main reason for this image to be modified was the filter. Then we looked at the convolution operation where we apply this filter over the image and it moves left to right. Right? This is something which is very obvious. We have just seen it. And then you completed this. And then after that, we just looked at the various types of modes, which we have just seen and summarized over here. So yeah, that's exactly what we have in over here. I hope this serves the purpose, Raj, and we are good to go ahead. Welcome, Raj. Yes. Next one. A new perspective on convolution. Now what? Welcome. So I was saying, let's now go through a new perspective on convolution. Now, see, what was the first perspective on convolution? The first perspective on convolution, our first perspective on convolution was it is image modifier. Now we are looking at a new perspective. Why? Why? So now what? The reason why this is important is if you don't have, the reason why this is more important is you don't have to think of a filter as an abstract concept. In fact, it is just a pattern finder. This actually makes the term filter a lot more sense because it will filter out the things related to the pattern contained in the filter by setting them to 0 and keeping the rest of the things related to the pattern. Person, what are you saying? We are not understanding. Okay. Okay. If you're not understanding, let me make you understand this with the help of a very, very simple example. So let's play a small, sweet game. And my dear friends, in this image, you have to find out a honeybee. I just kind of labeled the objects so that you can see it clearly. And yeah, you have exactly 30 seconds to spot a honeybee. No extra time. Tick, tick, 30. Tick, tick, 29. Tick, tick, 27. Tick, tick, 25. 20. 17. 14. 10. You're gonna lose. 7. 5. 3. 1, 0. Ha 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 ha. Out of 37, Sandeep was able to find it. Rahul was able to find it. Karthik said, and near six tail. Ah, ha, 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 ha. So now those of you who could not see it, see what these guys found out and confirm if that is correct. I'm still not pointing out anywhere in this image. Are you all able to locate it now? Right. And if you're not able to locate it earlier, it's okay. It was just a game. And these guys were also lucky, right? Maybe sometime later in some other image, you are able to find it faster than them. It's just a luck. There is nothing intelligence required over here. But if you had to do this thing intelligently, if I say, that, hey, no mistakes, there can be more than one honeybees. No mistakes. Don't miss out even a single honeybee. If you find out all the honeybees correctly, you get a reward of 500 rupees. If you miss out even a single one, you have to pay 200 rupees from your pocket. So if I say there are more than one honeybees, and actually let's say there are 6 honeybees, if you find out all the 6, you bag away 500 rupees. But if you find out less than that and say that, okay, there are 4 honeybees, you have to pay 200. So in that scenario, you will have to go for a structured approach to find out the things. So think about it. What can be the structured approach? See, now you cannot rely on randomly finding here, 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 here. You will look, you'll look into this part of the image. Honeybee there, not there. Then this, there, not there. There, not there. So these are your eyes looking here, then looking here, then looking here, and so on and so forth till here. Then you move down, found honeybee, no, 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 no. So you follow this approach, left to right, top to bottom. This is the approach that you follow throughout. A time will come where in one of this box, you are likely to locate a honeybee. Now, with this approach, even if there are more than one honeybees, you are likely to not miss out even a single honeybee. And that's exactly what I was saying. This boxes that we are moving around. So I was saying that these are nothing but the filters. And I was saying that you don't think of filter as an abstract concept. In fact, it is just a pattern finder. This actually makes the term filter having a lot more sense. So everything which is related to the pattern, like honeybee, you keep it. The rest all things you make it as 0. So this red honeybee ka pixel, this red circle ka pixel, you keep it. Rest all you make it null. So moral of the story, from here, what I want to say is that what are you basically doing? Now consider the similar example of Aishwarya Rai. Okay, now don't teach me by saying that Darshan sir, this is not Aishwarya Rai. I know that. I know that. Huh? This is not Aishwarya Rai. But let me call it Aishwarya Rai. Huh? Let us be happy with that only. Okay. Now, this is the input image of Aishwarya Rai. And in the filter, I'm actually searching for what? Specifically, let's say I am searching for the right eye of Aishwarya Rai. It's found here. So only that pattern is highlighted, rest all is blacked out. So what I do over here is here basically I give a high number and here all low numbers. Right, here high number and here all low numbers. Right. So So looking at this, how did you locate the right eye of Aishwarya Rai? Again, by moving left to right, top to bottom, and wherever found, got it, right? You say, gotcha. So my second perspective on convolution is that it is basically you are looking for a honeybee. So it is nothing but you are looking for a particular pattern. Like you are looking for a right eye, you are looking for a honeybee. How? By sliding left to right. So I call it as a sliding pattern finder. I call it as a sliding pattern finder that passes through the entire image. That passes through the entire image. And this is our second perspective on convolution. Remember these two perspectives, you will be needing it when I start with the actual architecture. This is not the architecture. These are the basic fundamental things needed to understand the architecture. Number one, it's an image modifier where you looked at the various modes. Number two, as I told you, it is a sliding pattern finder. Okay. Now, obviously, anyone would have a question. Why are you doing this? Why? Why are you actually doing this? See, the answer is very, very simple. If you consider a fully connected artificial neural network for an MNIST dataset, luckily, all of the images were 28 cross 28, which means when you flatten it, you get a vector of 784, comma. And there is one more data set which we'll be working on very soon after the fashion MNIST, which is called a CFAR10 data set. CFAR10 data set consists of slightly bigger images. 32 cross 32. And by the way, they all are color images. So in color images, you will have 3 color channels. I'll show you how a color image looks like. So color image is nothing but a combination of red, green, and blue layers to get this beautiful image. So in black and white images, you only had one layer, which had numbers from 0 to 255 in every pixel. But now you have three. You have three, as you see. So essentially, you don't have a single layer, but you have 3 layers over here, as you see in over here. Each of these are having values in the range 0 to 255. What you see here is they have already divided it by 255. That is, these all are normalized values. Okay. Now, so in our CFAR, the images are of size 32 into 32 into 3. When I flatten it, it becomes 3072, comma size vector. Now, let me tell you that this 32 cross 32, I would say that this is still of a very modest size image to see. If you look at the modern convolutional neural network, over there you have VGG network, which is considered to be one of the best CNN, visual geometry group. We'll be learning this in the transfer learning topic. It is just a bigger convolutional neural network, and let me tell you, they process image of size 224 cross 224. So that means if I flatten it, it becomes 1,50,528, comma. So do you realize these many are the features? So now this time, like an idiot, your data set after flattening will be consisting of a dependent variable and independent variable going from x1 to x150528, and you try to understand the relationship in between these things. Isn't that really crazy? 1,50,528 independent variables. पागलपंती है ना? Crazy to understand the relationship, and any big model as well will get confused. Any neural network will get confused. Till this point of time, we had only 784, but now it is 1,50,000. Are yes or no? Don't you think this is crazy? It's idioticness. Training on this thing, right? And this is still okay. Let me, I am opening my phone. I'm opening my phone right now, and I want to see the size of an image. I'm going to my gallery of the phone. I'm just looking at one of the latest image, which I have taken on 27th August 2025. I see the size of the image as 4,284 cross 5712 cross 3, obviously color image. Could you tell me over here what is the result of multiplication of these? This into this into this. Calculators, please. Don't go wrong. This into 3. 73410. 73410. 624. How much it is? Is it 7 crore or 73 crore? How do you call it in simple terms? 7 crore or 73 crore or 73 lakhs? How much is it? Mota, what is the figure? 7 crore, 34 lakhs? Yes. If I have to process the image taken from my phone, it is 7 crore, 7.34 crore independent variables. Now, do you understand that going for a simple thing like this is not going to make sense, right? You can imagine that this is too much. This is too much, right? So I would say over here, that is much too large for a neural network. So why do this? See, but there is another good reason, to use the weights here, which is why you don't need different weights every time. What did I tell you? Convolution is actually correlation and filter is really a pattern finder. So in this scenario, we actually find the same filter to look at the locations in the image. And this is the idea of translational variance. So obviously we can't do that, and therefore we are going for convolutional variance. Sorry, convolutional network. We'll dig more into this. But you can understand it's crazy. The next thing is, now I'm talking about convolution on color images. We just saw that a color images is not just having a height and a width, but rather it has a height, it has a width, and it has color channels. So this image is 5 cross 10 cross 3 or 5 comma 10 comma 3, where this is the red channel, this is the green channel, and this is the blue channel. Now, how is the convolution applied? Now, the big problem, the big problem that you are going to see, pay attention. This is very, very important. So here, you have understood the convolution operation. Huh? You understood the convolution operation on the MNIST dataset ka image or any black and white image where I said, if the input image is of size n and if the kernel is of size k, I'll not even write what is that. So if the input image is, let's say, uh, 20, let's consider MNIST only. I'm considering a black and white image, right? So let's consider the input image 28 cross 28. The filter or the kernel is 3 cross 3. So when I do the convolution operation, let's say I am using over here the valid mode. So the output is going to be n minus k plus 1, which is 28 minus 3 plus 1, which is 28 minus is 25, 26. So the output will be 26 cross 26. That's okay. So therefore, the output will be 26 cross 26. Now understand, the input image is 28 cross 28, which clearly says that it is two-dimensional in nature. The kernel is 3 cross 3, which also clearly says that it is two-dimensional in nature, two dimensions, na? And the output image is 26 cross 26. This also clearly specifies that it is two-dimensional in nature. That's an important thing. That's an important thing. Now, this is an important thing because I am trying to tell you all from this that the input is 2D and the output is also 2D. I'm trying to tell you from this that the input image is 2D and the output is also 2D. I repeat, I'm trying to tell you that the input is 2D and output is also 2D. But have a look at convolution on color images. So in color images, obviously you have color channel. One would be a red channel. One would be a green channel, and one would be a blue channel, right? So here we know that we have red, green, and blue, three color channels over here, right? And we clearly understand in this scenario that the input image is, let's assume it is input image is 28 comma 28 comma 3, where I say it is three-dimensional. My kernel, let's say I am going for a kernel which is 3 in height, 3 in this, and 3 over here. So it is 3 cross 3 cross 3, which is again 3 dimension. So it's quite obvious here also you will have a red layer, and here also you have a green layer, and you have a blue layer. So basically now pay attention. Now the important thing over here. Now if this is 28 cross 28, this is 3 cross 3. So what is going to happen? See here, just like one layer was overlapping on one layer of the image. So here 3 layers will be overlapping on the corresponding 3 layers of the image. Am I correct or not? Here one was overlapping. Here all the 3 are overlapping. So, right, 3 layers are overlapping with the 3 layers of the image. Kernel layers are overlapping with the corresponding 3 image layers of the image. Do you agree to that? Right? That's an important point. Huh? Everyone agrees now. Did you get that point? This figure I have sketched with the inks. I hope that is clear to all of you. Please confirm before we go ahead. If you have a question, this is the time to ask. Okay, great. Thank you, everyone. So, because you understand this, right? For 3D, can you please go one more time? Yeah, see here, Sandeep. Input is 3D. So you have R, G, and B, three layers, which I have perfectly sketched in red, blue, and green is pink over here. So three layers are there. One layer, two layer, and one more layer, three layers, right? One, two, three. One, two, three. Three layers are there. Kernel is also three-dimensional. So kernel also has three layers, one which is going to overlap with the red, one which is going to overlap with green, and the third which will overlap with blue. So technically now if you look into my 3D kernel and 3D image, right now we clearly see that this much part of the image is overlapping with this much part of the kernel. Does that make sense to you, Sandeep? Right. So now understand over here, technically, if you realize, so I'll just say this much part of the image, this much part of the image overlaps with this much part of the kernel. But wait a minute, you have one such part of the red image part overlapping with the red kernel part. In the same way, you have green overlapping with green. In the same way, you have blue overlapping with blue. Right? Three layers are there. Raj, I'm not understanding. Which side image are you talking about? I'm writing on the screen. I hope you are able to see it. I'm inking with the blue boxes on the screen. Everyone, are you able to see that? Acha, now how do you want me to show the side image? I don't have it. Imagination. Imagination. I don't have it. This is what we have. You have to imagine. Yes. So the three layers are overlapping with this. Now, when a convolution is going to happen, we know that this into this plus this into this plus this into this, right? Image is having RGB and separate is fine. Why should kernel have RGB? Wouldn't there be a single layer of filter and apply across all? No. How? See, you are try to approach the problem like a software developer, Amit. So Amit over here, the reason we need three layers of the kernel is how the multiplication will happen, Amit. For the multiplication to happen across the three layers, technically in the back end, there will be a nested for loop which will be written, which will go through the corresponding values one by one, layer by layer. So you can't essentially use a single filter multiplied everywhere. Technically, that will not work. So how do you develop a logic? That's the reason you need to have three layers. The three layers can definitely have the same content, but you need three for sure. Kernel for different layer will be different. Yes, they will be different. They can be same also. Right? They can be same, they can be different. As I told you earlier, these filters are nothing but the weights of the convolution, which will be learned by the CNN network during the back propagation. So what they could be, no one knows. No one knows. So now, don't complicate the concept so much. It's not that complicated as you have gone into depth of thinking it. It's not really that complicated as well. What have we learned so far is in this image was 2D, kernel applied was 2D, and the output image is also 2D. In this image, the image is 3D, kernel is 3D, and the output image that you will get will be how? In this 3D image, the three layers of the kernel will overlap with the 3 layers of the image. So this can be image ka 3 layers, just for example, and this can be kernel ka 3 layers. So what is going to happen? This into this, plus this into this, plus this into this, so on till last. That's going to give you one value. Similarly, convolution happens over here, that's going to give you one value. Similarly, convolution happens over here, that's going to give you one value. Let's say this value is 2, this is 4, and this is 9. What is the total of all? 2 plus 4, 6, 9 plus 6, 15. The number 15 gets saved here. Then this filter moves ahead. Let's say this gives the number 16, that gets saved here. That gets saved here. Then this moves ahead. Let's say this gives you answer 21, that gets saved here. Then let's say it moves over here. Let's say this gave you answer as 61, that gets saved here. Let's say it moved over here. Convolution gave you the answer 29, saved here. Moved here. Let's say this gave you answer as 65. Similarly, here, and here, giving us, let's say, answers like 11, 13, 29. What do you realize over here is the output image, friends, is what? Whatever be the dimension, so ideally it is n minus k plus 1. So if it is 28, so 28 minus 3 is 25, plus 1 it is 26. But the thing is, the output is 26 cross 26 only, not 3 cross 3 ideally. It is ideally 26 cross 26. Where we realize that it is only two-dimensional in nature. We realize that the output is two-dimensional. This is the most important point I wanted to tell you. In the grayscale images, this is matching. The input and output dimensions are matching. But here, the input and the output dimensions are not matching. So we realize that the same size in the depth dimension, and we see that this is not matching. And the thing is, neural networks, right? So we understand it's not matching. Neural networks always have a repeating structure. But here it is not actually matching, and this is a problem. This is the problem which was encountered during the convolutional neural network. That is the only point that you have to remember. If you understood, awesome. Even if you don't understood, just remember this. In black and white images, you see grayscale image. Input is 2D, output is 2D. But in color image, input is 3D, but the output is 2D. So over here, that is the reason the problem occurs. So neural networks prefer uniformity. So when you have an input image of, let's say, 28 cross 28 cross 3, which is 3D, and the input image, which is 3 cross 3 cross 3, which is 3D, the output is h minus k plus 1 cross h minus k plus 1, which is 26 cross 26, which is 2D. We know that neural networks always have a repeating structure, that is, may need uniformity. So when it goes from input layer to hidden layer 1 to hidden layer 2 to output layer, we need uniformity. So for a dense layer, if the input is 1D, the output is also 1D. And see, if this is turning out to be the input, if the input is 3D, the output is also expected to be 3D, so that the next one can process it and give the output as 3D. But if the input is 3D and the output is not 3D, but instead of that, if it is 2D, then there is a problem. then there is a problem. So you cannot actually feed the output of one layer to another, because in our case, output is 2D and the input is 3D. So how do we solve this? And that's exactly what we are going to see now. Is that clear to everyone? This is how the operation happens, Ramani. Ultimately, it is in a loop, right? Try to understand it like a developer. These three values will not give you three different answers. Convolution operation on a three-dimensional array is applied like this. The total comes out as a single value. Because you are in a loop, right? See, technically, in a loop, you are applying this formula. This is the image and this is the kernel. Technically, you are applying this formula. So technically, if you actually try to implement this, Ramani, in a raw way, then if you are trying to implement this ideally in a raw way, then effectively you are doing this, Ramani. So how do you expect the value to be a single value? You see, a for inside a for inside a for inside a for, that gives you the answer. So it's either running in a loop, right? So our imagination will not work. The working of the loop will work. That's why I don't get into so much details, right? So that was a very detailed architecture when they give me 4 hours to just teach the CNN. But that's okay. So therefore, what I'm doing is I'm going for multiple features. So if you remember the filter or the kernel, what did I say? What is the filter or a kernel? It is like the second perspective. It is like a sliding pattern finder. So in machine learning, we have multiple features like how each heading unit in a network that represents a different feature based on the input. That kind of makes sense. But if you're looking at an image, we would want to identify multiple features in this image. For example, if you are building a facial recognition system, let's say this is Aishwarya Rai's photo. Now, when a filter might look for an eye and another filter can look for a nose, then it will make more sense because we want to try to find out multiple features. This is something very important. So I know that I'm looking for a right eye. I found that over here, which you see over here highlighted. I'm looking for a nose. I found that over here, which you see over here highlighted. So this is filter one, this is filter two. In the same way, let's say I apply filter 100. Many features like this I applied. So this image, let's say, was of the size 28 cross 28 cross 3. This image was of the size 28 cross 28 cross 3. And the kernel is of size 3 cross 3 cross 3. Assumption, I can choose any size of kernel. Right now, I'm assuming 3 cross 3 only. Right? So, yeah, this is the kernel. This is of size 3 cross 3 cross 3. So, the output image is what? The output image is 26 cross 26. This is also 26 cross 26. I know this is two-dimensional in nature. I know this is two-dimensional in nature. But in this way, I have got 100 outputs. Output 1, output 2, right? Output 100. I have got 100 outputs over here. So you know what is my idea? My idea is very simple. That's your first output. That's my first output. I hate this second time it happened. So this was my first output. That is my second output. That is my third output. So on, this is my 100th output. 1, 2, 3, 100. So what am I doing? I am stacking the 100 outputs. One after another. So now the output is what? So this is 26. And as we understand, this is also 26. So therefore, the output is of dimension 26 cross 26 cross 100. And therefore, now it has become 3D. And by the way, this 100, this is no more a color channel, right? But these are nothing but the features. They are no more the color channel, but these are nothing but the features. This is something which is very, very important for everyone to know. So technically, I call them as feature maps. Technically, I call them as a feature map. Or I can also call them as the number of channels. So now my problem is solved because now my input is 3D. Now my filter is also 3D. And my output is also 3D. Are you all understanding how smartly the researchers solved this issue? So this was the idea behind applying convolution on color images, because very soon we have to migrate to color images. We will not be continuously working on black and white images. Who takes black and white images today? No one, right? So this is the idea how we essentially achieve it. That's a very, very important thing that we learned. Very, very important thing. Output is 3D, but the third dimension is not color. It is number of feature maps or the number of channels. Dimension changed, but see, ultimately we are not concerned with the dimensions. I am concerned with 3D, 3D, 3D. The output cannot be 2D. Else the next hidden layer will say that, sorry, it is not in the right format. I cannot process the image. That was the entire efforts about. So this is what we said, that when you have multiple things swapped over each other, first one, second one, and then what they say is you stack those things. 1, 2, 100, right? 1, 2, and you have 100 over here. And then what is the third dimension? Well, as I told you, the third dimension, it is certainly not color. So over here, the input was nothing but a true color image, height cross width cross 3 color channel. And after subsequent application of this, so after applying various convolutions, it will still have a height and width and some arbitrary number. And this arbitrary number is what we call as number of channels or number of feature maps. This is something which is very, very important.
And with that, we have come to the end of our full course. You now have the tools to build, train, and optimize models, and with more practice, you will continue to improve. If you have any doubts or questions, ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn.